In terms of logistics, please, if you have questions for the talks, raise your hand or you can post them in the chat. And for the speakers, you have a 20-minute slot, so we'll try and leave about 5 minutes for questions. So I'll give you a warning at 13 minutes, which would be kind of the cue to wrap up over the next couple of minutes. So I think that was all I had to say. We'll go ahead and get started with the science talks. And our first speaker is Xiaoning Wu, who's going to tell us about ENSO and MJO and aquaplanet simulations. So Xiaoning, if you want to go ahead and share your slides. So we can see your slides, but you're muted.
Okay, here we go. Can you see the slides?
Yep, looks good.
Great. Thanks everybody for being here. It's my pleasure to open up the CVC working group meeting today with some of the more exotic or idealized experiments. So the title here is making some pretty bold claims that I am aware of. And although I think a starting point is to say that features such as ENSO and MJO are of major interest to the modeling community. So let's see if the idealized words are going to tell us something about how they are maybe represented in the more realistic type of models. This work comes out of a collaboration with NCAR-CGD, especially with the oceanography section, in helping to develop the fully coupled idealized configurations of CESM with dynamic ocean. And this work is also made possible by a long list of generous collaborators listed here. And also I would like to acknowledge some of the people in this room that have given me really helpful feedbacks when I did my presentation at the AGU in the winter. So to start off with the rationale for, or the motivation for looking at this type of features in the idealized setup is to borrow from a biological analog being put forth by other scientists in the field advocating for the use of a simplified model, even though oftentimes our major interest is in the intricate real system of the Earth's climate as our interest in the human body. And in the process of investigating these things, oftentimes the simpler systems can help us see more clearly some of the processes. And in many ways, even the conventional or simple type of models is already a simplification of the real world. And but even at that level, we are still dealing with a lot of details in the different components. So if we take it even a step further to simplify it in various ways, and in this case, we're looking at simplifications of the ocean, of the shape of the ocean basin or the ocean geometry. So hopefully that would be one step down the hierarchy, which would where the phenomenon that we see and interpret in this simpler system can loop back to help us understand the more complex system. And we are, and in the details, we're looking at the two simplified setups in particular. The first setup, called the ridge, is basically a rectangular ocean basin that has a lot in common in the Pacific, with the Pacific, as we'll see later. So the entire planet is ocean covered, other than a single pole-to-pole strip continent. And the other configuration on the right is called aqua, which is almost entirely ocean covered, other than like two polar caps that's required by the model grid. And for those of us coming from the atmospheric community, oftentimes zonally uniform aqua planets are to be seen as like the first order simplification. However, when the ocean dynamics is involved, we will see that the behavior of the aqua planet is not necessarily the easiest to draw parallels for the real world. for the ocean components, it's basic, for all the model components, it's basically all taken from CESM, and with the 1 degree atmosphere and roughly 2 degree ocean with equatorial refinement. We have retained an idealized seasonal cycle, and the simulation has run for 500 years, which brings it to reasonable equilibrium with regard to the top of the atmosphere balance. So just to have a closer look at what those idealized words look at, here we're looking at the seasonal cycle of the sea surface temperature. And in the rectangular ocean representation of ridge, I think it's pretty nice that it does capture a lot of the interesting features in the realistic world with regard to the western wormhole on the western side of like either the Atlantic or the Pacific, and the eastern coast town, which is really a predominant feature in the realistic Pacific Ocean, and here we have it on the eastern side of this idealized ocean basin. When we take that ridge continent away, and when we're looking at a zonally uniform aqua coupled to a dynamic ocean, still the equatorial upwelling is still there, but now it's extended globally, and without the contribution from the eastern boundary currents as the real Pacific or the ridge continent have, now the magnitude of this upwelling has been reduced, and we'll see how this global belt of cold band would have an impact on the overall climate and in the variability. And furthermore, look at this analog with the Pacific. On the left, we are seeing just like a pretty standard textbook schematic of how in the Pacific we have this zonal contrast of thermocline deepening towards the western side, and the atmosphere in response to the wormhole and the cold town, we have this water circulation with a convection on the western side and subsidence over the relatively cold and dry eastern region. And a lot of these features are pretty well represented in the ridge continent, with the ridge planet, where we have in the ocean predominantly due to ocean dynamics and the west and then the westward intensification, we have the wormhole on the western side and the deepening thermocline. And in the atmosphere, correspondingly, we have the ascending branch of this Walker-like circulation over this wormhole region, and the subsidence over the cold and dry region. So that's like a match to the schematic on the left. And when we look at aqua, when we take that zonal contrast away, then what corresponds to the global belt of equatorial upwelling is just a really shallow thermocline in the immediate equatorial region. And in the atmosphere, again, we lose all zonal contrast, and we are just looking at subsidence over the equatorial region, and pretty near uniform massive zonal flows that if we take a closer look here, to look at the zonally average atmospheric circulation, we see that on the ridge planet, because of the zonal gradient, a lot of these features are just reduced in magnitude, including the easterly zonal wind in the tropics, and also some of these jets at in more of the subtropical regions. And I'm putting some like eyeball estimates of the speed of the mean zonal wind here, because that would relate to how the variability aspect plays out. So those are the major features of the mean climate of the aqua and the ridge planets. And now moving on to the features in variability that's of interest. So the first one we're looking at is the MJO mode, or the subseasonal to seasonal variability. In the real Earth situation, it's often represented by in the Wheeler-Clarence diagram by this bullseye power signal that separates itself from the equatorial Kelvin waves and occupies the the frequency band of say like 20 to 100 days and stretching into zonal wave number 3 or 4. On the rich planet, here the Wheeler-Classic theorem is having I think 2 features of interest. One of them is that we do see this MJO-like mode, which is pretty distinctively separated from the Kelvin waves and going and stretching to zonal wave number closer to 4 or even 5. And the other feature that I've put here is that so this blue dashed lines are I would say another flavor of the dispersal relations, which includes the effect of a Doppler shifting by the background mean flow. Because in more of like the vanilla type of Wheeler-Classic diagrams, the dispersion curves that we're seeing assumes a 0 mean flow. And because for both aqua and rich planets, we do see that we have this effect of the easterly mean flow in the tropics. If we put that in, if we include this impact, it might better describe the power spectra that we're seeing. For the rich planet, because it's reasonably Pacific-like, I think even the regular dispersion curves are working reasonably well. But if we move to the aqua planet, where the mean flow is pretty massive, then without considering the Doppler shifting, it would be harder to explain what's happening with the easterly waves. So that's a side note on the impact of mean flow on all these convectively coupled equatorial waves. Looking back to the MJO discussion, in the aqua planets, in the seasonal spectral band, we see that it does have a seasonal-ish mode, but the separation from Kelvin waves is a lot less clear. So that's one of the, I think the seasonal or like intra-seasonal modes have been investigated oftentimes with in the context of the zonally uniform type of atmospheric only aqua planets. And I think it's an important or interesting point of contrast here in terms of like what would contribute to its separation from the Kelvin waves. And furthermore, on how MJO propagates, in the realistic Earth system, oftentimes the starting point is to be said to be in somewhere in the Indian Ocean. And to make that analogy, I am picking this box, which is on the western side of the climatological warm pool here, and looking at the lag correlation to see how this signal is propagating. And for the aqua planet, the longitude really doesn't matter, could be anywhere. Now, here we're looking at the lag correlation in both precipitation and the low level U wind of that filtered signal between 20 to 100 days. And in the Earth scenario, we see the propagation of precipitation signal until it reaches the region, the Eastern Pacific region, which is drier, and the precipitation signal gradually fades out. And in the dynamic component, in the U wind, the propagation would slow down in response to reaching this dry region. And we see that on the rich planet, these characteristics are captured relatively well in how the precipitation kind of propagates over the warm pole region before fading away. And the dynamic signal in the U wind would also be slowing down as we reach the area with the eastern basin upwelling. So I think it's a pretty curious aspect that this massive simplification also captures some of those features. And for the aqua planet, because it's not uniform, then it's just like happening pretty uniformly. So now switching gear real quick into the other feature of interest, or the ENSO type of variability. On the left, we're looking at a typical Earth warming pattern and the power spectrum with the 3 to 5 periodicity. On the rich planet, which is a Pacific analog, we do see a similar pattern of cold town warming, and also with the periodicity of 3 to 5 years within the usual ENSO band. I think it's a point of contrast of how, even though the size of the basin is pretty different, the periodicity is still somewhat constrained in this band. And because the ridge configuration is a rectangular Pacific, which is among some of the earliest models that's trying to explain what gives rise to ENSO. So a lot of the classical ENSO theories would still apply. However, when we go to the aquaplanet without a meridional boundary and without the wave reflection mechanisms, it's a major curiosity for me that the aquaplanet also shows this interannual variability dominated in the immediate equatorial region. So this is a major mystery that I'm trying to find out more about in terms of what gives rise to this timescale. And a very rough look at the ocean subsurface processes. Here we're looking at the composites of, if we use the term lineal very loosely to mean the warming of the equatorial upwelling region. And in the composites for the ridge configuration, we see this contrast in the zonal direction of warming on the eastern side near the surface, corresponding to the cooling on the western side along the climatological thermocline. And in aqua, we would not necessarily have any pattern in the zonal direction. So here we're looking at the zonally averaged composite. Sorry for missing a label here. So we're going from the ocean extent from 80 south to 80 north, and the equator in the middle. So in the equatorial warming years for aqua, we have warming in the immediate equatorial region and the subsurface cooling in the off-equatorial region. And I'm speculating a little bit in how this subsurface cooling might play a role in the phase switching, which might have some analog with what's happening for the ridge planet in the meridional, in the zonal direction. So this is still very much an ongoing work. And to wrap up, we've seen some interesting features in these idealized worlds. For the equatorial waves, we see the effect of a Doppler shifting. For MJO ingredients, the contrast can potentially tell us something about the factors that's affecting the propagation and how that mode would separate from the Kelvin waves. For ENSO ingredients, it's a major question for me on whether this aqua interannual mode is something physical or say real or relatable to the ridge or more realistic configurations. So a broader question for all of this is, to what extent do these features from the idealized world relate to the CMIP class of more complex configurations and potentially the real world? And I think there's definitely avenue for further research using this hierarchy for simplified models where we can like take away or add in additional aspects. Thank you for listening, and I will welcome any questions.
Thank you. So does anyone have any questions for Xiaoning? You can either raise your hands or post them in the chat. I'll give you a chance. So I guess I had one question, and I'm not an expert on this, but ENSO, the periodicity of ENSO is somewhat related to waves propagating across the Pacific, but you have the whole planet where the waves are propagating basically. So yeah, do you have any sense of why you end up with a very similar time scale?
Yeah, this is one of the major questions that I'm thinking about in terms of how much of the control of this time scale has to do with the zonal propagation of those waves, or if it's mostly controlled by something that's happening in the meridional direction with some of the atmospheric, like maybe stochastic processes, and how the ocean thermocline responds to how the wind stress is varying on the surface. So I still tend to think that the time scale is most likely due to the ocean processes in the interior. So that's something that I'm trying to work out more.
Yeah, it'll be interesting. Any more questions? One in the chat from Anish. I don't know, do you want to unmute or shall I read it out? Oh, carry on.
Okay, sorry. Yeah, thanks for the nice presentation, Shannon, and a very interesting work. I was wondering if you'd be doing any process-based diagnostics to understand what's driving the kind of equatorial wave behavior you're seeing. So something like a moist static energy budget, or there are other diagnostics that look at moisture mode hypothesis that drives the MJO, right? And another question that was somewhat related is, have you looked at the anti-symmetric spectrum in the wave number frequency space? And do you see energy in the MRG waves as well as the MJO band and the anti-symmetric?
Yeah. Those are great questions. With regard to the analysis in the moist static energy, that's definitely one of the further diagnostics that we can do with regard to like some of the previous research on if we impose a wormhole in the zonally symmetric aquaplanet, how that might enhance some of the MJO signals. So, and that's relatable. And for the anti-symmetric part of the spectrum, I think the MJO signal there is like not very strong. But we can, yeah. Thanks for the suggestions.
Thanks.
Okay, thanks. I guess if you have any more questions for Zhaneng, you can post them in the chat. And we're at 9:20 now, so we'll move on to the next speaker. Thanks, Zhaneng. So the next speaker is Dylan Amaya, who will be talking about how air-sea coupling shapes the North American hydroclimate response to ice sheets.
Thanks, Isla. Can you guys hear me okay? I'm plugged into a mic and I'm not sure exactly if it's...
Yep, it's working well.
Okay, great. All right. Do you see presenter view or full screen?
Full screen.
Okay, awesome. Thank you. Yeah, thanks everybody for tuning in. Excited to be here. Glad we could get the CVC working group off the ground again this year, given the whole COVID situation. But I'd like to change gears a little bit and think about a paleo type question, but I think it has some interesting implications for how different high latitude signals might unfold in future climate change as well. But we're going to be looking at the role of air-sea coupling in shaping North American hydroclimate responses to different kind of high latitude forcing, which in this case is continental ice sheets. To give you some perspective on what this looks like, and sorry, I just really quickly want to acknowledge my co-authors on this as well. Alan Seltzers, who is at Hui, Chris Karnauskas at CU Boulder, Juan Laura, who's at Yale, Sally Zong, who's a former ASP postdoc, but is now at Johns Hopkins, and then Pedro Denizio, who's also at CU Boulder. But to, just sort of motivate this a little bit here. In modern day climate, this map is showing you sort of climatological precipitation values in the annual mean. And, I think it's no secret that the Pacific Northwest is really wet and the American Southwest is really dry. But that wasn't always the case. We have very good modeling and proxy evidence to suggest that, in about 20,000 years ago, when, we were at the peak of the last glacial maximum, the American Southwest was much wetter than today. And this is sort of an artist's rendition of what sort of the megafauna that California could support back then, because it was a lot more, there was a lot more rainfall, there was a lot more vegetation and wildlife. And as I said, there's really good proxy and model evidence to support this. I understand this is all really busy, but you don't really need to understand exactly everything on here. The catch here is that if you focus on this right panel here, you can see that these are different proxy estimates of what the LGM hydroclimate looked like. And the shading is showing you the ice sheet thickness. So you're just sort of seeing the edge of the Laurentide ice sheet during the LGM, and each dot is representing a proxy, and the color tells you whether it was drier or wetter than today. And basically what you're seeing is that in the Southwest, you get all these blues, which says it was wetter than today. And in the Northwest, you get, notably fewer records, but most of them are saying it was drier than today. And then looking at different models in the PMIP3 archive, each of these models are forced with our best guesses at what LGM boundary conditions looked like. And you can see that The blue is showing you what are the normal conditions, and red is showing you drier than modern conditions. And you can see that most models give you sort of a shift in the hydroclimate with this north-south dipole that agrees, generally speaking, with proxies as well. So, mechanistically, why did we think this happened? Well, for the longest time, some of the earliest theories about why this occurred had to do with the height of the Laurentide ice sheet. This is a topography map for modern day and during the LGM based on our best estimates of what the ice sheet looked like. And, this ice sheet was really tall. It was something like 3 kilometers tall. And the prevailing theory for a very long time was that, the North Pacific jet would interact with this ice sheet and get deflected southward. So that, in modern day, storms tend to make landfall in sort of the Northwest Pacific as the steering flow is sort of making landfall in the Pacific Northwest. Whereas in LGM, that might not have been the case. It might have been deflected southward. And all these storms were now making landfall in Southern California, where they could dump all their rain. But more recent studies have also pointed to the role of albedo. It's not just the height of the ice sheet, but also how shiny it is and the thermodynamic effects of that could have a really strong impact on stationary waves and the position of the jet. And again, this is busy. It's not super important that you understand the exact details, but in a recent paper by Roberts et al., they use some single forcing runs using HAD-CM3, where they turn on and off the ice sheet albedo. And basically what I'm trying to show you here is that there's a different summer stationary wave response that persists into the winter when you consider just albedo or just topography of the ice sheet. So this is sort of the overarching motivation of what we're after here today is, can we develop a mechanistic approach to determining whether, is it the mechanical tall aspects of the ice sheet or the thermodynamic bright aspects of the continental ice sheets in driving changes in West Coast hydroclimate during the LGM. And a lot of the early studies that have thought about this series of questions were limited to AGCM experiments, because the LGM is a really, it's an old period, right? It takes a long time to get dynamical ocean models up to speed, spun up. So you sort of by necessity, you were limited to AGCM experiments. So now what we're going to do is look at a nice spun up series of simulations to also ask the question, how do air-sea interactions or ocean dynamics modulate this overall response if we look across different kinds of ocean configurations? So let's look at the different kinds of experiments that we are analyzing here. These are all been run by Denizio et al. 2018. So I'll just refer you to this paper for the complete details on these experiments, but I'll try to give you a sense of what we're looking at. We have a pre-industrial control simulation, and each of these panels are going to be showing you surface height to give you a sense of how tall the ice sheet is, and you really can just focus on North America here to get a sense of what each run is doing. And then I'm also showing you an estimate of albedo. So this is top of the atmosphere upward shortwave. So in the control simulation, obviously we have low ice sheets that are relatively dark because it's not ice, it's just regular land. Whereas in the LGM climate simulation that we're going to be analyzing, we have really tall ice sheets that are very bright, in addition to other boundary condition changes, things like greenhouse gases are much lower, orbital forcing is different. And this is going to be sort of a full LGM climate. And we're going to look at a series of single forcing experiments, very similar to that Roberts et al. Paper, where we're looking at what we call a Green Mountain experiment, where we have just a tall ice sheet, and we set the land surface process or the land surface conditions back to pre-industrial values. So it's tall and dark ice sheet. And this will primarily isolate the impacts of mechanical forcing on the climate system, mechanical forcing of the Laurentide ice sheet in this case. And then we'll also compare this to what we call a White Mountain experiment, where we're going to have a tall and bright ice sheet, very similar to the LGM climate, but we're going to put all the other boundary conditions back to pre-industrial values. So the greenhouse gases and the orbital configuration of the White Mountain are the same as pre-industrial. So this should explicitly isolate the impacts of mechanical and thermodynamic forcing on the climate system. And differences between these two should also isolate the thermodynamic component by itself. So in addition to these different single forcing runs, the White Mountain and Green Mountain experiments were repeated across a variety of ocean configurations. There was an AGCM only experiment where we forced the model with the control climatological sea surface temperatures. So this should give us an idea of, what's the direct atmospheric response to these different boundary conditions. And then we also repeated it in a slab ocean setting and a dynamical ocean setting. And this will give us a better sense of, what's the relative role of air-sea interactions versus dynamical ocean adjustment in driving the ocean's modulation of the overall climate system response. And again, all runs were appropriately spun up. So when there was the dynamical ocean, it was run until it was in equilibrium, same for the slab and same for the AGCM. So I understand that was a lot, and I just want to give you a brief summary of what the simulations we're looking at are. These are the different boundary conditions that we can turn on and off, and the different ocean configurations for which we have additional simulations for. So for the LGM, again, these are all the boundary conditions that we have set to LGM levels. In the White Mountain case, we just have topography and albedo set to LGM levels. And for the Green Mountain case, we just have topography set to LGM levels. Where there's no X, that's all pre-industrial. And just to give you a more illustrative approach here, this is a Green Mountain. This is basically how tall the ice sheet was. It goes up to about 3,000 meters. And just indicating that, the Green Mountain ice sheet goes this high, but it's dark. And then the White Mountain is tall and bright. All right, so let's look at the results. Focus here on the top right. This is the full LGM minus control wintertime atmospheric circulation response. So this is zonal winds at 500 millibars. The shading is the anomaly and the contours are climatology. And what you can see is this southward shift in the jet that it happens in response to full LGM boundary conditions. And this leads to a general north-south shift in hydroclimate. So it's drier in the northwest and wetter in the southwest. And this is, again, in line with proxies and aligned with other modeling experiments. So this is sort of the answer. And now the question is, which boundary conditions are driving this? And can we understand the role of the ocean in modulating and getting this response? So let's look at the simplest case. Let's look at the simplest case being, let's just add a bump. Let's add a dark green bump that's not particularly bright. And let's do it in an AGCM only setting. So let's not worry about ocean coupling just yet. So this is the Green Mountain minus control in an AGCM setting. So there's no ocean to interact with, basically. And what you're seeing is, you get a very similar response. You get a southward shift to the jet and a general wetting in the southwest and a general drying of the northwest. And if this is all the information that you had, which a lot of the earlier studies only had these AGCM experiments, you might be pleased with it. I mean, you might say, okay, this is it. It's all due to topography, and the ocean doesn't really play a strong role. But now that we have the computational capabilities to look at ocean coupling, we should. And when you couple, I should mention that the reason why this is shifting in the Green Mountain is because of this direct mechanical forcing, because there's no albedo effect on the ice sheets here. But as I said, as soon as you couple an ocean to this boundary condition, oh my goodness, I'm sorry, I'm just missing the transitions on this, but we should look at this in 3D as well. This is the 3D zonal wind anomaly. So this is just at 500 millibars. This is the same thing. Zonal wind anomaly, zonally averaged over the North Pacific. And I'm just trying to show you how deep in the atmosphere this is going here. So the climatological values are black and the shading is the anomaly. And you can just see the southward shift of the jet pretty much at all levels. You can ignore the purple and green and sort of ignore the animation for now, because I just think we're going to run out of time to really explain it in more detail. But anyway, so now let's couple it to an ocean and let's see what it looks like. As soon as you include ocean-atmosphere interactions, the response is significantly different. You basically get the opposite result, where you don't really get a strong southward shift of the jet. You get just a general weakening of the westerlies. And if you look at it with height and sort of a latitude height cross section here, you can see that this is just a general weakening of the jet again, without any clear indication of a southward shift. And you definitely get the opposite hydroclimate response. So, something about ocean atmosphere interactions is really affecting the way that the climate system is responding to mechanical forcing from these ice sheets. And I don't have a ton of time to get into it, but it's primarily due to the SST response in the model. So in the LGM full case, in response to full LGM boundary conditions, you get something like a PDO-like pattern, to get a cooling throughout the Kuroshio extension. But in the Green Mountain case, you actually get a warming in the subpolar North Pacific and not much of a cooling in the Kuroshio extension region. And we do a mixed layer temperature budget to show you, in the paper at least, to see why we get this warming. And again, I don't really have time to get into it, but it has to do partly with, if you mechanically weaken the westerlies at the surface, you reduce evaporative cooling at the surface, which will give you a downward latent heat flux and warm the waters here. And this decreases the meridional temperature gradient. And by thermal wind, the atmosphere is going to adjust and the westerlies are going to weaken as a result. So that's the Green Mountain case. It's not really giving you gives you the right answer for the wrong reasons, but once you include something that's more realistic, you get the wrong answer. So what about the White Mountain case? Do we get something that's more similar to the LGM in a more realistic ocean setting? Well, The AGCM response is, again, very similar to the Green Mountain case. We get a southward shift of the jet, a general, north-south dipole and hydroclimate. But the fact that they're so similar, the fact that they're basically the same between Green Mountain and White Mountain says that in the White Mountain situation, albedo doesn't matter at all. It's just mechanical forcing that's driving this response in the AGCM case. So let's add the ocean components, both in a slab ocean and a dynamical ocean setting. You can see that they look much similar to the full LGM response. You get a southward shift of the jet, you get a much more appropriate hydroclimate response in this West Coast dipole. And so this is implying that ocean coupling is reinforcing this overall mechanical forced shift of the jet in the White Mountain case. So there's something about thermodynamic forcing that is exciting the ocean response, and those subsequent air-sea feedbacks are reinforcing the jet shift as opposed to clobbering it in the Green Mountain case. And then another sort of subtler point here is that the similarity between the slab ocean and the dynamical ocean suggests that ocean dynamics actually play a secondary role to air-sea feedbacks in driving the overall climate response, which is interesting. Again, we can look at this in 3D, and I just want to indicate that all three of these look the same, but this panel, the AGCM is again mostly mechanical, but in the slab and the ocean and the dynamical ocean setting, the thermodynamic effects are they're important, and it's the subsequent air-sea interactions that are really critical in shaping this overall climate system response. And again, I'm just sort of comparing between the White Mountain and the Green Mountain, and you can see the similarities in the AGCM and the differences when you couple an ocean. So why is this happening? Well, we can look at the SST again. This is the White Mountain SST response, and you'll see that it's very similar to the full LGM case. So why do we get cooling in the Kuroshio extension when you have thermodynamic forcing, and as opposed to warming when you don't? Something about thermodynamic forcing is leading to this cooling, and the primary reason for that is going to happen in the summertime when albedo forcing is going to be most important anyway. So we'll look at the summertime in a second, but it's probably important to note at this point that this SST pattern between our LGM run and our White Mountain run is robust across other model simulations. So this is a PMIP3 ensemble mean LGM minus control across several different PMIP3 models, showing you the ensemble mean SST response. And this is from Gray et al. But I just want to point out that this cooling of the Kuroshio extension is robust across different models. So again, why do we get cooling in the tropical or in the Kuroshio extension, especially when this is a coupled response, right? I mean, the atmosphere, by thermal wind, you would expect this to increase the meridional temperature gradient and strengthen the jet and get that southward shift that we're seeing in the White Mountain case. But it's a coupled response. The atmosphere is going to be in equilibrium with the ocean, and the ocean should be in equilibrium with the atmosphere. But that's not necessarily going to be true in the summertime. If you look at like summer stationary waves in each of these White Mountain simulations, you can see that the atmospheric response is very similar. And again, it's not super important that you understand everything that's going on here, but just that the patterns are basically the same. And what this is suggesting is that in the summertime, the large scale atmospheric circulation is uncoupled from the ocean. So if the ice sheets, the direct atmospheric response to the ice sheets are going to imprint themselves on the ocean, at any point in the year, it's going to be in the summertime when the ocean is not eliciting a really strong response in the atmosphere, when the ocean and the atmosphere are uncoupled.
Well, and you're 50 minutes, so if you just wrap up in the next couple of minutes. Sure,
thanks. And we don't in the paper we go into a detailed mixed layer temperature budget to tell you why we get this cooling, but I'll just highlight here the most important effect is a direct response in the North Pacific to the ice sheet, and that's the reduction in low clouds at the surface. So basically what I'm showing you here are the SST anomalies implied by changes in shortwave radiation in the dynamical ocean run. And you'll see that you'll get cooling associated with increased cloud cover in the dynamical ocean that is also seen in the AGCM. Low clouds are really highly coupled to SST. So the fact that it shows up in the AGCM as well, when you don't have that SST coupling, really shows you that this is a direct response to the ice sheets. And you can average low cloud fraction anomalies within this box, and you can see that this effect, the effect of increased cloud cover, is strongest in the summertime. And the differences between the AGCM and the dynamical ocean run are really highlighting the importance of low cloud feedbacks in amplifying this signal and getting it into the summertime, into the wintertime, where it couples back to the atmosphere and drives a really strong change in the hydroclimate. So yeah, as Isla mentioned, I'm low on time, so I'm going to skip this last part and just get to the summary schematic here. And I'm just going to give you a very 3-second overview of what I mentioned and sort of our interpretation of what the direct atmospheric response is to a tall, bright ice sheet, how that couples back onto the ocean, and how that gives you a southward shift of the jet in the wintertime and a shift in hydroclimate. So, in the summertime, you get insolation, which reflects off the ice sheet. This generates a cyclonic circulation over the North Pacific in the summertime. It ends up giving you cold air advection on the west side in the North Pacific and increased moisture transport over the east side of the North Pacific. This increases low clouds. It reflects sunlight. It cools the SSTs in the summertime. Low cloud SST feedback will persist this signal into the winter, where it will couple back to the atmosphere and drive a really robust southward shift in the jet stream and an overall shift in the hydroclimate. So happy to take any questions. I'm sorry I went a little over there. Thanks.
Thanks. So yeah, we have time for one quick question. Rob?
Nice talk, Dylan. Thanks. I was interested in the warming you showed in the Green Mountains case and your explanation for it, where you said this is due to the weakened westerlies and the wind evaporative feedbacks. But I would have thought that this is actually weakening enough that you're transitioning to easterlies in this case. So could you explain that a bit more? Are you still in the westerly regime in like the Gulf of Alaska?
That's a good question. If you look at the wind anomalies, I'll have to go back and check, but I don't think they're as strong as the westerly climatology from the control. But that is a good question, whether they actually turn into easterlies or not. But again, this is all relative to the control. So there is going to be a reduction in evaporation relative to modern day, even if the climatological wind during the LGM is now easterly. Is sort of my interpretation.
Thanks.
Mm-hmm.
Okay, thanks. So I guess if you have more questions for Dylan, please put them in the chat. And we'll move on to the next speaker. That's Hui Ding on the role of geostrophic currents and future changes in coastal upwelling of California.
Hello, good morning, everyone. Share screen. Okay. Yeah, sorry, one moment, please.
No problem.
What? Yeah. Okay. Why can't?
Are you having issues?
Yeah. Well. Why can't I?
Are you not able to share, or?
It's not working. I mean, the screen sharing is not working. Sorry.
Is it because you need to be a host, or is it something, do you think, on your end?
Oh, so.
Okay.
So.
Yeah.
Okay. Sorry.
That's okay. We can see it now, but it's not full screen yet.
Yeah.
But, okay.
So now it's the full screen.
Yep, looks good.
Yeah. Yeah. So good morning, everyone. My talk is about the role of geostrophic currents in future changes of coastal upwelling in the California current system. And I did this work with Michael Alexander and Michael J. Cox. So why are we interested in the coastal upwelling? Here is a schematic for the upwelling system near the California coast. And we can see coastal upwelling can bring nutrient-rich water from the bottom to the sunlit surface, which fuels phytoplankton and the high trophic levels like fish, seabirds, and so on. So coastal upwelling is a key factor for maintaining a productive marine ecosystem. In addition, coastal upwelling also brings cold water to the surface, which cools the sea surface temperature and regulate local air interaction and stratocumulus clouds. So yeah, given the importance of coastal upwelling, there is considerable interest in predicting the response of coastal upwelling to greenhouse gas warming. So far, many studies have already examined the coastal upwelling for the eastern boundary upwelling systems in a changing climate by looking at only the alongshore wind stress. Given ECMA transport is the dominant component of the coastal upwelling. For example, back in 1919 found the increasing trend in the upwelling favorable alongshore wind stress shown this figure, and panel A is for California, and the other panels are for other eastern boundary upwelling systems. And we can see increasing trend in all these systems. Barkin further argued the increasing trend is due to anthropogenic forcing. But Ekman theory is an incomplete picture of coastal upwelling dynamics, given we already know alongshore sea level gradient-induced geostrophic transport is also an important component of coastal upwelling, so it may not be sufficient to consider alongshore wind stress only. For example, in this figure, and this figure shows the monthly response to greenhouse gas forcing in vertical transport and upwelling favorable alongshore wind stress calculated from CESM1 large ensemble. And the x-axis shows calendar month, and the y-axis shows the actual latitudes of coastal grid cells. And it is obvious we can see the forced change in alongshore wind stress mismatch the forced change in vertical transport. The mismatch suggests changes in alongshore wind stress are insufficient to represent the overall changes in the vertical transport. So in this talk, we will diagnose the respective contributions of ECMA and geostrophic transport to change in coastal upwelling. Yeah, in this figure, Haiqi indicate 95% significance, by the way. So for this work, we use CESM1 large ensemble. There are 40 ensemble members, different only slightly in their initial atmospheric conditions in January 1920. And all the members are subject to identical historical forcing over the years 1920 to 2005, and then RCP 8.5 radiative forcing over the years 2006 to 2100. One benefit of using the large ensemble is because anthropogenic forced signals can be separated from internal climate variability. And in this work, we use a later epoch over the years 2071 to 2100 minus an earlier epoch over the years 1925 to 1954 to indicate greenhouse gas forcing forced changes. In addition, CESM1 is also a very good model in simulating climate in the coastal area near the California coast. This figure shows the alongshore wind stress in the northern part, central part, and southern part of the California coast, and the x-axis shows the calendar month. And we can see the model has a pretty good performance in simulating the monthly mean climatology of alongshore wind stress from observations. Oh, sorry. And this figure shows the monthly mean seasonal cycle for alongshore sea surface height, which is from the first offshore grid cells. Panel A is from ECMWF ocean reanalysis, and panel B is CESM large ensemble. And the y-axis shows the actual latitudes of coastal grid cells. And we can also see the model has a good performance in simulating the alongshore sea surface height. So this indicates the model also has good performance in simulating geostrophic transport. So we use vertical transport at 30-meter depth from the first offshore grid cell as a measure of coasting upwelling in the west coast of North America. And here we can see the latitudes of 30 north to 49 north. And Ekman and the geographic volume transport are calculated following J. Cox 2018. And zonal and meridional Ekman volume transport are given by these two equations. Here, tau x and tau y are wind stress. F is Coriolis parameter. Rho is sea water density. And zonal and meridional near surface geographic transport are given by the bottom two equations. And here we assume geostrophic currents are barotropic and uniform in the upper ocean. So the transport are a linear function of mixed layer depth d. And here d equals 30 meters. And eta is the sea surface height. And here is a schematic for a coasting grid cell. So to obtain the contributions of Ekman and geostrophic transport to coasting upwelling, so we calculate the horizontal transport in the northern, western, and southern side of each grid cell, but not for the eastern side. Here, where is coastline and the transport equals 0, then the net effect of horizontal transport must be balanced by vertical transport. So this, and we did this for Ekman and geostrophic transport respectively. So this can give us a contribution of Ekman and geostrophic transport to coasting upwelling separately. And so we, in this slide, we show the monthly mean climatology of vertical transport and its two components, Ekman and the geostrophic component. Panel A is for vertical transport. Panel B is for Ekman, for its Ekman component. And in each panel, the x-axis shows calendar month, and the y-axis shows the actual latitudes of coasting grid cells. Now we can see Ekman component has a substantial contribution to the total vertical transport, in panel A. But by looking at their difference in panel C, so which is panel A minus panel B, and we can see Ekman component overestimated total vertical transport in the southern part of the coast and underestimated the vertical transport for many grid cells in the northern part, and the difference between total vertical transport and the Ekman component closely resemble the geostrophic component in panel D. So the combination of geostrophic and the Ekman component can reproduce the monthly mean climatology of total vertical transport pretty well. So this indicates the contribution of geostrophic component. We also checked the contribution of geostrophic transport to coasting upwelling by examining momentum budget, looking at correlation and IMS error. And panel A shows a correlation between total vertical transport and the Ekman component. And we can see correlation is high only for some grid cells. For other grid cells, the correlation can be very low. For example, for this grid cell near 46 north, the correlation is even negative. And panel C shows the correlation between the total vertical transport and the combination of geostrophic and Ekman components. And we can see correlation is high almost everywhere, and for all months. And the right two panels shows the IMS error. And again, from panel D, we can see the combination of geostrophic and Ekman component shows much less IMS error than the Ekman component alone. So the combination of the two components can close the momentum budget much better than Ekman component itself. So it's also nice to show some time series. And the top left panel shows time series from a grid cell near 30 north in September. And top right panel shows time series from a grid cell near 38 north in May. In both cases, Ekman component overestimated the total vertical transport, and geographic component has a negative effect on coastal upwelling. So the combination of the two components match the time series of total vertical transport pretty well. And in the bottom panel, we show the time series from a grid cell near 47 north in June. In this case, Ekman component underestimated the total vertical transport, and geographic component has a positive effect on the coastal upwelling. And in this case, the combination of the two components also reproduce the total vertical transport pretty well. So all this shows the contribution from the geographic transport induced coastal upwelling. Now, in this figure, we show the forced response to greenhouse gas forcing by the epoch difference between these two epochs. And panel A is for vertical transport, and panel B is for Ekman component. And in each panel, the x-axis shows the calendar month, and the y-axis shows the actual latitudes of coastal grid cells. Shading is a response to greenhouse gas forcing, and hatching indicate 95% significance. And we can see it is insufficient for Ekman component to represent the overall change in the total vertical transport. There are many, and Ekman component miss many changes in the coastal upwelling. And panel C shows the forced changes or shows a response in geographic component to greenhouse gas forcing. And we can see the geographic component also shows significant changes for most of the grid cells and months. And by comparing panels A, B, and C, we can see the contributions from the geographic component to the forced changes in vertical transport at least can match or even exceed the contributions from Ekman component. And in panel D, it shows the combination of geographic and Ekman component. And and we can see the combination can also reproduce the long-term change in vertical transport for almost all grid cells and months. So now we come to summary. So changes in alongshore wind stress are insufficient to obtain overall change in the coastal upwelling near the California coast. Change in geographic transport make a substantial contribution to change in the coastal upwelling. In some part of the California coast, the contribution of geographic transport to long-term change in upwelling is equal or greater than the contribution from Ekman component. The combination of the two transport nearly close the momentum budget and thus reproduce the mean state interannual variability and the long-term changes. All results highlight the importance of accounting for ocean circulation when quantifying upwelling and its variability and change. Thank you.
Thank you. Do we have any questions for Hui? Okay, there's one in the chat. I don't know if you want to unmute or I can read it out.
Yeah, sure. Hi, nice presentation. I have a quick question on the time series where you show a different latitude, the contribution from this one. So in the last one, like 47 degree north, like both Ekman and geostrophic, like the underestimation that I can see, right?
Oh, yeah.
So I'm just curious how like combination of both can give us the total vertical transport.
Sorry, can you see the question again, please?
Yeah, so I just see that the Ekman and geostrophic here is underestimation, but the combination of the Ekman and geostrophic, the black line, how it, just curious how it is representing the vertical transport, the red line.
Yeah.
I'm just curious to see like an offset from the vertical transport.
Oh, the vertical transport is from the model output itself, so it's calculated from the full equations. It's not the So is this your question? Sorry,
no, it's yeah, I think I get it. Thank you.
Yeah, I think it would make sense that you wouldn't perfectly be able to reproduce the black line is because of the difference in the numerics as well.
Right.
Actually, here we consider only Ekman and the geostrophic components, right? But in the governing equations for vertical velocity, there are some other terms, even though they are pretty small, right? Like time derivative and the nonlinear transportation, and so on. So yeah, I guess it depends on the contribution from other terms. Yeah. So it can be difficult to perfectly match them sometimes. And here
Yeah, seems like a pretty good match overall. Okay, I guess if there are no more, well, if you have questions, you can add them in the chat, but we should probably move on to the final speaker of this morning's session, which is Zhan Wu, who's going to talk about the equatorial cold tongue bias in CSM1 and its influence on ENSO forecasts. So if you could stop sharing your screen, Hui. Hello, you still there, Hui? Okay. Thanks.
Can you see my screen okay?
Yep.
Hello, everyone. I'm Xian Wu and currently a postdoc at NCAR. I'd like to talk about the equatorial Pacific cold tongue bias in the CESM1 and its influence on the ENSO forecasts. The mean climate in the tropical Pacific Ocean exhibits the sea surface temperature contrast between the Western Pacific warm pool and Eastern Pacific cold tongue. And the cold tongue simulated by the current climate models, for example, the CESM1, is too strong and extends excessively to the west. This mean state bias in the climate models can influence the model simulations and forecasts of ENSO variability. In this talk, I will examine the mean state bias in a suite of 2-year forecasts conducted with CESM1 and also show the forecast errors of ENSO characteristics, not only the amplitude and the spatial pattern, which were noted in previous studies, but also the forecast errors of ENSO duration. We have 3 sets of forecasts initialized on March 1st, June 1st, and November 1st during every year since 1954 to 2015. The November initialized forecast is part of the CESM1 decadal prediction large ensemble, which consists of 40 ensemble members and 10-year integration for each initialization year. And we just make use of the first 2 years. The March and June initialized forecasts consist of 10 and 20 members respectively. For each initialization year, the ensemble forecasts are initialized from the same observed oceanic and sea ice states, but with slightly different atmospheric initial conditions to generate the ensemble spread. The oceanic and sea ice states is obtained from the ocean sea ice ocean model simulation sea ice model simulation forced with the observed atmospheric and surface flux fields. And these 2-year forecasts are conducted under the CIMIT 5 external forcing. We conducted those 2-year forecasts to investigate the predictability of ENSO event duration, especially the predictability of multi-year ENSO events in our recently accepted manuscript, but in this talk, I will focus on the biases in those forecasts. So first, I'd like to show you the seasonal cycle in the equatorial Pacific. Here is the longitude in x-axis and y-axis is calendar month for observation and forecast lead month for forecasts. The color shading is the climatological SST and thermocline depth in black contours, surface wind in vectors. In observation, the climatological SST cooling start to intensify in Boreas early summer and propagate eastward, along with the climatological southeasterly winds. This seasonal intensification of the cold tongue is captured in the 3 sets of forecasts, but the simulated cold tongue is too strong and shift too far to the west. In the difference map between the forecasts minus observation, we can see there is clearly SST cooling bias of up to 4 degrees and also westward displacement of climatological easterly winds. It is interesting that the initial development of SST cooling bias is preceded by the eastward propagation of negative thermocline depth anomalies in the dashed contours. And I will show in the next slide, this initial thermocline shoaling bias is rooted in the initial condition data. Another 2 interesting features I will discuss is the bias is larger in the first year after initialization than longer lead times. And also the bias is larger in March and June initialized forecasts than the November forecasts. Here is the seasonal cycle of equatorial Pacific SST and thermocline based on the initial condition data, the fuzzy simulation. Compared to observations, the fuzzy simulates shallower climatological thermocline depth, but warmer in the Western Central Pacific, but warmer climatological SST across the Pacific compared to observations. And when the model is initialized from the fuzzy state, it will give an initialization shock. So here I'm comparing the climatology of forecasts I have shown in previous slide and the climatology of CESM1 large ensemble. Here the CESM1 large ensemble is used to represent the intrinsic model climatology under the CIMIT 5 forcing for the same period of the forecasts. So in the difference map between forecasts and CESM1, it shows that in forecasts, the model is initialized from a state that is different from its own climatology. The difference is like El Nino-like warming, SST warming, and thermocline shoaling in the beginning. The imbalance between the model's climatology and the initial condition data will give the La Nina-like shock in the first year after initialization. That's why we have the stronger bias in the first year. Why is the cold tongue bias is also larger in the March and June forecasts than November? It is related to the seasonality of thermocline and SST coupling. Here I'm showing you the scatter plots of thermocline and SST in 4 different seasons denoted by different colors for observation and CESM1 large ensemble. In both observation and model, the regression coefficient between SST and thermocline is larger during JJA and SON. So it indicates the coupling between thermocline and SST is stronger in the summer and fall season. So in the March and June forecasts, the initial thermocline shoaling propagate eastward and arrive at the Eastern Pacific in boreal summer and fall. Those thermocline bias can more effectively cool the sea surface temperature than those arrive at the boreal spring in the November forecasts. So the seasonality of thermocline SST coupling gives the rise to the dependence of cold tongue bias on the initialization timing. After discussing the mean state bias in the forecasts, in the rest of the talk, I will discuss the forecast errors of ENSO events in the forecasts. Here, I'm decompose the all El Nino and La Nina events into 1 year and 2 year types to show the errors in the duration of ENSO events. This is the observed and predicted Nino 3.4 index composited for all 1 year and 2 year events during this period. The black curve is the observed evolution of ENSO events, and the colored curves are the 6 different ensemble forecasts initialized at 6 different lead times relative to December +1, and December 0 is when the El Nino and La Nina first peak. The first forecast error we observe is related to the ENSO amplitude and peak timing is weaker and earlier in forecasts than the observations. After the peak of 1 year El Nino, the model, all the forecasts have a warming bias in predicting the subsequent La Nina in the following year. And all the forecasts show a cooling bias in predicting the termination of 1 year La Nina. In contrast, some of the forecasts initialized in and after November 0, can predict the persistence of 2 year El Nino, and all the forecasts can capture the persistence of 2 year La Nina. So the model show bias in predicting the termination of ENSO events. And in the rest of the talk, I will focus on the 1 year El Nino as an example. Here I'm showing you the longitude time sections of SST anomalies in color shading, thermocline depth in black contours, and surface wind anomalies in the equatorial Pacific, composited for all 1 year El Nino events. In March and June forecasts, we can see there is a fast westward extension of the SST warming and westerly wind anomalies during summer and fall season when the mean state bias is strongest in the forecasts. In the difference map between forecasts and observation, due to the westward shift of ENSO anomalies, the SST warming over the eastern central Pacific is weaker in the forecasts than observations. And also the thermocline tilt associated with El Nino development is weaker in the forecasts than the observations. This is induced by both the errors of surface wind anomalies and also the errors in the initial thermocline depth. The initial condition data simulates shallower, like weaker thermocline deepening before the El Nino development. So it provides a weaker initial recharge state. Also, in the second year, those westward shifted winds persisting to the second year, and due to the weak amplitude of El Nino and the persistent wind, the thermocline shoaling happening around the mature phase of El Nino is weaker in the forecasts than the observations. So El Nino persists for a second year. Those bias in predicting ENSO characteristics are improved in the November initialized forecasts, although especially it predicts the termination of El Nino, although there is still a warming bias. Why is the wind persist into the second year? First is related to the forecast errors of tropical interbasin teleconnections. In observation, in response to the El Nino development, the Indian Ocean and Atlantic Ocean warms up. And this warming of the other two oceans act to weaken the wind anomalies over Western Pacific around the mature phase and help terminate El Nino. But in the June forecasts, the westerly wind anomalies shift too far to the west. So the wind variability over Western Pacific is more controlled by the Pacific condition rather than the negative feedbacks from the other two oceans. And also in the difference map, we can see the warming up of the other two oceans is weaker in the forecasts than the observation. The weaker interbasin adjustment is not sufficient to terminate the El Nino. The other errors that contribute to the persistent wind is through the errors of North Pacific teleconnection in boreal winter. Here I'm showing the spatial patterns of SST precipitation surface wind anomalies in DJF around the peak of 1 year El Nino. In observation, the Aleutian low circulation deepens in response to the tropical SST warming and increased precipitation. But in the June forecasts, the westward extension of the precipitation and SST forcing induces a southward shift of this Aleutian low response. In the difference map, we can see the biased southwesterly wind anomalies induce the subtropical SST warming, which is similar to the North Pacific meridional mode. And this mode is known to affect the wind variability over Western Pacific and trigger El Nino in the following seasons. In the November forecasts, the tropical SST forcing is more realistic. So the bias in the Aleutian low response is reduced. So does the SST warming over the tropical Pacific Ocean. This would induce a weakened bias over of the wind over Western Pacific. In summary, we investigated the potential causes of cold tongue bias in the CESM1 forecasts related to the mean state bias, especially the spatial pattern of cold tongue. We also identified the ENSO forecast errors in spatial pattern amplitude and its duration. I will stop here and take any questions.
Thank you. Okay, do we have any questions for Jean? Please either raise your hand or put them in the chat. I guess I was wondering about the extratropical bias that you showed. I think the CSM2 is a bit improved in kind of the canonical extratropical response to ENSO. Do you think that, or have you looked at CSM2 at all? Maybe we don't have the runs yet, but do you think this is going to be better?
If the tropical Pacific SST forcing is improved, it should be better according to the comparison between June and November forecast here.
Okay. Yeah, I guess I don't know if the SSTs have improved, but I think the extratropical circulation anomalies have improved. But yeah, that will be interesting to see. Sarah has a question.
Yeah, thanks for the talk. It was nice to see biases connected to the physical processes. So I did have one question. So in real-time ENSO predictions, the NINO 3-4 predictions are, bias corrected one way by removing the lead time dependent climatology, and then the other by correcting for the amplitude issues that you're talking about. So multiplying by the ratio of the standard deviation of observations divided by that of the model. So I guess the question that I have is, what do you think those methods are missing, right? Because you've kind of described some more complicated processes that are going on. Are the typical bias correcting methods that we use correcting for a lot of what you're seeing? And maybe this is too much of a loaded question, but I was just curious about your thoughts.
Thanks for your question. For our ENSO predictions, we also have the biased climatology removed as a function of the lead times. Even though we remove the biased climatology, we still have biased pattern associated with the mean climate and also biased feedbacks. So I think the model bias could still influence the ENSO forecasts. And for
I think I see what you're saying.
I think there was a related question in the chat that you probably just answered. The question was whether you compute a lead dependent bias, subtract a lead dependent climatology to make the anomaly. So I think the answer is yes, right, from what you just said.
Yes.
Yeah.
But it would indicate whether this process was linear or not.
I think the amplitude bias of the mean state can be removed by such a bias correction, but the spatial patterns, influence of spatial pattern of Cotang bias cannot be removed because it determines where the convection happens in the interannual timescale, on interannual timescales. Hope I answered your question.
Well, we're getting into the coffee break, so you can always continue this chat offline. So we have a 20-minute break now, I believe. Let me just check. Yeah, until 10:40. When we'll have some more talks that are focused on kind of Atlantic and Pacific multi-decadal variability and change. So thanks to all the speakers from this first session, and we'll see you in 18 minutes.
Thanks, Isla. I'll put up the sort of placeholder slide.
Okay, sounds good.
I stopped sharing so Jerry can get ready.
Okay, well.
Good. So Aishu, are you gonna chair this session?
Yes.
Okay, great.
I'll make you a co-host then, so you can raise and lower hands if you need to.
Okay, thanks. Now it's 10:40, and welcome everyone. Come back to the second session of CVC-WG Winter Working Group meeting. In this session, we will have 4 talks, and each speaker has 20 minutes, and we should say the speaker will talk about 15 minutes and give 5 minutes for question and answer. The first speaker is Jerry Mill. He will talk about Atlantic and Pacific tropics connected by mutually interactive decadal timescale processes.
Okay, thanks, Aishu. Yeah, thanks. So I want to acknowledge my co-authors on this work, Aishu, Fred, Susan, Gokhan, and Nan are all at NCAR. Matt England's at University of New South Wales in Sydney. Shane McGregor and Julie Arbelast are at Monash University in Australia, and Shang Ping is at Scripps. And if you want to see more details in this paper, you can look at this. There's the reference there. It appeared a couple months ago in Nature Geoscience. So the whole idea behind decadal climate prediction is that you have to hope that there are some processes and mechanisms that if you initialize them in the initial states of the model predictions, you can get more predictive skill than you'd expect from persistence. And maybe if you capture the time evolution of these slowly varying processes correctly, you may get more skill beyond 1 or 2 years in the future. And when you look in the literature, the usual suspects originate from the Pacific and the Atlantic, generically called Pacific Decadal Variability, or PDV, which includes the IPO and the PDO, and Atlantic Multi-Decadal Variability, or AMV, which includes the AMO. And these, of course, involve slow fluctuations of tropical Pacific and Atlantic sea surface temperatures, among other things. And when we're talking about the positive phase of PDV, you're talking about kind of anomalously warm tropical Pacific sea surface temperatures. And if you're talking about the positive phase of the AMV, you're talking about warmer Atlantic SSTs north of the equator. And if you look at the literature, there's a whole bunch of papers that say that the Atlantic is driving the Pacific, and then there's a whole bunch of other papers that say the Pacific is driving the Atlantic. And if one of these two possibilities were true, that would simplify our decadal prediction problem, because then you could just focus on one basin. For example, if you thought the Atlantic was driving the Pacific, then if you just got things right in the Atlantic, then that would drive the Pacific, and the Pacific would fall into place. And if the tropics are heavily involved in this, and you get nice teleconnections coming out of the tropical convective heating anomalies, and you'd be able to get skill over a large area of the globe. But of course, it's hard to figure out if one is driving the other. This is true for the observations and in models. So what we're going to do is use so-called pacemaker model configurations, where we're going to have observed patterns of sea surface temperatures for AMV and PDV, and then the rest of the model is fully coupled, and you see how each basin reacts to the other in that way. And this is just kind of a summary of these experiments. We're using the CESM large ensemble version at 1 degree. We have 2 types of pacemaker experiments. We have so-called idealized pacemakers and time series pacemakers. The idealized pacemakers, you basically separate out the internally generated component of variability. So you get a PDV pattern for the Pacific and an AMV pattern for the Atlantic. And you put those patterns into the model, and you run for 10 years for 30 member ensembles. And of course, everywhere else, the model is fully coupled, and you are basically just gauging the model response to these idealized decadal patterns of PDV and AMV. And we're running an AMV plus and AMV minus set and a PDV plus and a PDV minus set. The time series pacemakers go back to the Kosaka and Shi methodology in 2013, where you just nudge SSTs toward observed values, in this case over the equatorial or tropical Eastern Pacific, and then in the Atlantic from equator to 60 north. And these are just running as a time series from 1920 to 2013 with the observed values in those areas, and the rest of the model is fully coupled. So first, results from the idealized pacemakers, and this is the PDV plus minus PDV minus is the top two panels here for sea surface temperatures and precip. And you can see wind vectors, anomalous wind vectors in here on the upper left. So the sign of these differences is for PDV plus, and the green lines here demarcate the area of the Pacific where we've specified this pattern. So this pattern you see here in SST anomalies is what we're specifying, and everything else is responding to that. And so what you can see is that when you're in this PDV plus phase, you're getting positive SST anomalies in the tropical Atlantic. So you get the same sign response of tropical sea surface temperatures when you're driving the system from the Pacific. You also get this interesting teleconnection pattern, and you can see these the low, high, and low patterns here, the PNA and PSA, and these are, you can see the wind vectors here kind of demarcating these. You can see these better in sea level pressure, but I'm showing here just for the winds. And of course, this is associated with when you get these positive SST anomalies, you get positive precipitation anomalies. That's these red colors over here in the upper right. You're also getting positive precipitation over here in the tropical Atlantic, over this warmer water in the tropical Atlantic. And these positive convective heat anomalies in the tropical Pacific are driving the PNA and PSA patterns. And what that ends up doing is when you have an anomalous low that kind of creeps into the subtropical North and South Atlantic, that weakens the trade winds near about 15 north and 15 south. And that's going to be an important factor as we go into this. For the AMV plus minus AMV minus, now we're driving the system from this area here between the two green lines in the Atlantic. So when this is in a positive phase, the SSTs are positive, but now you're getting this opposite sign response in the tropical Pacific. And this is looking more like kind of an IPO type pattern. And then the convective heating anomalies are associated with precipitation anomalies, and you're getting, of course, big positive precipitation anomalies over here in the tropical Atlantic, negative precipitation anomalies in the Pacific. These negative precipitation anomalies are driving kind of a weak kind of teleconnection pattern, but it's not really making it back over here to the Atlantic. So this is just the Pacific responding to the Atlantic. So you have a fundamental difference in the way these basins are responding to each other. If the Pacific is driving things, the Atlantic has the same, tropical Atlantic has the same sign SST response. If the Atlantic is driving things, the Pacific has tropical Pacific has an opposite sign sea surface temperature response. And so what's producing this, the typical thing that's looked at, and we looked at it as well, is the anomalous Walker circulation. These are vertical cross sections of vertical motion, average from 5 north to 5 south. The Pacific is roughly in this area here. The Atlantic is in this area here. The blue shading, and this is going up through the depth of the troposphere here, the blue shading is anomalous upward vertical motion. Red is anomalous descent. And so for positive PDV, we have the big positive precipitation anomalies that are driving this really strong vertical motion here. And it spreads out when it gets to the tropopause, and you get descent coming down in the Atlantic, and you're getting kind of weak easterlies here on the surface in the Atlantic. For the PDV or AMV plus minus AMV minus, now we're getting these strong positive vertical motion anomalies over here over the Atlantic sector, and they're getting this anomalous descent coming down here in the Pacific, and pretty strong. You can even see here the vectors, you can see strong easterlies here in the equatorial Eastern Pacific. And so what is that doing? Well, we did an energy budget here, which I'm not going to go through the details of. I'm going to summarize it here. We look basically at the first 5 seasons of these 10-year simulations to see how these things evolve. But when the Atlantic responds to the Pacific, you're getting 2 things that are important. First of all, you're getting this positive net surface heat flux. I mentioned the fact that this teleconnection pattern, the PNA and PSA patterns, weaken the trades in the tropical Atlantic, and that produces weakened latent heat fluxes, and that contributes to positive downward net surface heat fluxes. So that's one of the things that causes that same sign response between the tropical Atlantic and the tropical Pacific. And also you get this ocean heat convergence, and that also warms the surface layers. You're getting weak southeasterlies as an association with the anomalous Walker circulation, and that's giving ocean heat convergence. So you're getting two things, net surface heat flux and ocean heat convergence are both contributing to that same sign response. The Pacific response, the Atlantic pacemaker, is almost all through the Walker circulation, Walker circulation. You're getting this really strong easterly anomaly surface winds, and that's contributing to basically horizontal heat divergence coming out of the surface layer, and that cools the surface layer. So it's kind of two different sets of processes are involved with these reactions to each basin kind of forcing the other. Those results were from these kind of interesting idealized pacemaker simulations. The question is, can you see anything like this in a long pre-industrial control run or in observations? So we looked at the 1800-year large ensemble pre-industrial control run, and we basically regressed a PDV index and with various lags, and I'm illustrating here where the PDV is leading by 3 years, and we're seeing this same sign response. So when the PDV is leading, you're getting basically a warm tropical Pacific and a warm tropical Atlantic, so the same sign response. When the AMV is leading by 3 years, you're getting this warm tropical Atlantic and an opposite sign response in the tropical Pacific. So at least for these sets of processes in an unforced control run, we're seeing something similar to what we saw in the idealized pacemaker experiments. If you go to the observations, it gets more complicated, of course, because we have external forcings that are coming into play. But you're seeing elements of what we're seeing in the model simulations and the pacemakers. If the PDV is leading by 3 years, you're seeing kind of a weak same sign response in the tropical Atlantic. If the EMV is leading by 3 years, you're seeing an opposite sign response in the tropical Pacific. So these results at least suggest that this may actually be going on, that you get this different kind of response depending on which basin is forcing the other. So how could this be happening? This is just a very idealized schematic of illustrating an AMV index, this red line, which is going from positive to negative, and a PDV index, which is going from positive to negative. And of course, these are not oscillatory. This is just to illustrate this kind of concept that if the AMV is in its positive phase, the results we've seen so far would indicate that it's going to try to drive an opposite sign response in the PDV. It's going to lead an opposite sign response in the PDV by a year or 2 or 3. But once the PDV gets negative, it's going to try to drive a same sign response in the Atlantic, and that's going to try to make the Atlantic AMV negative. So you get a same sign response with the PDV leading. Now the AMV is negative, it's going to try to drive the PDV back to an opposite sign response to make it positive with another lag of a few years. And then the PDV is positive, and it's going to drive the Atlantic into a same sign response. So it can kind of, these interactions could go back and forth with one affecting the other kind of sequentially. And this is, of course, an idealized view. If you look at a more realistic portrayal, this is an index of the PDV and AMV. PDV from a UF index, UF calculation for Pacific SSTs. This is AMV is kind of a version of the Trenberth and Shea detrended kind of index. And you can see that even by eye, these things are going back and forth. And just to illustrate a couple of these, and I'm going to show an example of this here. PDV is positive here, AMV is going from negative to positive. And when the PDV was negative, it's trying to make the Atlantic go negative. And so it looks like this is how we're getting these lagged regressions coming out to look like what we saw in the pacemakers and in the long control run, because something like this does seem to be happening in the real system. So just to kind of summarize kind of how this is working, if the tropical Atlantic is driving things, you get this strong anomalous Walker circulation with anomalous descent over here, strong trade winds, horizontal heat divergence out of the surface layer, and that cools things off. So you get this opposite sign response. If the tropical Pacific is driving things, you get the weakened trade winds, this anomalous descent over here in the Atlantic, and weaker southeasterlies. You get these teleconnection patterns coming out of the PNA and the PSA, which gives you these anomalous lows in the North and South Atlantic, weaker trades, and then you get a surface heat flux contribution to this, along with the ocean heat convergence, which warms the surface layer, and you get the same sign response. Okay, can we see anything like this in these time series pacemakers? I'm going to show one example of a time series pacemaker here, because we looked at various periods. This is the 1975 to 2000 period, and this is where the PDV is positive, and the AMV is trending positive, negative to positive. And so this is the observations from 1975 to 2000. You see the same sign response, which would suggest maybe that the Pacific is driving the Atlantic during this time period. This is the trend over that time period from the large ensembles. This is kind of what the external forcing is trying to do, the sum of all the external forcings. If we look at a Pacific pacemaker experiment for this time period, this is the trends. You see the same sign response in the Tropopacific and Tropical Atlantic. If you remove the external forcing from the lens, you're still getting a same sign response. So the external forcing doesn't seem to be a big factor in this particular time period for the Pacific. If you're looking at the Atlantic time series pacemaker for this time period, as you'd expect, you're seeing this opposite sign response when the Atlantic is SSTs are being specified. But of course, that isn't what happened in the observations. We had a same sign response. If you remove the external forcing, you still get this opposite sign response. If you keep the aerosols fixed, you still get the same kinds of patterns. So this would indicate that for this time period, and this is how you can use these time series pacemakers, that it's probably the Pacific was driving the Atlantic and not the Atlantic driving the Pacific for this time period. But then you can look at other time periods where the Atlantic is also driving the Pacific to give an opposite sign response in the observations. So we use these pacemaker model configurations to try to disentangle these cross-basin interactions. The pacemaker results show that when the AMV SSTs are specified in the Atlantic, there's an opposite sign response in the Tropical Pacific, and when the PDV SSTs are specified in the Pacific, there's a same sign response in the Tropical Atlantic. There's kind of different processes at play to give these different kinds of responses. The net surface heat flux and ocean dynamics in the Atlantic are both contributing. In the Pacific, it's mainly just the ocean dynamics in response to the anomalous Walker circulation. And we're proposing this kind of new paradigm for decadal timescale variability that processes in the Atlantic and the Pacific are mutually and sequentially interactive, mainly through the atmospheric Walker circulation, but also with contributions from mid-latitude teleconnections from the Atlantic response to the Pacific. So this is kind of a new way of looking at these kinds of interactions, that there's not one driving the other, it's both they both drive each other sequentially and they're mutually interactive. And then this, for the implication for decadal climate variability, is we don't get a free lunch out of this. We have to actually simulate the processes and mechanisms in both basins and their interactions to produce credible decadal climate predictions. Thanks.
Thank you, Jerry. So questions, and I see Clara, you raise your hand.
Hi, thanks. Thanks, Jerry. I had a question. So you were emphasizing that the Atlantic, it's the tropical Atlantic that responds to the Pacific.
Right.
And, you know, AMV is, I think, a little bit of an amorphous thing. And, you know, the role of AMOC in AMV seems to be mainly in the subpolar North Atlantic. So are you really talking about AMV response to the Pacific, or are you talking about tropical Atlantic response, and that's not, you know, the associated with AMOC?
Well, yeah, and this is kind of an outstanding question as to what's producing AMV in the first place. And AMOC is a candidate, and like you say, the subpolar gyre seems to have the biggest connection, but the tropical Atlantic is somehow connected to, when you look at the AMO kinds of indices and things, you see the tropical Atlantic is also playing a role. As we saw here, though, it's interesting that when you do these idealized pacemakers, and even when you do the lagged regressions and the control runs, it's mainly the tropical Atlantic that's responding to the Pacific with the same sign. So it's that part of it that's connected through the Walker circulation that seems to have the strongest response to the Pacific. The Atlantic, of course, when you specify those SST anomalies, the biggest convective heating anomalies are in the tropical Atlantic, and that's driving that really strong anomalous Walker circulation to the Pacific. So I think it's still an open question as to, definitely I'm looking at the tropical Atlantic and tropical Pacific here, because that's where the results are the strongest. But connections to the subpolar North Atlantic and how that connects to the AMOC, I think is still an open question, at least for these results.
Thanks.
Ella?
Yeah, I was just wondering if you quantified kind of how much variance in the modes is explained by the lag relationship with the other one. Is it kind of a small part of the overall variance, or it's kind of
smaller? Like when you, and I didn't point that out in those idealized pacemakers, when the Pacific is driving the Atlantic, you're getting a much smaller amplitude signal by about a factor of 2 in the tropical Atlantic as opposed to what the observed AMV variability is. So it's a contributing factor, I'd say, but I think the idea that these are both interacting with each other, that they have this kind of mutual interaction, I think that that seemed to be something that kind of came out with the pacemakers and the lag regressions.
Yeah. Thanks.
Tony, you're the last one.
Yeah. Hi, Jerry. Very nice talk. I was curious if you looked at the ENSO variability between the AMV positive and negative, in particular, one favoring Central Pacific ENSOs versus East Pacific ENSOs. Did you look at that?
No, we didn't. That's an interesting idea, though, because that would be something we could look at. It'd be, yeah, I think you could do it in the idealized pacemakers for sure. And the time series pacemakers, we could also look at that too. Yeah, so that would be an interesting thing to look at.
Yeah, because I think in the 80s and 90s, we were dominated by the East Pacific, and now in the 2000s, we see the Central Pacific, and I do think it's the stronger Walker circulation that gives rise to that. So your results maybe could highlight that as well.
Yeah, that's a good idea. We'll have to check that out.
Thanks, Jerry.
Yep.
Thank you, Jerry. Next speaker is Claire Desser. Her talk is toward an index of Atlantic multi-decadal variability that is robust to climate change. Claire.
Thanks a lot. Let's see, can you see my screen?
Yes.
Yep.
Great. Okay, great. Okay, so thanks a lot for the conveners here, and very nice to follow Jerry's talk on a related topic. So I'm not talking about mechanisms in this particular presentation, but just something that caught our attention and made me really want to look into, you know, how best to define, based on a simple SST index, the internally generated component of Atlantic multi-decadal variability that is robust to climate change, so future climate change. And you'll see what I mean by this in a moment. But I am emphasizing that I'm not looking at, you know, the very interesting possibility that AMV also has a forced component due to aerosols and greenhouse gases. So I'm only looking at the internal component. So typical definitions of IAMV, so I standing for internal, and these are empirical definitions, you know, from the observations, sort of, you know, the best we can do. So typically one takes, the precedent is to take a low pass filtered North Atlantic SST anomaly time series. And that is a convenient measure of IAMV. And this was done, I think, maybe early on by Enfield. Maybe there's even earlier papers than that. But of course, what arises is how do we deal with background climate change? So the simplest thing and straightforward thing to do that Enfield et al. In 2001 did was to simply linearly detrend the index as a way of removing some kind of, you know, forced component. So that was shown to not be optimal because, of course, global warming is not linear, and it's, you know, maybe not quite a fair thing to do. So the next simplest thing that one can do, and I'm really emphasizing simplicity here. There are, you know, much more complicated methods, but for the simple methods, Trenberth and Shea in 2006 introduced just a simple variant, which is let's subtract the global mean SST time series from the index as a way of accounting for any nonlinear trends, if you will, or pacing of global warming. So that's been a very well-used index in the literature. And I want to just show you some problems that come up as we look at future climate change, obviously in models. So the question for this talk is, how well does the Trenberth and Shea method work under future climate change? I don't think it's been explored enough. And the way we're going to address this is to use our lovely perfect model test beds, i.e. initial condition large ensembles. So these large ensembles, because we run lots and lots of simulations with the same model under the identical forcing, external forcing, but just changes, slight changes in the initial conditions. If you have enough ensemble members, then when you average them, you can reduce the noise of the internal variability and get the forced response. And then you can subtract that forced response from each individual simulation, and then thereby isolating the internal component. So that's what I mean by perfect model test bed. Okay, so we've looked at lots of models. I'll show you a result at the very end that synthesizes across models. But for now, I'm going to begin with just illustrating our method here using the MPI so-called grand ensemble. They had 100 members. So it's convenient to have lots of members and to look at how many members you need, et cetera, for robust results. So I'm using the MPI Grand Ensemble, and what you're going to be seeing are SST regression maps. And these maps are all regressions onto this AMV index, this North Atlantic area averaged SSTs. And I'm using 20-year running means for everything. Previous literature has sort of done 10-year running means, but recent work of Delworth and Isla and others really emphasize that when we use a more heavy low-pass filter, i.e. 20-year running means, you really isolate the AMOC-driven component of AMV, i.e. of subpolar North Atlantic SSTs. That said, my results really are not very sensitive to whether I use 10 or 20-year running means, but I'm going to show you 20-year running means. Okay, so here's the first map. So this is AMV internal, or an estimate of the internal component of AMV, at least its spatial pattern, in the MPI Grand Ensemble. So here I'm looking at the historical period 1950 to 2020. And what I'm doing is, you see the box in the North Atlantic. That is just, I'm area averaging the SSTs in that box. And then I use the Trenberth and Shea method. So I remove the global mean SST from that index. And I also remove the global mean SST from the SSTs at each grid box. And then I perform my regression, and I do this for each ensemble member. And here I'm using the first 40 ensemble members. And then I average those 40 regression maps for a robust estimate of the spatial pattern that goes along with the internal component of AMV in this model. So that's what that is. The units, there are no units because I'm regressing SST onto the Atlantic SST index. So it's a unitless color bar there. Okay, so first, does this pattern have any resemblance to reality? So I'll just show you again, in the observations, we estimate AMV internal with the Trenberth and Shea method. This is the map using the ERSST v5. It doesn't matter very much what data set we use. So actually the pattern correlation is not bad. It's 0.69. You can see there's much more amplitude in the observations compared to the model. But overall, as quantified by that pattern correlation, the pattern is actually quite good. Okay, so now we'll set aside the observations and go into our perfect model world to test the Trenberth and Shea method further. So the upper left map is the truth in the model of what the internal AMV pattern looks like. And by truth, I mean what I said earlier, if you subtract the ensemble mean from each ensemble member, so at each grid box and each time step, subtract the forced component of SST that you obtain by the ensemble mean, and then you do these regressions onto the North Atlantic SST index. And so that is the truth according to the model, you know, and we have enough ensemble members to you know, be able to do this. And you can see there's a really nice match. The pattern correlation is 0.93 between the true internal AMV and that estimated from the Trenberth and Shea method in this model. Okay, so the Trenberth and Shea method works very well for this historical time period, so no worries. All right, so now we're going to move on to the future, and that's really what got us going here in this project. So now I'm looking now from 1950 all the way out to 2100, and I'm just going to do this same comparison between Trenberth and Shea estimate and the true internal AMV estimate. So here's the truth, again, by subtracting the forced component before doing any of these regressions onto the North Atlantic SST index. And the truth, so it looks actually really similar to what we got for the historical period. It has a bit more amplitude in the remote regions from the North Atlantic, particularly the Pacific. So that's an interesting, perhaps forced response to the amplitude of AMV, but we don't need to go there for this particular talk. So that's the truth. How well can we estimate it using our Trenberth and Shea method that we found worked very well for the historical period? And this is, of course, what prompted this whole investigation. It fails miserably. So the Trenberth and Shea method gives you a pattern that looks nothing like the true pattern. And that pattern correlation is only 0.18. You can see there's just the structure is just really, really off. So why is that happening? It's happening because the forced trend has a very strong spatial expression. So this map on the bottom here is just the ensemble mean SST trend over this 1950 to 2100 period. I've removed the global mean SST so you can just look at the pattern. And you can see that there's this really strong anti-correlation, minus 0.92, between the Trenberth and Shea estimate and the forced trend. So basically, by subtracting the global mean SST time series from each grid box, you have not accounted for the fact that there is a very strong spatial pattern to the forced trend. So you're basically aliasing that pattern. You're aliasing the forced trend pattern onto this Trenberth and Shea based AMV. So that's really why it fails. I should say for this historical period, 1950 to 2020, this is the forced trend map. Again, minus the spatial mean, and it's much more muted. So maybe there is a little bit of an issue for this, even for the historical period, but it's much less of an issue for the historical period. Okay, so is there a better approach? What can we do? Luckily, I think that there is, and it's not me who has come up with it. I've just applied it. Other people have done this for a long time. And instead of removing just the global mean SST time series from each grid box, remove the pattern of SSTs that are associated with the global mean. And this was done by Aigo Dai early on, not for AMV, but for other purposes. But Rong Zhang, in her review paper of AMV, employs it, and a recent paper, Chin et al. Also. But they didn't look at the future, so that's my angle here. Okay, so what we do is, and that is referred to in their papers as the residual method. So taking away the forced pattern of SST that's associated with the global mean time series. And that's the new thing here. So here is our estimate of AMV internal using this residual method, i.e. regressing out the pattern of SST associated with the global mean SST. And for this future time period, it works extremely well. It looks a lot like the true AMV with a pattern correlation of 0.83. So it does seem extremely promising. Yeah. So the final question I want to turn to is, of course, when does this Trenberth and Shea method start to fail? And does this residual method work well throughout the 21st century? So I'll show you now, I'll come back to the MPI Grand Ensemble, of course, as my test bed. And now I'll just show you, instead of maps, I'm just going to show you these cumulative pattern correlations since 1950. So I just take the data from 1950 to 2020, and then I do 1950 to 2021, 1950 to 2022, and I keep adding years to the end of the record all the way to 2100. And then I perform these analyses, and then I summarize things with pattern correlations. So here is the figure that I want to show you. So these are these cumulative pattern correlations. The y-axis runs from +1 to -1, and the x-axis starts in 2020. So that's a pattern correlation for the time period 1950 to 2020. So it's the end year that's plotted. And then I go all the way out to 2090 in this particular plot. So the blue curve is the pattern correlation for each one of these time periods between the estimated Trenberth and Shea estimate of the IAMV pattern versus the truth. And it works very well, as we saw at the beginning, and then it plunges down to near zero values in the future. And the 1/e folding time is roughly 2044. So maybe that's a benchmark for when we can expect that method to start to fail. The red lines here, I've estimated with the residual method. I've just done it every 10 years. That's why I don't have a continuous line. It's kind of labor intensive. So that's a pattern correlation between this residual method and the truth. And it's always above 0.85. So it works very well throughout this period. And then I bring in two more curves here. The cyan colored curve is the pattern correlation between the Trenberth and Shea estimate of the IAMV versus the pattern of the forced trend, which we think is the culprit here. And you can see that that forced trend resemblance or anti-correlation really becomes very strong at the time when the Trenberth and Shea method fails. And then just for completeness, this green curve is the pattern correlation between the true IAMV pattern and the forced trend, and it's negligible throughout this period. Other models give overall similar results. There is some difference in the timing of when the Trenberth and Shea method starts to fail. This is my last slide here. Sorry, the pictures are not so pretty. I kind of ran out of time yesterday. But I'm just showing you these same two pattern correlations, cumulative, as I showed you before. Now the cyan colored curve is that residual method versus the truth, and the blue curve is the Trenberth and Shea method versus the truth. I'm using 30-member ensembles. That's sort of the smallest ensemble size for this collection of models. So MPI, this is the first collection of 30 members, and this is the second collection. You can see it doesn't, 30 members is plenty. Here's CESM1, very similar results, although the residual method doesn't perform quite as well at the end. I don't quite know why. And then here's the GFDL, CAN-ESM, and CSIRO, and they're all a little bit different. And I especially point to CAN-ESM, where the Trenberth and Shea method fails no matter what time period you look at. So summary, defining internally generated AMV in a changing climate, subtracting the global mean SST time series, i.e. the Trenberth and Shea method, works well, generally speaking, under current and near-term climate change in most of the models we've examined, but fails thereafter due to aliasing of the global warming pattern. And removing the global warming pattern by a spatial regression onto the global mean SST time series yields robust results, pattern correlations generally in excess of 0.8 throughout the 21st century. Thanks very much.
Okay, we have time for one quick question.
So I should have my hand up. I don't know if you see it.
Oh, no, I didn't. Okay, go ahead, Jir.
So Claire, I presume that this trend pattern in the forced response is aerosols mainly. It has this hemispheric character to it. And then that kind of, and you said you weren't going to go there into the aerosol forcing of AMV. I was wondering if that also, the time evolution of that forced pattern could actually also cause another complication for an AMV index.
So thanks for your question. I'm not sure that I think that forced trend pattern is dominated by greenhouse gases, at least all the way to 2100. Remember, I've taken away the spatial mean. So if I had added that back in, it would be warming almost everywhere except the warming hole in the North Atlantic and maybe a little bit, a lot less warming in the Southern Ocean. But I think that pattern is dominated by the greenhouse gases. That said, however, I agree with you completely that this residual method, one shortcoming of it is if the forced pattern, has different contributions at different times. So aerosols, maybe if we look at the, 1940 to 2000 or something, and then dominated by greenhouse gases thereafter. If you're only regressing on that single global mean SST time series, you're never going to be able to accommodate changes in the pattern of the forced response. So it's a little tricky, but I think what I showed, that was a greenhouse gas pattern, really.
Even with that northern hemisphere, southern hemisphere contrast?
Well, you get that I'll double check. We have the greenhouse gas only ensemble, but I think you do get that. I think that is mainly a greenhouse gas, but thanks. I'll take a look at that.
Yeah, thanks, Clara. Nice talk.
Thanks.
Thanks, Claire. There's another question in the chat. Please answer it, Claire, from Christine. And we move on to the next talk. Next talk will be Haruki Hirasawa. His talk will be opposing the complementary effect of aerosol forced Atlantic and Pacific SAT anomalies in 20th century Sahara precipitation. Yeah, Haruki. Are you still muted?
Hi, can you hear me?
Yes, I can hear you now.
Okay, sorry, my mic hasn't been cooperating today. Right, so, okay, so yeah, thank you. So yeah, my name is Haruki, and my talk is, I guess, more on the externally forced multi-decadal signal. In particular, we're looking at aerosol forcing and how it influences Sahel precipitation in the late 20th century. And in particular, looking at how different regional components of the response influence the Sahel. And so this is work I've been doing at the University of Toronto with my supervisor, Paul Kushner, as well as Michael Sigmund and John Fife at the CCCMA in Victoria, Canada, and Claire as well at NCAR. So just to introduce the problem we're looking at. So, the Sahel is a arid region of North Africa, just south of the Sahara. And most of the rainfall in this region occurs during the West African monsoon, which peaks in July, August, September. So all my plots are showing this season in particular. And so the Sahel experienced a significant multi-decadal precipitation change, which saw a drying from the 50s to the 80s, and then a short recovery thereafter, which you can see in these plots on the right here. And so in a wide range of GCMs, we find that historical aerosol forcing can reduce rainfall, particularly sulfate aerosol forcing in the Sahel region of Africa. And so this can be seen in these plots from the CSM1 large ensemble, where we're showing the off forcing and then just the effect of aerosols on the left and right respectively for 2 periods, the 70s minus 50s and the 2000s minus 70s. And so you see that aerosols are the main external forcing driving a drying signal early on and then later a recovery. And I guess something important to note is that these anomalies are quite a bit smaller than what you see in observations. So obviously, I think most of the variability is internal, but there is some contribution from this external forcing. And so this is just showing the precipitation in the large ensemble alongside the SST anomalies in the Pacific and Indian Oceans. And so typically when you see this kind of aerosol force drying, it's interpreted as a response to hemispheric differences in sea surface temperature cooling, which you can see here. You have more cooling in the North Atlantic, and maybe it's causing a southward shift of the ITCZ, and that's what's causing the West African monsoon drying. But there have been AGCM simulations, for example, this paper by Dong et al., which find that sulfate forcing, in particular, in this case from Europe and Asia, can both cause drying in the Sahel, even in the absence of SST change. And so what we want to do is to clearly determine how these two components of the response to aerosols affect the Sahel. And so we're testing the ocean-mediated, also known as the slow effect, of aerosol forced SST change without emission changes. And so that would be like the hemispheric SST gradient. And then we're also looking at the direct atmospheric or fast response to changing aerosol emissions without changing sea surface temperatures. And so that would be like the rapid atmospheric response to European emissions. And so what we do is we conduct a set of time slice CAM5 simulations to separately test the roles of these two components of the response. And so I'm showing here the perturbations we apply in these time slice simulations. So on the left, we have the SST anomalies that we apply to the CAM5 SSTs for the ocean-mediated response. And we get these from the CSM1 large ensemble, all minus ALBA aerosol simulation anomalies. And since we are looking at pretty short periods, I think it's quite important that we're able to use a large ensemble in order to more confidently identify what the forced SST patterns are with less internal variability in them. And then I'm showing here the sulfate burden anomalies for the direct atmospheric response. And so what we're doing is setting the anthropogenic aerosol emission levels to target decade levels. And we're changing both sulfate and black carbon. And we're omitting fire emissions here. So these are the results from these time slice simulations. So starting from left to right, we have the total response, which is the addition of the two components, and then the direct atmospheric effect of the emissions and the ocean-mediated effect of changing the SST anomalies. And so we have the precipitation over Africa, and you also have the regional mean in this blue box in the bottom left for each of the panels. And so we find that most of the drying rather than being because of the SST anomalies, is actually because of the direct atmospheric effect with a weak ocean-mediated effect. And then later on in the recovery period, the recovery is caused partially by the ocean-mediated effect on the East Sahel, and then there's a small increase in precipitation from the direct atmospheric effect in the West Sahel. And so in order to better understand what's happening in these simulations, what we've decided to do is to further break down the direct atmospheric and ocean-mediated effects by taking a look at the regional components. So here we're looking at the effect of different emission regions and how they affect the climate. And so here I'm showing the sulfate and black carbon anomalies for the 2 periods that we're looking at. And I have contours showing where the burden anomalies are most associated with the different emission regions. So we have North America in blue, Europe in purple, Asia in red, and Africa in green. And in the case of the ocean-mediated response, we are instead looking at the effect of different ocean basins on this. So we perform tests by applying the aerosol forced anomalies in the Atlantic, Indian, and Pacific Oceans. And in this talk, I'll be focusing from here on out on the 70s minus 50s and just showing some of the selected experiments that have the largest effect on the Sahel. So in the case of the 70s minus 50s, looking at the burden changes, we would sort of expect a lot of the effect to be from European emissions because that's where most of the sulfate and black carbon burden anomalies are coming from. But actually, when we take a look at the precipitation effect of those emissions, we find that the European emissions have relatively little effect on precipitation over the Sahel, while in fact, it's actually the remote North American emissions that cause most of the drying, although it's not statistically significant in the regional average. And just to get an idea for why this might be happening, I think, so here we're taking a look at the top of model clear sky shortwave anomalies. And you can see that the effect of European emissions over the oceans is having a large negative forcing, but it suddenly stops over the Sahara. So perhaps the combination of the dust as well as the high albedo of the Sahara means that there's relatively weak direct radiative forcing, not direct atmospheric, effect over Northern Africa. And that's why we see this weak European effect. And then this North American drying might be a circulation change due to the North American emissions. All right, and then switching over to this ocean-mediated response, we see again, there's a weak response to these SST anomalies, even though there is a substantial cooling over much of the Northern Hemisphere. And what we find is that actually when the Atlantic cooling signal does cause a drying over the Sahel, sort of as we would expect from those maps. But in addition, we have that the Pacific cooling causes an increase in precipitation over the Sahel. And so there's a canceling effect of the SST anomalies in the 2 basins for this period. And so just to get an idea for why this is happening, again, I'm showing here the zonal mean moist static energy anomalies over Africa, so 15 west to 35 east, as well as the inset on the bottom, I have the zonal mean precipitation. And so Atlantic cooling, it reduces humidity and heat input into the monsoon. And so I think this is what is probably causing this reduction in precipitation as you get a reduction in MSC near the surface here. On the other hand, the Pacific cooling effect sort of suggests an upped ante-like mechanism where you get tropical Pacific cooling, which then cools the tropical upper troposphere globally and including over Africa, as you can see here. And then that is what's reducing, and that reduces the threshold for convection over Africa and increases precipitation. And so just to summarize that, so you see here the different regional averages over the Sahel, the precipitation anomalies, and so you see the opposing effects of Atlantic and Pacific. You also see that the Indian Ocean doesn't have much of an effect during this period, and there's a little bit of drying from the African and Asian emissions. And then if you add up the different simulations, you would sort of expect them to match the total effect, and they do, but the error bars are quite large because you're adding up the internal variability from from 4 different simulations. So it's maybe not that satisfying, but it matches. But there's this huge error bar. And just to quickly go over the 2000s minus 70s effect, so the recovery period effect, we end up seeing African emissions. So there's a small increase of sulfate as well as black carbon over West Africa during this period. And so that causes a bit of drying, and you get less effect from the other regions. And in the case of the ocean-mediated effect, you have Atlantic warming or North Atlantic warming during this period. So the effect of Atlantic SST anomalies switches signs, while the Pacific continues to cause an increase in precipitation, which may be due to additional cooling in the tropical West Pacific. And so those add up to give you this increase in precipitation in the total. Although, again, you can see that there's a bit of a mismatch, but the error bars are quite large. So there might be some nonlinearity, but I don't think we have enough data to conclusively say that yet. So to summarize, it seems like based on our results that the mechanisms of how aerosols affect precipitation in the Sahel change with time as well as and the resulting changing spatial pattern in emissions and SSTs. And in particular, when we're looking at the 70s and minus 50s, we find that most of the drying is direct atmospheric due to the North American emissions. And then later on, and then the ocean-mediated response is the result of a canceling effects of Atlantic and Pacific anomalies, which switched to complementary effects in the later period. So thank you. And if you have any questions, I'll be happy to take them.
Thank you. Now we have time for a few questions. And Ella, right?
Yeah, I was just wondering if your results are kind of contradicting the hemispheric energy imbalance arguments like Huang and Frierson. It seems like it matters where that imbalance is. Is that the correct conclusion? So you could have a big change in the radiative forcing over Europe, but it's not going to shift the ITCZ in this region in the same way.
Yeah, I think, well, yeah, like for example, here this Pacific anomaly is, it's big, you have like a big cooling in the North Pacific, but you still get this increase in precipitation. So yeah, well, so that causes like a southward shift of the ITCZ in the Pacific, but the answer is different in the Atlantic, I guess. So yeah, it seems like it's not quite as straightforward as just the hemispheric differences.
Yeah, thanks.
Any other question? Okay, if not, we move on to the last talk of this session. It's John O'Brien, and the title is Quantifying the Force Changes to Enforce Modes of Atmospheric Variability. John, go ahead.
Cool, thank you. Can everyone hear me all right?
Yep.
Okay, great, and see my screen?
Yes.
Awesome. All right, excited to be giving this talk. Quantifying force changes to unforced modes of atmospheric variability. This is work I've done with Clara Desser as part of my postdoc here at NCAR. So the goal of this study is to assess the role of anthropogenic forcing that it has on internal unforced modes of atmospheric variability. For this study, we're going to focus on interannual North Pacific atmospheric variability in the boreal winter. We're going to use the CESM large ensemble, combined using both the historical and the future simulations, which total 180 years, and we're going to be using DJF averages. We're going to use an ensemble-based EOF method in this study, known as the snapshot EOF. This is fairly new in the climate literature, so I'm going to go into what exactly a snapshot EOF is. If we conceptualize the large ensemble as a four-dimensional object, two spatial dimensions, a time dimension and an ensemble dimension, our traditional EOF is applied along the time axis. And in a lot of ways, this is suboptimal because the statistics in the time dimension are non-stationary. There is primarily from anthropogenic forcing, but also from aperiodic forcing such as volcanoes. This makes the EOF sensitive or dependent on the time window over which you want to apply the EOF. So results aren't necessarily going to be statistically similar. However, with a large ensemble, we now have another dimension to work with. And this is the snapshot EOF is how we apply the EOF across the ensemble dimension. In this case, we have zero mean stationary statistics, where each realization is an independent an independent mode of variability for the forcing at that given instant in time. Further, what we'll do is we'll use a 5-year running window to increase our sample size for the EOF calculation. So we'll have 5 years times 40 members, we'll have 200 years per SEOF calculation. So given that we're using these stationary zero means statistics to calculate our EOFs on, by kind of construction, they will isolate these unforced modes of variability in the atmosphere at each individual instant in time, so for a given instantaneous forcing. So jumping right into results here, the EOF is calculated over this North Pacific domain using 500 hectopascal heights. And what we see here for our first EOF is the familiar PNA pattern. Stippling corresponds to significance of the regression along the ensemble dimension at 0.1. And because we have an SEOF at each moment in time, we can watch how this pattern, this first mode, changes as a function of external forcing or time here. What I'm also plotting here in the center is the center of action of the PNA pattern, just indicated by the location of the max depth, and it is colored by the year on which the SEOF is calculated across. Below the animation, I'm showing the first and last frames of the animation. So the first SEOF versus the last SEOF. And there are three main things to take away here. One is that there is a substantial deepening of the PNA pattern, indicative of greater variability towards the end of the 21st century. The second thing to notice here is that there is a very uniform and consistent connection to the tropics here. And the third thing to see is that there is this extension, this transatlantic extension of the teleconnection of this pattern across the Northern Atlantic. So we can take these snapshot principal components that are along the ensemble dimension, and then we can regress them along the precipitation anomalies in that same dimension. And so what I'm showing here are the 500 hectopascal contours associated with, again, the first and the last SEOF. And we can see this amplification of the PNA pattern itself But what also stands out in the precipitation field is this very strong and increasing connection to the tropics. And we can also see here the enhancement of the precipitation associated with this cyclonic circulation associated with the PNA pattern. And it's almost more easy to see the effect of this kind of the change in the transatlantic teleconnection here associated with this. So the PNA shows about a 30% deepening as a result of climate change here. And so to kind of get further into this, the PNA is not the only mode that is important for extratropical variability. There are also other lower order modes that are also known to be important as well. So we're going to look here also at EOF2 and EOF3. This is EOF1, what we were just looking at. EOF2 shows this kind of meridionally oriented dipole structure reminiscent of the MPO pattern. There is not much of a, if really any, tropical connection to precipitation here, but by end of the 21st century, there is. And this NPO-like pattern has now kind of changed its structure and the way it is oriented, and actually looks more like a more continuous wave train where you have this high, low pattern, where it's indicative of this kind of semi-hemispheric wave train. EOF3 is really interesting. It is associated with subtropical moisture transport from the Hawaiian Islands. And this would be associated with atmospheric river activity, specifically of the kind of Pineapple Express flavor, where you're getting this Hawaiian Island moisture transport. And you can see that this pattern really deepens in the future, as well as increases its the precipitation associated with this cyclonic circulation and the precipitation connection to the tropics here. So rather than looking at the first and last SEOFs, we can more succinctly summarize these changes by regressing along the time dimension, since we have a sample at each time step. And if we do that, we can see that these the changes in time now are, you can see this deepening a little more clearly, and this pattern that extends out across the North Atlantic, and this steady increase in the connection to tropical precipitation. We can see the same thing here in EOF2, a very clear connection to the tropics. The pattern of change here is, it's a little harder to interpret. That's why it's nice to actually look at the individual beginning and end patterns. And what the pattern that shows the most change across time is interesting. This EOF3 mode associated with subtropical moisture transport shows a substantial enhancement of the cyclonic circulation anomalies that are associated with this pattern, and the precipitation that is also associated with it. So there's a clear connection to the tropics to all these modes. And so the idea of this study is to understand extratropical variability, and that only, not and control for what's going on in the tropics. So how do we do that? It's well known that the SST perturbation associated with ENSO is the largest source of tropical variability. And when I say ENSO, I'm trying to be very clear here that I'm talking about the SST perturbation and not the teleconnection, which aren't necessarily synonymous or one for one. So what we'll do is we'll calculate the first EOF and SEOFs of tropical SST variability, classically associated with ENSO. We're going to include all these modes of variability into a single multiple linear regression model, where the independent variables are the ensemble principal components, which are indexed by time. So this multiple linear regression will take place across the ensemble dimension at each time step. And by doing this, we can separate out our tropical and extratropical modes of variability, and then look at the relative contributions from each mode by plotting their respective regression coefficients. So what we had before with just our direct snapshot principal component regressions, now we're including ENSO, or the the mode associated with the first EOF of tropical SST variability. And what we see here looks very much like what we're used to for ENSO, deepening of the PNA pattern and enhancement of West Coast US precipitation. This tropical precipitation anomaly, which in the future, by end of 21st century, is enhanced. And this deepening of the pattern and this extension of the transatlantic teleconnection out to Western Europe. So now our results from the multiple linear regression model, if we're looking at our tropical Pacific mode first, the precipitation does not change substantially in the tropics, which is what we would expect because this precipitation is tropically forced by the SST perturbation associated with ENSO. What we do see change substantially is the extratropical response, because what we've done here is we've removed or separated out tropical and extratropical variability. So we're looking at the component of extratropical variability that is associated or originates from the tropics. And we can see that this pattern is primarily affecting central and southern California and across the southeastern US, which is kind of a classic ENSO-like pattern. And we could see that this pattern is amplified and enhanced, and that this transatlantic teleconnection is associated with ENSO variability. EOF1, which is the PNA, first thing to notice here is that ENSO variability has been removed. There is no connection to the tropics anymore, and that's exactly what we were trying to achieve. We wanted to understand how extratropical variability changed as a result of anthropogenic forcing and not tropical ocean forcing. And you can see that this pattern still shows the same amplification. So this is indicative that this is a result of climate change and not a change in tropical ocean variability. EOF2 shows pretty much the same thing as far as the extratropical atmospheric response. The patterns do not change substantially, indicating that there was not a large influence to ENSO with regard to how the pattern behaved. You still see this development of this kind of semi-hemispheric wave train. There is some residual precipitation variability here, but that would not be associated with ENSO. That could be two things: either an example of the extratropics forcing tropical precipitation, or this could be a result of a lower order tropical mode, say like tropical mode EOF2, for example. And then EOF3, again, we see that the tropical component of precipitation has been removed, and that we still see this enhancement of this subtropical moisture transport, indicating that this is a result of anthropogenic climate change. Again, we can more succinctly summarize these changes by linearly regressing the coefficients through time. What we didn't see before was the linear regression of ENSO and this kind of deepening of the pattern. But now when we control and remove the extratropical variability, we see that this pattern here has shifted from the northwest down to the southeast, and that there is an increase in the variability associated with tropical precipitation. And this is associated with greater an enhancement of tropical hydroclimate variability. We can see that the PNA pattern, rather than being kind of smoothed out by this response, because it is commingled with ENSO here, it is now separated, and we can see this kind of deepening and this kind of increase of the cyclonic circulation associated with this pattern and the associated advection of North Pacific moisture. EOF2, again, doesn't show huge changes, either in precipitation or in the atmospheric pattern associated with it, potentially out here in the North Atlantic. And again, EOF3 shows the most distinct changes, where again, we have removed the tropical component, yet this mode of subtropical moisture transport is still enhanced in and of itself. and the enhancement of that cyclonic circulation advects moisture from the Hawaiian Islands, which would be indicative of a greater propensity in the future of pineapple-like or pineapple express-like atmospheric rivers. So now that we've separated out and have individual representations of all these three components, we can look to see how they interact. And so if we look at the correlations, starting off first between ENSO and EOF1, extratropical EOF1, so this would be the PNA pattern, it is always very high. Starts off early in the record at around 0.5, and this is what we've come to know, that the ENSO does excite the PNA pattern, and this does not change in the future. If anything, it gets slightly stronger. EOF2 goes from having a negative relationship with ENSO to around 2020, where it starts going positive and shows this very kind of monotonic change in the relationship towards the end of the 21st century. Again, EOF3 shows the most interesting changes, where early in the record is kind of characterized by this very high variability, and where some years it is as important as the PNA pattern to the ENSO teleconnection, and some years it is not excited at all. However, when you get towards the end of the 21st century, this mode becomes as important or more important to PNA to the ENSO teleconnection. And again, this mode is specifically associated with subtropical moisture transport from the Hawaiian Islands to the Western US. So this suggests that ENSOs of the future could be characterized more by North Pacific atmospheric moisture transport, as well as subtropical moisture transport, essentially getting a kind of a double whammy ENSO in the future. So to summarize here, we were able to employ an EOF-based framework to isolate modes of North Pacific variability, and then use a multiple linear regression model to partition variability that's intrinsic to the extratropical atmosphere from variability arising from tropical ocean forcing. Both the PNA pattern and EOF3 show a substantial strengthening by the end of the 21st century that's a result of climate change. This is indicative of a greater Western US hydroclimate variability in the future. The tropical SST perturbation associated with ENSO shows a spatial transition that shows grit enhancement of the effects in the South and Southeastern US with a greatly enhanced transatlantic teleconnection. And the ENSO-PNA correlations, their interactions remain high and slightly increased by the end of the 21st century. However, ENSO appears to preferentially excite this EOF3 mode in the future, whereby it becomes as important as the PNA pattern, leading to enhanced subtropical moisture transport. And with that, thank you, and I'll take any questions.
Thank you, John. Questions? Okay, Nicola?
Oh, hi, great talk. I was curious, how noisy are your snapshot EOFs like in time?
Not very. As you could kind of see from the animation, they're extremely stable. And this is a result of using that 5-year running window, where you can assume a stationarity in a kind of a 5-year time period. And so you get those 200 samples informing the EOF. So from year to year to year, they're extremely stable. And we did just the 40, just like a single member, and you could definitely see the effect sampling has in that increasing the sample size and leading to greater stability.
Yang Ho.
Hi, interesting talk. So I just have simple question. So you try to separate the effect of the extratropical atmospheric variability versus the tropical ocean OS interaction. But wouldn't it be more accurate to say the extratropical climate variability interaction between ocean and atmosphere or land and sea ice, whatever is intrinsic to the extratropics versus tropics, rather than just saying intrinsic mid-latitude or extratropical atmospheric variability?
If I understood your question correctly, you're saying, would it be more accurate to just include variability from, or say this includes variability from land and sea ice forcing? Is that correct? I'm not 100% sure.
So everything in the extratropics versus tropics.
Yeah. I mean, yeah, extratropical variability is driven by a lot of things. A lot of it is internal to the atmosphere, and there are some components that, like, sea ice can affect the extratropical variability as well. For the PNA pattern, that is an inherent mode that I think most likely is just inherent to the atmosphere, and things like sea ice would play a much lesser role as opposed to, say, tropical influence, but that's not something that we have specifically parsed out.
Thank you.
Yeah.
Okay. Jerry.
Yeah, he just answered my question.
Okay.
I'm going to ask about the sources of, what's the drivers of the extratropical modes.
All right.
Yeah.
Other question?
Yeah, sorry, this is Claire. I maybe just follow up, I think, on these very good questions of Young-Oh and Jerry. JP didn't show it, but he's analyzed the long atmosphere only control run. And he finds those same Z500 EOFs that he obtains after doing the multiple linear regression. So I think, at least in this model, that does point to that his EOFs in the multiple linear regression model are primarily intrinsic atmospheric variability. It doesn't mean in the real world that ocean and ice, extratropical ocean and ice don't affect those modes, but at least in this model, I think we have some good evidence that it's just atmosphere only processes. Thanks.
Yeah, thanks for mentioning that, Clara.
Maria.
Thanks. Super interesting talk. I have a question about the multivariate regression. And I was curious about how sensitive the coefficients were to the number of variables that you were considering. Had you tried fitting that regression to just, let's say, the ENSO EOF and then the one of the extratropical?
I actually did do that. Yeah, so that was, I originally started off with, just calculating extratropical variability. And then I saw that, there was clearly this tropical influence that I needed to control for. So I had originally started with a multiple linear regression model, just using the PNA and ENSO. And we went to higher order modes, partly to test that, but partly to understand or to account for more extratropical variability. And so when we increased the number of covariates from 2 to 4, the patterns associated with the PNA and ENSO did not change hardly at all. And this is suggestive that because we're using this 5-year window and we have the large ensemble, we're getting really good sampling. And this is, something I'm kind of wondering whether I should do now, is whether I should include more modes. And it's this argument of you try to achieve parsimony and high samples in your model, or do you try to account for more and more modes? But to your point, the 4-variable model is very well informed at present with the samples that we have.
Excellent, thank you.
Yeah.
Any other question? And if not, now is our lunch break time. Let's thank all the speakers this morning. And we will reconvene at 1 o'clock this afternoon. and see you in 1 hour.
Hi, Anne. Do you want to check your screen share?
Okay, thanks, Isla. Can you hear me?
Yep.
Looks like I need to give my system permission.
Hi, Isla. I'll bring up that slide again as a placeholder so people know that we're back at 1 Mountain Time.
Okay, I think Hyann is just trying to check her screen share.
Okay,
so
I'll hold
maybe
off
we'll
on.
tell it
Sure.
for a minute or two. Are you having trouble, Hyann?
Can you hear me now, Isla?
Yep.
Okay, great. Let me try again. No. Application window. Okay, can you see my screen?
Yep, looks good.
And let me try the pointer. Can you see the pointer?
Yep.
Okay.
It's not full screen at the moment, but I guess you'll view the slideshow or
I can do a full screen. Oops. Okay. Can you see the pointer? Okay, great.
Actually, no, I did not see the pointer now.
Oh.
I think if you click on that little pen thing down on the bottom left.
Okay. Laser pointer. Can you see the pointer now?
Yeah.
Okay. We're set. Thank you so much, Ilo.
Okay. And I saw emails from you, but I haven't read them. Is it all good? You have some issues about it?
Email.
Sorry?
I don't think I've sent you an email.
Oh. Was it someone else? Yeah, you did. You sent one at 10:04. Oh. I think Elizabeth maybe had CC'd.
Oh, it's Elizabeth's email. I asked Elizabeth not to post my PowerPoint online, and she probably forwarded my email to you.
Okay, but it
doesn't matter because I'm kind of I'm still writing the manuscript. I don't want to upload my my PowerPoint online, but video is fine. If people just watch and listen, it's fine. I just don't want to post thoughts and. But it's no big deal.
That's no problem. Thank you. Yeah, because Ryan and I have to try to figure out to stop the stream and then restart it, and we haven't tested that yet.
I know it's the hassle, and the video tip is really no big deal, but I just feel it's still early for me to post the PowerPoint online. Thank you so much, Elizabeth. Whatever you want to do, just go ahead and just don't post the PowerPoint.
Okay, thank you.
Okay, I'm all set, Isla, and I kind of want to hear your comments later about this work because it has something to do with I'm casting lots of doubts about models simulated AMV and IPO, especially AMV, and I think you're working on simple simple atmosphere land coupling models, coupled models, and I think it will be. I'm very interested in using your tool to test how land coupling affect the amplitude and the amplitude of AMV and things like that. And I think it may help to explain why the models simulate very weak multi-decadal variability, like the multi-decadal trends. And so I like to hear your comments.
Okay. Yeah, sounds interesting.
Okay. I'll talk to you in an hour.
Okay. Yeah, sounds good. Will you stop sharing?
Oh.
Because then Elizabeth can put up the kind of.
Okay, I just closed my file. I think that will end the sharing.
Okay.
And by the way, I just contacted Ted Shepard yesterday, inviting him to give a US Clever webinar in March about storyline. And I think if you are interested, I can forward you the link once we make the announcement. And I'm very interested in his work too. And it's I think it's a useful. A month ago, I sent you and Laura and Yaga the paper, a storyline paper, and I think it fits the trend of or the interest of the community kind of shifting towards a system prediction, and we're kind of frustrated with the model projection of regional climate change. And I think the storyline approach encourage us to use the model as approach, but not limited. Our work is not limited by the same kind of modeling framework, and we can use a model to and the real case to help us understand the processes of extreme events. So I think this can help give NSF a reason to support our system prediction. You look tired.
Yeah. No, sorry. I just was, it's been a lot of Zooms.
Okay.
Yeah, no, I agree.
I'll
I
let
think that would be interesting.
I'll let you go.
Yeah, forward the information when you have it. I best go and get some lunch before.
Yeah. Thanks for help.
Okay, see you.
Bye.
Everybody is special. 你这儿来以后，你看人家不 special。这个就跟几个还不一样。
All right, hello everyone, welcome back. I hope you're there. It's 1 o'clock, so we'll get started with the first set of talks this afternoon, which are focused on kind of climate change trends and impacts. And so the first speaker is Karina Yang, who's going to be talking about widespread reductions in human labor capacity after 1.5 degrees warming. So Karina, if you're able to share your slides. And just a reminder for the speakers, it's a 20-minute slot, so aim to be wrapping up at about 15 minutes, and I'll give you a warning then if you're going over. Karina, are you having some issues or?
Sorry, I'm good now. Thank you.
Okay.
All right. Am I audible?
Yep.
All right. So hi everybody, my name is Karina. I'm an undergraduate student at Princeton University, and today I'd like to present my research projecting future reductions in human labor capacity due to global warming. So to motivate this, it's well known that rising temperatures due to climate change are leading to an increased severity and frequency of extreme heat events, which poses as a major human health threat. And when we look at the human health effects of extreme heat, it's important to consider not only temperature, but also humidity, because at high relative humidity, the evaporative cooling effect of sweating decreases, and that increases the risk of heat stress, as shown in this little figure here. So one common metric that's often used to measure heat stress for human health applications is called wet bulb globe temperature. And it takes into consideration not only just regular temperature, but also humidity and other factors such as wind chill and solar radiation. So this figure plots both temperature and wet bulb globe temperature from the end of the 20th century versus the end of the 21st century. And you can see the expansion of hot regions for the top row, and on the bottom row, the expansion of hot and humid regions. And even though there are a lot of similarities, there are also a few key differences. For example, we can observe that the Western United States, as well as Central Asia, experience extreme heat, but not necessarily extreme humidity. So they don't show up as vulnerable in the wet bulb globe temperature plots. So increasing wet bulb globe temperature has pretty important impacts for human labor, because when you're performing physical activity, the risk of heat stress increases. And in workplaces where air conditioning isn't available, one of the most common strategies to combat heat stress is to take longer breaks. And international labor organizations actually have regulations that map certain levels of wet bulb globe temperature to appropriate work rest cycles that maintain human safety. So essentially, as wet bulb globe temperature increases, human labor capacity decreases because you can spend less time actively working. And in this inset figure here, it plots wet bulb globe temperature against labor capacity. And you can see that at low wet bulb globe temperature, you have 100% labor capacity, meaning that continuous heavy labor is safe. Whereas if you get to high extreme wet bulb globe temperature, labor capacity actually goes to 0, which means that no labor is safe. And previous studies have projected the impacts that climate change will have on global average human labor capacity, showing that historically it was around 95%, but that under an RCP 8.5 scenario, by 2200, that'll decrease to around 40%, which has major economic repercussions. So for my research, I had two main goals. I wanted to expand on prior work by using ESM large ensembles to estimate the timing of first emergence for significant labor capacity reductions in vulnerable regions. So not just looking at the magnitude of reductions, but looking at when exactly they might happen, which can help inform the timing of action for adaptation efforts such as workplace air conditioning. In addition to that, I also wanted to characterize the uncertainty in the timing of these reductions that stem from two factors: climate model design and internal climate variability. So moving on to my methodology, I used data from two Earth system models, GFDL ESM2M and CESM2, both under comparable high emission scenarios of RCP 8.5 and SSP 37. Each ESM large ensemble had 30 ensemble members each, and I used daily mean metrics for temperature, humidity, and pressure. Using those metrics, I then computed daily mean wet bulb globe temperature and converted that to labor capacity using the algorithm that I showed in the previous figure and took the monthly mean of the labor capacity. I then took those monthly figures and split them into historical data from 1980 to 2000 and future data from 2000 to 2100. Based on that, I defined a metric that I called time of first emergence, which is the first year in which a grid cell experiences summertime labor capacity reduced by a certain percentage relative to its historical labor capacity levels. And the two thresholds that I analyzed in this project were 25% and 50%. So moving on to some results. This plot shows the ensemble mean time of emergence, which is essentially the projected time of emergence for 25% and 50% levels of labor capacity reduction during the summertime. The top row is for the ESM2M model, and the bottom row is for CESM2. And as shown in the color bar, each color represents a different 5-year period in which the first occurrence of this level of labor capacity reduction occurs. So darker colors represent time of emergences that are closer to the beginning of the century. Lighter colors correspond to the end of the century. And grid cells that don't experience these levels of reduction at all are blacked out in gray. So across the two models, between 31% and 44% of the global land area is expected to have experienced at least moderate reductions of 25% by the end of the century. We can observe that a lot of them are in these tropical and subtropical regions, with a few critical vulnerable regions also boxed in the first panel here. Looking at some specifically vulnerable regions, we can also see that in the CESM2 model, both the southeastern US and the entire Indian subcontinent are expected to experience region-wide labor capacity reductions of 25% by around 2040. Comparing the two models, we can also see that CESM2 tends to have larger affected areas and also earlier time of emergences by around 12 years due to CESM2's higher climate sensitivity. So although the ensemble mean represents the projected time of emergence, we can also analyze the uncertainty that stems from internal climate variability. And that I did by analyzing the ensemble range of first occurrence, which is essentially the latest time of emergence among the ensemble members minus the earliest time of emergence among the ensemble members. So putting that into a way that's easily conceptualizable, we can look at this example grid cell in West Africa. Based on the plot from the previous slide, it had an expected time of first emergence of around 2070. But because it has a range of 40 years, if it gets lucky, it might not emerge until 2090. But if it gets unlucky, it could experience its first occurrence of reduced labor capacity as early as 2050. So between the two models, between 48% and 76% of vulnerable locations are convergent within 30 years, so they have a range lower than 30 years. But there are also hotspots of internal variability where the range is higher, up to 50 years, and these are marked in yellow and orange in the panels. Now, building upon the idea of internal variability being significant at the local scale, this plot shows the full ensemble spread of time of first emergences among the ensemble members for select cities. So in this case, we can look at Delhi as an example. So each bar represents the time of first emergence from one ensemble member. And we can see that the spread is pretty large here. The earliest one is in 2020, but the latest one isn't around until 2060. We see a similarly large spread for the other cities displayed here as well. So we can see that in general, localities have significant internal variability. But despite that, we can also make a few observations with pretty high confidence. For example, there's high confidence that the first occurrence of moderate reduction will occur prior to 2060, because as seen here, all of the bars from both the two models and all ensemble members occur prior to 2060 for this moderate threshold. We can also compare the city level time of first emergences to regional time of first emergences. And here I calculated regional average time of first emergence by taking the population weighted average of the grid cell time of first emergences for each region, which again are illustrated in this little panel. So for example, we can compare the time of first emergences for Delhi versus those of the Indian subcontinent as a whole. And we see that if we compare different spatial scales, internal variability uncertainty decreases as you get to larger spatial scales, from Delhi to the region of India to the entire globe. So for the local grid cell level, it was around 40 years. For the regional level, it's around 20 years. For the global level, it's less than 10 years. We can also observe that the internal variability uncertainty reduces at higher reduction thresholds. So it's smaller for these dark bars that represent the 50% reduction threshold. And that is likely because at these higher severities of reduction, it's less likely to occur due to natural variability by itself. And the forced climate signal actually plays a larger role. So we have more certainty in predicting these time of first emergences. So finally, I looked at the progression of labor capacity reductions over time. So I plotted the fraction of the population for both the globe and for vulnerable regions that have experienced reduced labor capacity based on the time of first emergences for each year between 2020 and 2100. And looking at this panel for the globe, you can see that by 2100, between 50% and 70% of the global population is expected to have been affected by moderate reductions, and around 20 to 50% are expected to have experienced severe reductions. If we compare that to these different regions, we can also observe that they all share this characteristic shape of rapid onset that kind of resembles logistic growth. So at the beginning, a very small portion of the population has experienced reductions, but once they start, it increases very rapidly and very suddenly, and then flattens off at the saturation level, at which point basically all the vulnerable population has been affected. And we can also see that for a lot of these regions, for example, the Indian subcontinent, Southeast Asia, West Africa, the saturation level is near 100%. So that means that almost the entire population is vulnerable to these labor capacity reductions. Comparing the two models, you can see that there is again a pretty noticeable difference between CESM2 and ESM2M due to the differing climate sensitivities. But what we can do for that is instead of plotting this against time, we can actually normalize it by temperature, which is shown in this plot here. So essentially, we map each year and the different ESMs to the corresponding change in global average surface temperature, and then plot the same effective fraction. And when we do that, these models actually converge a lot more. So you can see that these light blue dots and the light red dots converge, as well as the dark red dots and dark blue dots. So that shows that the forcing pathway or the speed of emissions doesn't necessarily affect the timing of labor capacity reductions. It's more just the global surface temperature that dictates the level of reductions. But what the speed of emissions does affect is how much time we have to prepare for it. So for example, we have plotted the effective fraction for ESM2M versus for CESM2 at 2050. And the effective fraction is a lot higher if we have a higher emissions, which means that we have less time to prepare for that. And again, we see this trend of rapid onset that occurs around 1.5 degrees Celsius. So beyond 1.5 degrees Celsius, the effective fraction really jumps. And that is in alignment with the Paris Agreement and a lot of other studies that have shown that 1.5 degrees Celsius is this critical temperature that leads to far worse effects of climate change. And that if we can mitigate below that, we can avoid a lot of those adverse effects. So overall, just to summarizing what I talked about and a few key takeaways. In terms of large-scale impacts, large populations in the tropics and subtropics are threatened by labor capacity reductions that are expected to occur over the 21st century. And within vulnerable regions, with some of them being the Indian subcontinent, Southeast Asia, West Africa, there's a trend of rapid onset in which the population really jumps that's being affected suddenly and very dramatically. And that this trend of rapid onset can start as early as the 2040s, so within the next 2 decades. Taking a look at uncertainty, when we're talking about internal variability uncertainty, this is significant locally, so at the grid cell level, and it precludes very accurate predictions. But if we go to larger spatial scales, such as the regional scale, we get more certainty and we can make more certain predictions for timing of action. And also, if we look at model uncertainty, there is model uncertainty between the two models I looked at due to their different climate sensitivities. But when we normalize by temperature, we actually get decreased uncertainty and they converge a lot more, which again allows for better predictions when we talk about temperature. And finally, broad implications. There is a significant possibility of sudden and severe labor capacity reductions beyond 1.5 degrees Celsius of global average surface temperature warming. And this once again emphasizes the importance of mitigation to reduce global warming. And finally, it's important to note that these decreases in labor capacity disproportionately affect developing nations, because in contrast to regions such as the United States, where we have workplace air conditioning pretty common, in developing nations, there is not only a greater degree of manual labor, but also reduced cooling access. So workers there are especially vulnerable. And this requires precautionary measures, such as workplace air conditioning, to be able to avoid the health and economic repercussions that could propagate global inequity if this occurs. All right, thank you, and I'd be happy to take any questions.
Thank you. Are there any questions for Karina? Please either raise your hand or put them in the chat. I guess I had a question. So you showed that if you take a global average, there's obviously a bigger signal to noise ratio. I was wondering if you, and I apologize if you showed this, but if you took a tropical average where the response is really large, presumably it would be an even bigger signal, and maybe I was wondering if the time of emergence would be soon enough that we should actually be seeing it already.
So the global average I took wasn't the entire world, it's the global vulnerable area. So it's essentially taking all of the grid cells that are already likely to be affected.
Oh, okay, so there's that. So even then you can't, okay, so even then the time of emergence was past where we're at now, right? It was like 2040 or, did I get that right? Okay, so we shouldn't necessarily be seeing it already in the kind of tropical average. Any other questions? People a chance.
A comment.
Yep.
You analyze this the CESM2 large ensemble and GFDR large ensemble. They are following a different climate scenario. Actually, SSP7 and emission scenario is lower than RCP 8.5. To better compare, you may want to analyze CESM1 large ensemble, which for the future projection session, we use the RCP 8.5, which is more comparable with GLDR model. So the difference between these two models may not just because the climate sensitivity is different, it's also the emission scenario is quite different too.
That is also true. Thank you for the comment.
All right, well, if there are no more questions, then we'll move on to the next speaker. Thanks, Karina. So the next speaker is Nicola Marr, talking about more accurate quantification of model-to-model agreement and externally forced climatic responses over the coming century.
Sorry. Okay, can you see my slides?
Yep.
Okay, perfect. Okay, so I'm going to talk about some work I did in my previous postdoc, sorry, at the Max Planck Institute for Meteorology with Scott Power, who's at Monash in Melbourne, and Joachim Marotzka, who was my supervisor. And I'm going to talk about accurately quantifying model agreement. Okay. Okay, so it's important to understand why our model projections differ, and they can differ for 3 different reasons. They can differ because the models are actually different. They can differ when we look at single model realizations because of the phase of internal variability, and they can differ because of the scenario choices we make. And the magnitude of each of these types of uncertainty depends on both the variable you look at, but also the timescale and the location. And this quantification of uncertainty is complicated by the fact that the models aren't completely independent and they share components and code. And so today I'm going to talk about the methods I use to quantify uncertainty. I'm then going to quantify uncertainty due to both internal variability and model differences in long-term projections. And I'm going to look at temperature and precipitation, but I'm also going to look at the temporal variability. And then I'm going to talk about a simple example of assessing model-to-model agreement specifically over the tropical Pacific. Okay, so in this study, I'm going to look at projections in RCP 8.5 over the period 2050 to 2099 as compared to 1950 to 1999 in the historical. I'm going to use 6 single model initial condition large ensembles, SMILES, and I'm also going to use CMIP5, but I'm going to use CMIP5 in a slightly different way, where I create small ensembles of CMIP5 models that share an atmospheric component or have a similar atmospheric component, and I'm going to treat them like small ensembles of climate models that are the same. We're going to quantify uncertainty due to internal variability by quantifying the internal variability uncertainty in each individual ensemble and then averaging across the ensembles. The uncertainty due to model differences is quantified as the spread of the ensemble means. And the forced response in each individual SMILE is quantified as the ensemble mean. Okay. And so I'm going to start with my summary plot, which shows us what you gain from the methods that we use. And so in this plot, on the left-hand side, you see each SMILES individual ensemble mean in a dot. So each different color is a different model. And the error bars here aren't actually error, but they're the uncertainty due to internal variability. In the middle panels, or the middle column, you can see just the ensemble mean from these CMIP5 atmospheric subensembles. So these are, again, models that share an atmospheric component. And I highlight the ones in blue because they only had one member, so perhaps they might be outliers. And on the right, I show the CMIP5 projections. And these are shown for all ensemble members in red and just the R1, I1, P1 in blue. Okay. And so if we look at the top panel, this is projections of global mean surface air temperature. And if you look at CMIP, you can see that all CMIP ensemble members say that the global mean surface temperature is going to warm, which is what we'd expect. But we can't really say how much of the spread of the CMIP models is due to model differences and how much is just due to internal variability. And by looking at the SMILES in the left-hand panel, you can see that the ensemble means from the SMILES cover basically the whole spread of CMIP by themselves, but their internal variability is very small. And if you look at the middle panels from the atmospheric CMIP method, you can see that the ensemble means also cover kind of the spread of the CMIP5 and the spread of the SMILES. And so by using this method, we can say that the range of CMIP5 projections we see for global mean surface air temperature is purely controlled by model differences. There's not really any influence of internal variability. This differs if we look at different variables. If you look at the second set of panels, so the second row, this is now temperature variability projections over Northern Europe. And in this case, you can see that the SMILE means agree quite well. And the spread of the CMIP5 ensemble means, so the CMIP5 atmospheric subensemble means in the middle panel are also a lot smaller than that of CMIP5, whereas the internal variability in the SMILES is quite large. And so from this, we can say that a lot of the CMIP5 spread for temporal temperature variability over Northern Europe is controlled by internal variability. And if you look at the bottom panel, which is precipitation variability projections over Southeast Asia, you can see by comparing the three different ensemble sets that the CMIP5 spread is controlled by both model differences and internal variability. Okay. And so I'm going to now apply this kind of separation globally for 4 different quantities. And here I show mean state temperature projections. The top row shows our estimates made by the SMILES, and the bottom row shows the estimates made from these atmospheric subensembles of CMIP5. The left-hand panels show the projections of mean state temperature. And you can see they agree quite well between the two methods, and they are what we would expect. You see more warming in the Arctic and over land and in the Northern Hemisphere than you do over ocean or in the Southern Hemisphere. If you look at the second column, this is now our estimate of the uncertainty due to internal variability. You can see for the SMILES, it's fairly small, but it's a bit larger using the atmospheric subensembles. And I think this is just because this is a failure of the method where those subensembles are not containing exactly the same models. And so we're pulling in some of the model uncertainty into the estimate of internal variability. If you look at the third columns, you see the uncertainty due to model differences, and you can see it agrees quite well between the methods, and the uncertainty due to model differences tends to be larger over land than the ocean, and in the high latitudes, Southern Ocean and over the Arctic. And finally, in the right-hand most columns, we show the percentage of the variance due to model differences. And this is just the percentage of the sum of the two different uncertainties, so uncertainty due to internal variability and the uncertainty due to model differences. And basically the point here is that if it's red, model differences are more important. If it's blue, internal variability is more important. And if it's white, they're a similar magnitude. And for this case, you can see that using both methods, we tend to find that model differences are much more important for mean state temperature projections on long time scales. And this agrees well with previous work. So we can do the same thing for mean state precipitation projections. Again, the left-hand panels show the projected changes themselves, and they agree quite well with previous work, such as that by Angie Pendergrass. The second column shows the uncertainty due to internal variability. You can see again in the smiles, it's quite small. It's largest in the Western Pacific. And you can see again that the atmospheric subensemble method overestimates this uncertainty. When we look at the third set of the third column, you can see the uncertainty due to model differences. And you can see that the two methods agree that the model differences are most important in the tropics. When we look at the last column, we can see again the percentage of the variance due to model differences. And you can see again, the maps are generally red, which tells us that for mean state precipitation projections on this long time scale, model differences are more important than internal variability. Okay, but we can also apply this to temporal variability. And this gets a little bit complicated because we're looking at the variability of variability, but bear with me. And so if you look at the left-hand panels, and this is annual mean temperature variability in this case, you can see again, the SMILES and the CMIP5 atmospheric subensembles agree on their projections. And you can see that there are projected decreases in variability over the northern over the high latitude oceans, perhaps due to ice changes. And you can see projected increases over large parts of the kind of tropical and extratropical land surface. When we look at the uncertainty due to internal variability, you can see that now the methods agree quite well, and we see kind of larger uncertainties over these high latitude oceans. When we look at the model differences in the third panel, we can see actually the model differences are kind of also important in the high latitude oceans and also over parts of the land surface. And finally, when we look at the percentage of the variance due to model differences, you can see that model differences no longer dominate everywhere. And so this means that the uncertainty due to internal variability is actually more important, particularly in the extratropics, for temporal temperature variability projections. Okay. And we can look at one more variable, which is temporal precipitation variability. You can see here on the left-hand panels that the projections no longer completely agree between the SMILES and the atmospheric subensembles. And this is likely because we have different models in the different ensembles. Both the uncertainty due to internal variability and the uncertainty due to model differences dominate in the tropical Pacific. And we find that in the tropical Pacific, the model differences are the most important, actually in the tropics in general, in those right-hand panels. But for the rest of the globe, again, internal variability is actually more important than model differences, even on these long time scales. Okay, so let's zoom in on the tropical Pacific, as this is an area of importance due to ENSO. And here I'm just plotting temperature variability projections on the left and precipitation variability projections on the right. Each color dot, again, is an individual SMILE, and the mean is shown in black. And the error bars are due to bootstrapping, which is basically because the ensemble sizes aren't infinite. And here I show the projections for the full Pacific, the far West Pacific, the West Pacific, the East Pacific, and the Central Pacific. And the point I'd like to make here is that for temperature variability, which is related to ENSO, we still don't really understand even the sign of the change, let alone the magnitude in our projections. When you look at precipitation variability on the right, you can see there's some model agreement in the East and Central Pacific with all but one SMILE showing a projected increase in precipitation variability, although the magnitudes can widely differ. And in the far Western Pacific and the kind of Western Pacific, the projections don't even agree on the sign of the change. Okay, so what have we found? We've found that grouping CMIP models that share an atmospheric component can give you a reasonable estimate of the SMILE results, particularly of which uncertainty, model differences, or internal variability is more important. Model-to-model differences are larger than internal variability globally for temperature and precipitation mean state projections. But for both temporal temperature and precipitation variability, the internal variability can be much larger than model differences, and it is in the extratropics. And we still find large amounts of model disagreement in projections of temporal variability in the tropical Pacific, particularly for temperature. Okay, so what does this mean? Perhaps for this audience, I don't really need to say this, but smiles are a powerful tool for quantifying internal variability and investigating model-to-model agreement. Interestingly, when we find that model differences dominate, theoretically, we could perhaps decrease our projections due to a better understanding of the Earth system. But where internal variability is larger, such for those temporal temperature and precipitation variability projections, improving our models may not actually decrease the spread of projections. And we find really that more work is needed in the tropical Pacific. And I'd just like to point out one last thing, that just because the models agree on the sign of the change, it does not mean they'll agree on the magnitude. And this may seem obvious, but it's something that we can really look at using these smiles. So I'd like to just finish by using my last 2 minutes to present what am I doing now and where am I, which is I've now a series postdoc at CU Boulder working with Antoinetta Capotondi and Jennifer Kay. And I'm looking at how Pacific decadal variability modulates ENSO teleconnections in these smiles. And I'd just like to show you one preliminary plot here, which shows 4 different smiles that have a fairly good representation of the tropical Pacific. And I'm showing ENSO teleconnections over North America. And so the top panel shows ENSO teleconnections for El Nino when the PDO is neutral. The second panel shows, or the second row shows the differences between that top row and when El Nino is in a positive, when you have an El Nino in a positive PDO. And then the third panel shows the same, but for a PDO negative state. And then the bottom 3 sets of panels show the same results, but for La Niñas. And I just want to point out 2 things here. First is that we see a really large modulation of the ENSO teleconnections by the PDO over North America. And we see quite a lot of model agreement on that, although there are kind of local differences. And so if anyone's interested in talking to me later about this new topic, that'd be cool. Thanks.
Thanks. Any questions for Nicola? I guess I had a couple of questions. I'll give people a chance to raise their hands and post theirs in the chat. The last slide you showed, those were anomalies relative to just all climatology or relative to that particular ENSO events in that particular?
Yeah.
I guess my question is the PDO influence in there, or is there kind of non-linearity and that ENSO response is actually different?
So I think it's the ENSO response is actually different because we've tried to basically do composites of when the PDO is in specific phases. And so it looks a little bit like the temperatures in the tropical Pacific aren't actually changing to cause these changing teleconnections, but the response of the precipitation is really different. And so this is kind of preliminary and I'm still looking into it.
Okay, interesting. Any more questions? I had one about your main piece of work for the temperature variability in Europe. I think this is a place where in the winter it's projected to decrease and in the summer it's projected to increase. And so what was the rationale for looking at the annual mean, and do you find different results and more kind of less of a role for internal variability, I guess, if you look at the winter itself or the summer itself?
Yeah, that's a really good point. We mostly just wanted to test the method, and the paper got way too big with just annual means, but I'm currently looking with a collaborator into the summer and the winter and whether you get kind of different results in that case. So we haven't done it yet, but that's the plan.
Cool. And Katie?
Yeah, thanks for the interesting talk. I was thinking more about the model sharing components, and maybe this is also another potential extension, but did you look at all at models, like I guess within the SMILE models, are there models that share components? And then also, does it make sense to group models together that might share land or ocean components? How might that change the results.
Yeah, thanks. So some of the SMILES do share components. There's 2 GFDL models that are pretty similar, but interestingly, they tend to have completely opposite responses. So we decided we could use them both because while they might share a component, they don't really behave very similarly. Otherwise, the SMILES tend to be fairly independent. We also did test our results by grouping the land, sorry, not the land, the ocean, and we get similar results by using an ocean grouping. I guess that's, yeah, I guess that kind of makes sense. And maybe some models that share an atmosphere also share an ocean, so it's not completely independent either. So,
thanks.
It seems like maybe CMIP6 would be an opportunity to test things a bit more, since many of the models have many more members. You could, yeah, see if you get the same results as if you take the ensemble mean. I mean, it's the same as what you did with the large ensembles, but with more models probably.
Yeah, that might be a good idea. And I think this could be easily applied to CMIP6, and it might be a nice way to try and do this without having to run CMIP6 large ensembles for all the models.
Yeah. Okay, well, any more questions? We're a little ahead of schedule, but I guess that's fine. All right, thanks, Nicola. We'll go on to Haiyan now, I think, yes. We'll be talking about accelerated warming in the Northern Hemisphere mid-latitudes in summer since the 90s.
Hello, can you hear me?
Yep.
Can you see my screen?
Yes.
Okay. First, I want to acknowledge my co-authors, Ruby Liang, Grant Brandstater, Jian Lu, Qinghua Ding, and the project that supports this study. And this talk is really about how we should how to understand the JJA summertime trends from 79 to 2020 or during the satellite era. So the top panel shows the surface air temperature trend, and the bottom panel shows the geopotential height anomaly, geopotential height at 200 hectopascal trend. And so this is contrary to the winter warming that has manifested as polar amplification. The summer warming is mostly concentrated at several regions in the mid-latitude overland, Europe, Mongolia, west coast of North America, west of Greenland, and Africa. And these hotspots are co-located at center of action, five centers of action of geopotential height anomalies, these high pressure ridges. And there's another center of action west of Greenland in the mid-latitude. And this wave number 5 circumglobal wave train, similar wave train has appeared frequently during extreme events in recent decades. Here I use these yellow dots to highlight these 5 centers. And in these 3 panels, they are 3 monthly anomalies of Z200. The first one, 2010 during Russian heat wave, 2017, and last September. So there are some case-to-case variation, but in general, we see lots of similarity between the trend and the individual monthly anomalies. And the warming during the last 4 decades is unprecedented, but there has been other periods in the 20th century with that has extended warming. For example, these are Hofmann diagrams of temperature anomalies averaged at 30 to 60 north. And the shading indicate 11-year average minus the previous 30-year climatology. And in the past 4 decades, the warming mostly started, the left is hot crude 4 and right is Gistan. So the warming in the past 4 decades mostly started from the 1990s. And there are other extended periods in the early to mid 20th century with large warming. For example, these red shading represents the Dust Bowl events, and the amplitude is even higher than the warming we see in the past 4 decades. Another way to look at the warming is to calculate the average in the mid-latitude of summertime surface air temperature. For comparison, I also show the global annual mean temperature on the top. In these 2 panels, the black curve and the gray shading represents the CESM 6 multi-model ensemble average and spread. The colored lines are reanalysis or instrumental records. I use the purple and orange color to highlight GISTEMP and HAT-Crew4. So contrary to the staircase warming in the global annual mean temperature, the mid-latitude warming show this V shape. And this V shape is slightly exaggerated by the CESM 6 model. In the bottom panel, I show the time series of IPO and AMV index, IPO in red and AMV in blue. And this V shape in the mid-latitude warming seem to be in phase with the evolution of AMV. For example, during the period that we're interested, from 1979 to present, in the IPO shifts from positive to negative, and AMV shifts from negative to positive both in around 1990s. In other words, the trend we are looking at can also be captured by these two, the later period, the difference between the later period minus this early period. In my study, I'm mostly interested in this 1980 to 1994. I call this period 2, and 2000 to 2014. I call this period 3. In period 2, there is positive IPO, negative AMV. Period 3, positive AMV, negative IPO. Also, there is an interesting period from 1945 to 1960 with positive AMV and a negative IPO. As I said, the trends in the past 4 decades can be represented by the difference between period 3 and period 2. This is temperature, and this is Z200. And on the top, I show the difference between the period 1 and period 2. Although the anomalies in the later, in the bottom panel have higher amplitudes, but if you compare the patterns, there is some resemblance, suggesting the trends that we looked at, the multi-decadal trend, is kind of tied to multi-decadal variability. So the question is, how much does the trend is the trend caused by climate change, and how much caused by multi-decadal variability? And to address this question, there have been many attribution studies, and but for this case, I think it is, given the low fidelity in model projected circulation trend, and also the uncertainties in IPO and AMV because of the lack of observational record, like lack of theoretical understanding, I think it is difficult to answer this question quantitatively. Instead, I want to take a storyline approach and use the available data and experiments to understand the process, and the work is, I think the analysis is like, in the following, I will show some CESM 6 experiments, but the work is not limited to these CESM 6 experiments, because I think it is also important to ask the question, what processes may be underrepresented by these models? And the first question we want to ask is, how does AMV affect the GGA temperature? here I'm showing the JJATS regress to AMV from the 15 CMIP6 per-industrial control runs. And on the top left, I show the gas temperature regress to the observed AMV. But I want to emphasize, we don't want to use this as a benchmark because there's only 1 to 2 events in nature, and there is big sampling issue. And for the CMIP6 models, well, the good news is, yes, indeed, AMV can have a strong impact on the mid-latitude summer temperature. We see mostly red color in these plots. But the bad news is there are large model-to-model variations. And this is partly caused by that the SST anomalies regressed associated with AMV has large model variations. In some models, for example, CESM2, the different CESM2, there are some warm SST anomalies in the tropical Pacific, but this is not always true. There are some other models that do not show this warm anomalies as well as in the Alps. We can also ask how the negative IPO can affect the mid-latitude temperature. The good news is the models tend to have better agreement in the IPO pattern. This is the SST regress to the IPO index. But when we look at the JJATS regress to the negative IPO, we see lots of blue colors. And if we calculate the 30 to 60 north domain average, there's really no robust connection between negative IPO or IPO and GGA surface air temperature. And my first impression of this plot is the IPO tend to have we tend to have better, the model seems to have better agreement on the IPO's impact on the JJ surface air temperature in terms of the large scale pattern. But if you look at the Eurasia continent very carefully, there's still large model to model disagreement. The second question we want to ask is, how does the CMIP6 model simulate the difference between period 3 and period 2? This is the Z200 anomalies. The top panel shows the INCEP inquiry analysis and the ERE5. The middle panel left is from the historical run, right from the AMIP run. And the shading shows the 15 model ensemble average, and the blue dots are local maximum from each model. So the models tend to overestimate the anomalies. In addition, the historical runs, there's not a clear preference of the local maximum, but we clearly see these 5 local maximum in the AMIP run when we compare this plot with the observation. So this means the SST plays an important role in forcing this wave train. In the bottom panel, I made 2 kinds of composite using the per-industrial control run. The left one is composite for positive AMV and a negative IPO. And in the right, I show this is a composite based on about 224-year segments with similar Z200 trend at 20 to 70. So by definition, this pattern should resemble the observed, but the amplitude I find from the pre-industrial control run is so weak that I have to multiply the composite by 6 in order to make it comparable to the observation. But when you look at these patterns, you think, okay, the AMIP run and the pre-industrial control run, these 2 panels, they both resemble the observed pattern. So the SST anomalies that may help to organize this wave pattern, the information is mainly carried by the positive AMV and negative IPO. This is the plot for surface air temperature. Again, top for the observed, the middle panel for historical run and EMIP run. And again, the models overestimate the warming. And this is the composite for positive AMV and negative IPO. And we really don't see a good agreement between this one and this observed. And only after we really kind of nudge the circulation to make it similar to the observed trend, we can finally get these hotspots at the correct places. As I mentioned, the pre-industrial control run really cannot produce big enough 42-year trend as comparable with the observed. And this plot compares the PDV, the PDF of the pre-industrial control runs trend from 15 different models in 15 different colors at the 6 centers of actions. And the vertical lines, they represent the observed trend. The top row is for 200 geopotential height, and bottom row for TAS. So this is a very typical diagram we use for attribution study. And the first impression you may get from this kind of plot is, okay, there's no way to produce such strong multi-decadal trend without anthropogenic forcing. But you may also ask this question, could there be processes underrepresented in the model and that cause such big discrepancy between the model and observed trend? So the 2 processes I want to talk about next. The first one is eddy-mean flow interaction. And I want to ask, how does synoptic eddy respond to slowly varying SST boundary condition? The reason I think this process is important is because eddy-mean flow interaction plays a key role in forming this circumglobal wave train. This, to demonstrate this, I run the linear planetary wave model that Grant developed, and I prescribed UV temperature of the climatology during the 42-year period. Then I diagnosed the synoptic eddy forcing difference from the change in synoptic eddy forcing from period 2 to period 3. Then I forced this linear model with this synoptic eddy forcing. And the second row shows the model response to the synoptic eddy forcing. So it can reproduce, roughly reproduce the observed circulation trend. Then I can further play with the synoptic eddy forcing, and I force the synoptic eddy forcing only in the North Atlantic region and in the North Pacific region. And these, the panel C and D correspond to the response I get. So I find this response to synoptic eddy mainly can be mostly explained by synoptic eddy forcing in the North Atlantic, because lots of us tend to think about mid-latitude circulation change is driven by tropical forcing. So in the bottom panel, I forced the model with the diabatic heating anomalies derived from the precipitation change, and the response is shown in panel E. So this is much weaker, makes the tropical forcing makes much smaller contribution to this wave train compared to the synoptic eddy forcing in the North Atlantic. And the second process I think we are not certain about is atmosphere-land interaction. For example, what role does atmosphere-land feedback play in this Z200 trend during the last 42 years or during the life cycle of AMV? And I think many of the audience remember I did some prescribed soil moisture experiments 3 years ago. And this bottom two panels show the response to prescribed soil water or soil water depletion in North Europe and the West Coast. So I just want to show you, I am amazed that this circulation response in the bottom panel looks very similar to the circulation trend from the observed. Although this is highly idealized experiments, this experiment suggests atmosphere-land interaction can provide a mechanism to amplify the circulation response and possibly during the life cycle of AMV. To summarize, so I think this study is about how to understand the trends in the last 42 years, and it is connected to AMV and IPO, especially the phase shift of AMV in the 1990s can accelerate the warming in the mid-latitude. And I also really like the storyline approach that encourages us to understand the process rather than just giving a probability, a number. And with this approach, I want to show you that synoptic eddy mean flow feedback and atmosphere-land interaction may influence the multi-decadal trend, and it may play a big role in forming the observed trend in the past 42 years. Thank you.
Thanks, Clara.
Yeah, thanks. Hi, Anne. That was just such a wonderful, interesting study. So I'm just wondering about, this whether models are deficient in their strength of these 42-year trends in the control runs. Do you think that relates to deficiencies in the amplitude of AMV, or do you think it relates to the maybe weaker than observed synoptic eddy mean flow feedbacks? I know Doug Smith and Adam Scaife maybe have begun to point to that as a shortcoming for the NAO. So I just wondered your thoughts on why the models might be so weak.
Yeah, nice question, Clara. And remember at the beginning of the year, you presented at the CAS meeting for the AMV comparison, and I really like the talk. But this plot shows the SST regress to AMV, and this is the Heidi SST, and others are the models. So if you look at the amplitude, you really don't see a big underrepresentation in the models in SST anomalies. But the problem is, I think, the circulation. It's the circulation. The circulation just doesn't respond to the AMV strong enough. Like you mentioned, Doug's paper and Adam's paper about the NAO. This is like paradox problem. The models just don't simulate the NAO trend. And for the summertime, we haven't really paid attention to the summertime circulation trend. I am thinking this wave trend is like the summer is a big either climate change or multi-decadal variability signal in the circulation, and this could be caused by this is just the models don't react strongly enough to the SSTs.
Yeah, I just wondered if you can somehow play with your planetary wave model and take the strength of the eddy mean flow couple of models and on the observed basis.
Yes, I get your point here. I am forcing the model with observed the synoptic eddy forcing. I actually have tried with the CESM2 control run, but the problem is the CESM2 control run does not write outputs for all the vertical layers, and so it is. But I think you're making a great point. I could I also diagnosed the CMIP6 models. Again, there are only 7 vertical layers from the CMIP6 daily outputs, so this kind of limited my analysis.
Yeah, I think the CSM2 large ensemble, Isla can correct me if I'm wrong, but I think that we will, at least for the MOAR runs, save all the vertical or many vertical levels, not all.
Yes,
this will be.
I think this is very important, and as I think also we for the next step, I'm really interested in looking at how. So here I'm showing the mean circulation change, but I think it is also important to understand how synoptic eddy activity has changed in the last 40 years.
Thanks.
Yeah, I guess along similar lines, I'd wondered, and this is maybe something you could do with a limited number of levels, is could you composite the eddy forcing, do your composites based on the eddy forcing in the North Atlantic and see if somehow the models are not capturing this wave train that seems to then extend to the east.
Yes, definitely. We can definitely, I think that we can definitely, I can do that.
All right, don't see any more hands raised. So we'll move to our, thanks Hayam, we'll move to our final speaker of this session. That's Dave Schneider. He's going to tell us about cloud and albedo feedbacks, how they're shaping 21st century warming patterns.
All right, hi Isla, can you hear me?
Yep.
Okay, great. And can you see my first slide now?
It's not full screen. Oh yeah, it is now.
It is now. Okay, good.
Yep.
So yeah, thanks everyone for being here, and thanks for the opportunity to speak today. So this work is a product of a relatively recent joint appointment and collaboration that I've set up at the University of Colorado, where I'm working with Jennifer Kay. And this work is also the product of a lot of work at NCAR. And most importantly for this talk is that Cecile Hannay has contributed a set of experiments with CESM2, which I'll describe in a moment. So if you've been following results from CMIP6 over the past year or so, you're probably well aware that a number of the CMIP6 models have a high climate sensitivity. And in this graph, the models are ordered by their climate sensitivity. And CESM2 is one of those models with a sensitivity of about 5.2 degrees Kelvin. And last year, Gavin Schmidt started tweeting about CMIP6 and climate sensitivity. And this graph labeled these high sensitivity models as the wolf pack, where the rest of the models were in the pack. These have moderate climate sensitivity. And then there's a couple of Russian models, which are outliers with low climate sensitivity. And Mark Zelinka has both tweeted and published a number of papers about the climate sensitivity in CMIP6 models. And one of the main results from his work is that the high climate sensitivity models tend to have a very strong and positive shortwave cloud feedback, especially with low clouds in the mid-latitudes of the Southern Hemisphere. And so we have the wolf pack, and then here is a close-up of CSM2 as a wolf. And then these red models are in the pack. So these are merely dots, and I'm waiting for the slide to go ahead. There we go. Okay, so that's CESM2 in the context of CMIP6. You may be less familiar with the fact that a few years ago, even before the CESM2 was released and before the other CMIP6 models were released, we had a version of CESM1, which had high climate sensitivity. This version was produced by Jen K. And the reason this came about is that people were concerned with a large bias in observed shortwave radiation over the Southern Ocean. And she made a few tweaks to the model to reduce this bias. And you can see that bias reduction here on this plot. This is for the Southern Hemisphere summer. So the bias had been something on the order of 30 to 40 watts per meter squared. It's a really huge bias. And that was reduced by quite a significant amount. And the reason this bias reduction came about, it was that what changed in the clouds was that the new clouds have more cloud liquid relative to their cloud ice amount. So these more liquid clouds are more reflective, reflect more sunlight, and that leads to this reduction in the absorbed shortwave radiation over the Southern Ocean. And this also really changed the climate sensitivity by changing the cloud feedbacks. And how that came about is described in this paper. So there were two main changes to the shortwave cloud feedbacks. So the first mechanism is the cloud phase feedback, which is probably a more intuitive mechanism. So as climate warms, the ice cloud converts to liquid cloud. And so if you start with more liquid in the first place, then you get less conversion of cloud ice to cloud liquid. And the second important shortwave cloud feedback is the amount effect, which is driven by changes in the vertical moisture gradient, especially in the lower latitudes. And that changes in a way that allows more dry air from the troposphere to mix down into the boundary layer, and that reduces the cloud amount. So both of these mechanisms are at play in increasing the climate sensitivity in this model. And so we call this modified version of CSM1 cloud mod. Sorry, my slides are lagging just a little bit here. I have a little bit of a frozen PowerPoint.
Does Elizabeth have your talk? I guess that would be an option for her to share it. Or do you think it's going to unfreeze?
Oh, wait, there we go. Okay.
Oh, okay.
So we moved on, thankfully. So with this modified version of the model, they asked this question, do these Southern Ocean cloud feedbacks matter for 21st century warming? And the answer was kind of sort of. The experiment with cloud mod for the 21st century produced a little bit more warming, but it wasn't clearly outside of the large ensemble. And it's shown here that this model had a stronger positive shortwave cloud feedback in the Southern Ocean. And important for this talk is that this is the only place in the globe where the shortwave cloud feedback really changed significantly. Over the rest of the globe, the feedback hardly changed from what you see in the large ensemble. So we're going to look at climate projections in 3 models with different climate sensitivity and cloud feedback. And we're using the same forcing for all 3 models. We have historical forcing through 2005, and then the RCP for 2006 to 2100. And for most of these results, I'll be looking at the ensemble mean or the force response, comparing the end of the 21st century to the beginning. And so in this framework, if CSM2 is a wolf, then CSM1 is just a dog. So this kind of golden retriever dog is very reliable and friendly and generally responds in the expected manner to forcing, but it doesn't have like the strength and the capabilities of CSM2. So where in the spectrum between the dog and the wolf does CloudMod lie? And I think if Gavin Schmidt were classifying models into dogs and wolf based on climate sensitivity, he would put this CloudMod into the wolf category. However, as we look at climate projections and how the CloudMod responds to forcing over the 21st century, it behaves a lot more like a dog. So I'm going to call it a dog with wolf-like characteristics, or this kind of German Shepherd. So these are the questions we're asking here. So we're repeating this question, but using larger ensemble size. And then we're looking more broadly at the spatial patterns of warming in the 21st century and how they differ among these three models. And we'll look at the role of radiative feedbacks in shaping these warming patterns. And we realized through the course of this work that we have to look beyond the Southern Ocean, and we have to look at beyond the shortwave cloud feedbacks at the whole suite of radiative feedbacks to really understand these warming patterns. So we'll use large ensemble as kind of a canonical warming pattern where you see enhanced warming at the high latitudes in the Northern Hemisphere and less warming over the oceans and less warming in the Southern Hemisphere. If you look at the other two models, they generally have the same gross features with amplified warming in the Northern Hemisphere, but you start to see some differences. So in CloudMod, you see a little bit more warming over the Southern Ocean, and in CSM2, you see more warming really across the whole globe. And you can see that the main differences highlighted here. So CloudMod minus lens is a more uniform difference. It's going to a little bit warmer everywhere with a few hot spots. Whereas CSM2 minus lens or CSM2 minus CloudMod has quite a rich structure. So there's especially more warming in the tropics and the subtropics, especially in the Southern Hemisphere, and more warming over Antarctica. And zonally average here difference, the largest differences are about 15 to 20 south, and then again over the Antarctic continent. And at the highest latitudes of the Northern Hemisphere, there's actually less warming in CSM2 than there is in CSM1. So to kind of understand when and where these warming patterns emerged, we have a couple of time series, and I've broken up the globe into 4 equal area parts. Where first for 30 to 90 north, you see the 3 ensembles evolve, and they're pretty much the same until late in the century at these latitudes. And so by the end of the century, you only have a little bit more warming in CSM2 than you do in both of the CSM1 models. For 0 to 30 north, the ensembles are much more separated. So there's about a 1.3 degree Kelvin difference in the warming at these latitudes. And the CSM2 kind of starts to break away from the CSM1 ensembles somewhere in the 2050 to 2060 timeframe. Sorry, now we're having the same issue again. Okay. Okay. And then in the Southern Hemisphere, at 0 to 30 south, there's even a bigger difference. So there's about a 1.4 degree difference by the end of the century between the CSM2 ensemble and the CSM1 ensemble. And then in the Antarctic and over the Southern Ocean, again, kind of like in the Arctic, the differences are pretty small, only about 0.7 degrees Kelvin by the end of the century. So the major differences between the ensembles are really coming from the low latitudes. And so that means that amplification is weaker in CSM2. So the amplification is simply the ratio of the zonal mean warming to the global warming. And you can see that both CSM1 models have similar amplification profile, whereas CSM2 has relatively more warming in these low latitudes and less warming in the high latitudes of the Northern Hemisphere. We can look into vertical. So again, the gross features are kind of the same with this sort of amplification profile near the surface, but you can see more warming everywhere in CSM2 than in CSM1. And it's kind of shifted towards these low latitudes in the Southern Hemisphere, and especially the biggest differences near the surface are at like 15 to 20 degrees south. So we're going to do some feedback calculations. Just to be thorough, we're going to use two different methods. The APRP is applied to shortwave feedbacks, and the radiated kernel method is applied to both shortwave and longwave feedbacks. And just a caveat with the results I'm about to show is that so far we only have results for one ensemble member for the kernel method. So I think qualitatively the results are robust, but quantitatively they might change a little bit once we do the full ensemble. So the shortwave cloud feedback from the two methods, you can see CSM1 in black and then CloudMod in red. And so again, similar to that Frey et al. Paper I showed, the biggest difference between CSM1 CloudMod and the lens is right here in the Southern Hemisphere, where this feedback is more positive, and there's good agreement on this between the two methods. In CSM2, by contrast, the positive feedback really kind of shifts in latitude towards the equator. And at the same time, kind of the negative feedback also shifts. And so there's a little bit difference to this depending on the method, but the large scale patterns are the same between the two methods. So if you look globally integrated values, the shortwave cloud feedback is stronger in CloudMod and in CSM2, but it doesn't appear to be much stronger, if at all stronger, in CSM2 compared to CloudMod. In map view, you can see a little bit more about where these feedbacks are occurring. So again, in CloudMod, there's stronger feedbacks over the Southern Ocean, and in CSM2, there's also stronger feedbacks over the Southern Ocean, but they're shifted a bit to the north. And then you see these strong feedbacks in the subtropics. So difference maps, again, give you kind of this rich structure between CSM2 and CSM1, whereas CloudMod versus lens is a much simpler structure owing to the more positive feedback in the Southern Hemisphere mid-latitudes. We've also done long wave feedbacks, and in the long wave, the most important differences are in the long wave cloud feedback. Here in the tropics, CSM2 gives a stronger, more positive long wave cloud feedback. There's some differences in the water vapor and lapse rate feedbacks, but they tend to offset each other. So for example, when there's a little bit more positive water vapor feedback, you tend to get a little bit more negative lapse rate feedback. So the most important difference is in the long wave cloud feedback. So from that, we can calculate a total cloud feedback using the kernel method. So in the total cloud feedback, again, you see these more positive cloud feedbacks in CSM2 in the low latitudes, where in the CloudMod, they're more positive in the mid latitudes. So overall, globally average, you get a stronger, more positive cloud feedback in CSM2 than you get in CSM1. Briefly, we have a rough estimate of the ocean heat uptake anomalies through these runs. And the important thing is that in these low latitudes where these shortwave cloud feedbacks are active, there really isn't much change in the ocean heat content anomaly through these runs. And that's true both in CSM1 and CSM2. So you do see some change in CSM2, but not much at these important latitudes of 15 to 20 south. And finally, the major feedback that I haven't mentioned so far is the surface albedo feedback. So in CSM1, both versions of CSM1, we have a pretty strong surface albedo feedback in the Northern Hemisphere. And this is much weaker in CSM2 by a couple of watts per meter squared. And so we think the primary reason for this weaker cloud feedback or weaker albedo feedback is the mean state of the sea ice between CSM2 and CSM1. So borrowing from a couple of other papers, we see that the ice is thinner in CSM2 compared to CSM1. And then as you go through the 21st century with strong forcing, CSM2 loses sea ice much quicker than CSM1. So you start to get much less ice to drive that ice albedo feedback in the first place. So in summary, we've shown again, following Frey et al. 2017, that the more positive shortwave cloud feedbacks over the Southern Ocean don't lead to much greater 21st century warming in CSM1. In CSM2, the negative cloud feedback, cloud phase and positive cloud amount feedbacks are shifted equatorwards in the Southern Hemisphere, while positive shortwave cloud feedbacks in the subtropics are enhanced. In addition, there's a more positive long wave cloud feedback in CSM2 and a weaker surface albedo feedback. And so these feedbacks, they are consistent with the shifted zonal mean profile of 21st century warming in CSM2, where there's enhanced warming in the low latitudes. And finally, we think the thin Arctic sea ice likely explains this weaker ice albedo feedback. And I didn't show the seasonal warming at 70 to 90 north, but the seasonality is consistent with sea ice playing a strong role. And finally, one dimension that I haven't gone into in this talk is kind of the temporal evolution of these patterns. And so one of the more interesting aspects is that the amplification in the Arctic is really much slower in CSM2 than it is in CSM1. So that's something we'll be looking at. So thank you. And if we have any time left, I'll take any questions.
Thanks. Yeah, we're into the break time, but if anyone has one quick question. I guess an obvious one is, which low cloud feedbacks do you think are more correct? CSM1 or CSM2?
Yeah, I think for the mid-latitude and extratropical cloud feedbacks, I think people are generally, pretty happy with the new model and how it represents those mid-latitude feedbacks, especially over the Southern Ocean. But I think my understanding, and I'm drawing on like Mark Silika's papers, is that this has kind of exposed problems in the tropics. So I think a lot of the focus, might be on these tropical cloud feedbacks, which are still pretty uncertain.
Yeah. Okay, great. Well, we should take our break. We'll come back at 2:40, so that's 16 minutes from now for the last set of talks, and then also the discussion. So thanks to all the speakers from this session, and we'll see you in a bit.
Okay, now it's 2:40, and welcome back everybody for the last session of the CWG Winter Working Group meeting. In this session, we will have 3 presentations followed up by the CVCWG updates and open discussion. The first talk will be given by Margaret Sutton. The topic is ENSO-driven suppression of interannual atmospheric variability over the United States. Margaret?
Hi, yes. Can everybody see my screen?
Yes.
Okay, great. Hi, my name is Margaret Sutton. I am a master's student at North Carolina State University. I'm working with Sarah Larson on ENSO-driven suppression on interannual atmospheric variability over North America. So the purpose of the study is to show the atmospheric circulation and terrestrial impacts due to ENSO. ENSO drives anomalous deep convection and latent heat release, which perturbs the global atmospheric circulation by Rossby wave train propagation, and shows, which is shown by the figure on the top right. The teleconvective response affects temperature and precipitation globally. This figure on the bottom right shows the atmospheric circulation during an El Nino event. These impacts can enhance the risk of natural disasters and limit natural resources. It is important to understand the climate without the presence of ENSO in order to better understand ENSO's impacts. Both the surface temperature and precipitation figures shown can be found at the Desser et al. Paper from 2018. The ENSO composite anomalies are calculated by subtracting 14 La Nina events from 18 El Nino events during the period of 1920 to 2013. The stippled regions are insignificant based on a 90% confidence interval. The surface temperature composites show warmer than average temperature in Canada and Alaska, while cooler than average temperatures along the southeastern region of the United States. The precipitation composites show wetter than average conditions in the southern regions of the United States and drier than average conditions in the northeastern and northwestern regions of the US into Canada. So there's been many statistical methods of removing ENSO. For example, ENSO is oftentimes removed through linear regression. However, ENSO contains many nonlinearities. Another method of removing ENSO is by removing the signal from the interannual frequency band. However, some studies show that ENSO potentially has a low frequency signal. Also, the assumption that the Nino 3.4 SST index is strictly an ENSO signal. However, this region can also be impacted by natural variability such as tropical instability waves and subtropical influences such as thermally coupled modes. And lastly, the assumption that all ENSO variability is encompassed within the first principal component. However, there could be a lag response to ENSO. All of these methods are nicely outlined in the Campo and Sardeshmuk paper of 2010. So in this study, the removal of ENSO is done by suppressing the dynamical process that supports ENSO variability. This process is referred to as the Berknes feedback. And this is where the positive feedback loop between the ocean and the atmosphere that reinforces the initial SST anomaly. The diagram on the right illustrates the Berknes feedback. The process is illustrated by is initialized by the trade winds and The process is initialized by the weakening of the zonal SST gradient, which weakens the Walker circulation, weakening the trade winds and reducing upwelling in the east and downwelling in the west, which further weakens the zonal SST gradient. This is an example of an El Nino process, or this is an example of the process that reinforces an El Nino event. Due to the inability to remove the influence of Berkney's feedback, and observational data, a climate model. This experiment is done using a climate model. So data is used from the NCAR CESM1 CAM4 model using present day forcing from year 2000 with 1 by 1 degree resolution. 2 experiments were used in the study. The first one being the control experiment, which simulates the Earth's climate system, and the other one being the no-ENSO experiment, where the ocean is decoupled from the anomalous wind stress in the tropical Pacific. This short circuits the Berkney's feedback and eliminates ENSO variability. The figure shown is an example of the mask applied to the no-ENSO experiment. The total wind stress the ocean feels is calculated by alpha, which is the mask, times the anomalous wind stress plus the climatological wind stress. Where the mask is white, the ocean feels all of the anomalous wind stress and acts similar to the control. Where the mask is red, the ocean does not feel any of the anomalous wind stress and the Berkney's feedback is deactivated. The anomalous wind stress is gradually reintroduced to avoid any unintended consequences. The figures on the right are the seasonal DJF SST climatology for both the control and the no-ENSO runs. As you can see, the spatial patterns are similar, showing that the mass does not strongly impact the SST climatology. For more information on this model experiment, you can see the paper by Larson and Kirkman, 2015, and Larson et al. In 2018. So the large December, January, February seasonal averages were used because the largest anomalies in the equatorial Pacific are found during these months. Anomalies from the Nino 3.4 region are used to categorize ENSO events using a plus or minus 0.5 degrees Celsius threshold. The monthly anomalies are calculated using the equation below. Notice that the no-ENSO reference is used for both the control and no-ENSO experiments. This is done due to the asymmetries found between ENSO events. El Nino is stronger than La Nina and projects onto the mean state, as shown in the figures below. The latitudinal profiles are taken from both the El Nino and La Nina 500 millibar height composites at 96 degrees west. This latitude corresponds with a large ENSO forced anomaly, or corresponds with large ENSO forced anomalies over the US. The figure on the left shows the composite anomalies using the control reference. And as you can see, the amplitudes of the anomalies are nearly symmetric, with higher anomalies in the mid and higher latitudes. On the right are the anomalies using the no-ENSO reference. There are clear asymmetries between the amplitudes and the composite anomalies. So first we looked at the SST for both runs. The figure on the right shows the DJF interannual SST variance for the control. The blue box shows the Nino 3.4 region. I'm sorry. And then the figure on the bottom right is the DJF no-ENSO run for the SST variance. And once again, the blue box is outlined. The DJF Nino 3.4 time series is shown on the left-hand side. And as you can see, the control run produces large anomalies in the Nino 3.4 index, and the no-ENSO run dampens the majority of the variability. However, there's still natural variability present. So some familiar features of SST variability are the equatorial Pacific and western boundary currents. The percent difference equation is used to compare the control and no-ENSO runs. The equation for percent difference is the control variance minus the no-ENSO variance divided by the no-ENSO variance. The goal here is to show the ENSO-driven impacts on the atmospheric circulation. The figure on the right is the SST percent difference plot. Where the figure is red, ENSO enhances variability. Where the figure is blue, ENSO suppresses variability. So as you can see, ENSO drives variability globally, particularly in the equatorial Pacific and Indian Oceans. So how does ENSO impact the atmospheric circulation? We first looked at the 500 millibar G potential height because it's considered the steering flow of the atmosphere. So interannual variance plots are produced for the control as well as the no ENSO. Once again, using the DJF months. So the main center of action in the control plot is located over the Aleutian Low, along with large variability over the United States. Similar spatial patterns are shown for the no ENSO variants as well, however, differences over the US. The percent difference plot is used to compare the differences. Like before, where the graph is red, ENSO enhances variability, where the graph is blue, ENSO suppresses variability. So ENSO enhances variability off the coast of the west coast of the United States, stretching across the North Pacific Basin and along the southern regions of the United States. Although there are many regions where ENSO has suppressed variability, we will be focusing on the largest region of suppressed variability over the United States. This is also one of the only regions that surpasses the 99% confidence interval. So when comparing the percent difference plot with the ENSO composite anomalies, with the El Nino composite anomaly on top and then the La Nina composite anomaly on the bottom, you can see that ENSO forces an anomalous dipole over the North American continent, which is reflected in the three regions of enhanced variability shown from the percent difference plot over North America. The regions of suppressed variability the region of suppressed variability is located where the ENSO-driven anomalies are 0. This is indicated by the blue arrows. So in other words, the node between the ENSO-driven anomalous dipole results in reduced variability when ENSO is included. A latitudinal profile at 96 degrees west is shown because it runs through the maximum of the suppression zone. ENSO reduces variability by about 31% at this point in the suppression. Once again, the red curve is El Nino and the blue curve is La Nina. El Nino and La Nina anomalies occur in the same regions. The center of the suppression occurs about 45 degrees north, which is outlined by the box in the latitudinal profile. At this latitude, ENSO forced anomalies are near 0. So how far does this feature go up? The zonal component of the jet level winds is used due to the zonal wind belts. The control jet level wind variance plots show larger variability in the northern hemisphere. The percent difference plot is shown on the right, and one would expect if the suppression occurs at 500 level, it would also occur at jet level. So how does the suppressed upper level atmospheric circulation impact the surface? Next, we looked at precipitation. On the right is the percent difference plot with the confidence level of 99%. And the small variance in the control run has been masked over to remove the effects of difference of small numbers. The figure on the left is the same percent difference plot, just zoomed in over the North American continent, and all insignificant values have been removed. So ENSO increased variability over the southeastern US by about 60%, and ENSO suppresses variability by more than 30% in a region south of the Great Lakes. So the suppressed region corresponds with the region of large interannual variability as shown in the control figure at the bottom. So when looking at surface temperature, the global view of the percent difference plot is shown on the right. When zooming in over the US, two regions of reduced variability are shown. However, the Central American region is due to difference of small numbers, as shown by the control variance plot. In the northern region, ENSO suppresses variability by more than 20%. And this region is located where ENSO or I'm sorry, when surface temperature variability is large. So how does the upper level suppression zones relate to the surface suppression? The shaded regions in the figures show the precipitation percent difference plot on top and surface temperature percent difference plot on the bottom. The surface, both are overlaid with the jet level winds percent difference plot. The suppressed precipitation the suppressed precipitation is to the east of the upper level suppression, and the surface temperature suppression occurs to the north of the upper level suppression. So future work would include distinguishing which phase would contribute, or which phase is contributing more to the suppressed region, and looking into the different flavors of ENSO to evaluate their contribution. So in conclusion, ENSO increases variability in the atmospheric circulation over the western and southern regions of the United States. ENSO suppresses variability in the atmospheric circulation over the northern United States. ENSO forces an anomalous dipole over the North American continent. The suppression zones are located where ENSO anomalies are 0. The atmospheric suppression has terrestrial impacts through precipitation and temperature. And with the changing climate, and ENSO events have been predicted to change in amplitude and frequency, which may impact the strength and frequency of ENSO teleconnections. Thank you so much.
Thank you. Any question? Ella.
Yeah, I think so. It was interesting. I guess I also find it quite surprising. I was wondering if you think, have you considered just looking at kind of the pre-industrial controls that we have with climatological SSTs to see if you get the same answer? Or do you think you need coupling elsewhere?
We haven't looked into that as of yet. Originally, I was using, I won't say that, but we haven't looked at pre-industrial run at all. But that would be interesting to look into.
Yeah, the data is available. So yeah, if you're interested, you can download it.
Any other question? So I do not see more hand raising, and let's move on to the next talk. Next talk will be given by Wen Kwong. The title is Southward Shift of Westerlies Intensifies the East Asian Early Summer Rain Bands Following El Niño. Wen, go ahead.
Okay, so let me, can you see my slide?
And we can see your slide, but now it's not really in the presentation mode because we can see 2 of your slides. Okay, now it's fine.
Oh, it's good.
Yes.
Okay, cool. All right, thanks, Ashley, and thanks everyone for joining the discussion. My name is Wen. I'm currently a postdoc at UCLA, working with Karen McNee and Ella, who is also on the call. Today, I'm going to present a piece of work that I did during my PhD in collaboration with my dissertation advisor, John Chang at UC Berkeley. And this work was published last year in GRL. So in this talk, I won't cover all the details reported in the paper. Instead, I will focus on walking you through the basic idea that motivated this work. Okay, so let's get started. Focusing on summers following El Niño, I'm going to tell a very simple story among 3 keywords, El Niño, Westerlies, and the East Asian Summer Rain Band. In particular, I'm going to argue that perturbations in the Westerlies during summers following El Niño can introduce a new perspective to our understanding on the teleconnection between El Niño and the East Asian Summer Rain Band. In this work, we identified ENSO events based on the DJF Oceanic Nino Index. And in order to see effects of El Nino, we use summers following El Nino minus neutral summers. And the data used in this work includes observation, reanalysis. I also use model outputs from a CESM1 fully coupled pre-industrial simulation just to increase the sampling size of the ENSO events. Okay, so let's first take a look at this satellite image from June 2016. Here, the bright shaded area indicates regions with convection and precipitation. And the striking feature of East Asia is this tilted banded rainfall structure that extends from South China to Northwestern Pacific and covers Korean Peninsula and Japan. And this is termed as the Meiyu Chaoma Baiyi rainband. In this talk, I will specifically focus on the Meiyu sector over China. During the summer, this banded rainfall structure is not static. It does not always appear at the same timing and location. In fact, the south to north migration of this rainband is the primary feature of the East Asian summer monsoon. For example, here I'm showing a Hall-Muller diagram of precipitation averaged over East China. The x-axis shows time and the y-axis shows latitude. So based on their timing and latitudes, we can break down the East Asian summer monsoon into several subseasonal stages. And the figures on the bottom are the spatial demonstrations of these rainfall stages. So as you can see, precipitation in this region experiences a south to north migration from spring to late summer. In particular, around June, the precipitation jumps from South China to Central China and forms the Meiyu. This corresponds to the rain band that we saw from that earlier satellite image. It is well known that East Asian summer rainfall tends to intensify during the summers following El Nino. For example, here I'm showing the Hall-Muller diagram of precipitation from neutral summers and anomalies during summers following El Nino from both observational analysis and CESM1 simulation. They all show enhancement of precipitation over central China in June to July during summers following El Nino. And the map view of the rainfall anomalies further show that there's a consistent enhancement of precipitation along the Meiyu rain band during the summers following El Nino. So this leads to a question: how are the effects of the El Nino conveyed to the East Asian summer rain band? Past interpretation suggests that changes in the Western Pacific subtropical high are key to the rain band intensification. In fact, there are many theories have been proposed to explain how the El Nino might affect the subtropical high. I won't go into details in this talk. These review papers by Champigny, Tim Lee, and other colleagues provide very nice summaries on that. But the central idea that guides this interpretation is the subtropical high is intensified during summers following El Nino, which enhances the moisture transport into central eastern China and enhances the Meiyu rain band. In this work, we want to offer an alternative interpretation. In particular, we want to explore the role of the westerly jet in connecting the El Nino and the East Asian summer rain band. So at this point, you may want to ask, why does the westerly jet matter? Let's go back to this slide that we saw earlier. Remember, we saw that precipitation in this region experienced a northward migration from spring to late summer. If we zoom out and look at the larger Eurasian continent, two interesting features stand out. First, there's a massive topography Tibetan plateau on the continent. Second, similar to the precipitation, the westerly jet impinging on the Tibetan plateau also experienced a south to north seasonal transition from spring to summer. So this synchronous relationship between the jet shift and seasonal rainfall transition has motivated me and my colleagues to explore the jet transition hypothesis proposed by Chang et al. In 2015. The central message of this hypothesis goes like this. Timing and the latitudes of the westerly jet impinging on the Tibetan plateau control the seasonal transition of the East Asian summer rainfall stages. And we have tested this hypothesis across a wide range of scenarios. In the next few slides, I will briefly introduce what we learned from our recent work on the May determination and what that can teach us to understand El Niño's impacts on the East Asian summer rain band intensification. So first, I want to point out that the East Asian summer rain band is essentially a large-scale frontal system. The meridional convergence between the warm, moist southerlies and cold, dry northerlies is crucial for its formation and maintenance. So intuitively, you would expect a strong convergence leads to strong rain band, and when the convergence disappears, the rain band disappears. And this is exactly where the effects of the westerly jet come in. The existence of the band plateau and its mechanical forcing on the westerly jet can modulate the orographic downstream northerlies. In particular, cyclonic circulation tends to appear downstream of large-scale topography like Tibetan Plateau. And this topographic forcing can be manifested as strong northerlies downstream of Tibetan Plateau as the jet impinges over the plateau. When the jet shifts away from the plateau, we lose that mechanical forcing. Therefore, the orographic downstream northerlies become much weaker, and we lose that strong convergence between the northerlies and southerlies. Therefore, you lose the rain band structure. So in summary, the East Asian summer rain band is closely related to the interaction between the westerly jet and the Tibetan Plateau. So based on that, we can make this very simple prediction. We would expect to see an intensification of the East Asian summer rain band when there's a southward displacement of jet that leads the jet impinges over the plateau for longer, and we would expect to see a weakening or even disappearance of the rain band when there's a northward displacement of jet that leads the jet to locate away from the plateau. So now going back to our storyline, let's take a look. How do the westerlies behave in summers following El Niño? Previous work had found that El Niño can lead to uniform tropical tropospheric warming, as shown in this example following the 1997-98 El Niño event. And it has also been shown that there's an equatorward intensification of subtropical jet following El Niño. In our work, we also saw very uniform tropical tropospheric warming from both observational analysis and the CESM1 simulation. And here we argue that this warming in the tropical troposphere strengthens the temperature gradient between the tropics and the subtropics and leads to a southward shift of westerlies. And we think this southward shift of westerlies intensify the East Asian summer rain band by inducing strong orographic downstream northerlies. And we do see these processes in our analysis. For example, both the observation and the model simulation suggest a southward displacement of westerly jet during summers following El Niño. And this gives us a quite pronounced strengthening of the northerly wind downstream of the plateau as well. And we think this is a primary reason why we get the rain band intensification during the summers following El Niño in this region. I also want to point out that this perspective has some implications for predicting future changes in the East Asian summer rain band. That's because the effects of the El Niño can be viewed as an analog of how the East Asian summer rain band respond to future warming. This might sound counterintuitive because we would expect a poleward shift of westerly jet under future warming, but at least two studies found that the boreal summer over Asia under future warming behaves similar to the summers following El Niño. For example, compared to the 21st century, the East Asian summer rain band is intensified around late 21st century, as shown in this blue blob. And this is especially pronounced in early summer during June. And similar to what we saw from summers following El Niño, there's a southward displacement of westerly jet around end of 21st century, as shown in this red color shading. The air temperature anomalies also show pronounced tropospheric warming around the end of the 21st century. And we did some idealized simulations, which further suggest that this southward jet shift is closely related to the tropospheric warming, which is induced by the SST warming. Similarly, Zhou et al. Found that the eastern equatorial Pacific warming is very crucial for the zonally coherent southward shift of a jet over Asia under global warming. And they also tied the early summer rain band intensification to this southward jet shift. So to wrap up, there are three take-home points from my talk. And this is, we think, what happens during the summers following El Nino. The tropospheric warming in summer following El Nino enhances the subtropical jet impinging on the Tibetan Plateau. And this strengthens the mechanical forcing of the Tibetan Plateau on the westerly jet and induce a strong northerly wind downstream, which enhance the meridional convergence and intensifies the East Asian summer rain band. And we think this mechanism has some implication for our understanding of how the East Asian summer rain band change in the future. Finally, I want to finish with this slide that we saw before, and I want to emphasize that the perturbations in the latitude of westerlies impinging on the Tibetan Plateau can be viewed as a very useful predictor for how East Asian summer rainfall respond to different forcings. And the work I'm presenting here is just one of those examples that can demonstrate the predictive power of the jet transition hypothesis. Yeah, so that's all. I will stop here and I'm happy to take any questions.
Thank you. And any question? I have a question I want to ask you is, what is the influence of ENSO or El Nino on this jet north-southward movement? Is there any interaction between these two?
You mean how the El Nino affect the seasonal transition of the jet?
That's right.
Okay, so so based on our analysis, I think so first of all, I'm focusing on the summers following El Nino, so not the concurrent year. So if we just talk about summers following El Nino, so my experience from this analysis is that that will delay the seasonal transition of the jet. As we saw here, we see a kind of the jet linger around over the Tibetan Plateau for longer during the summers following El Nino. And I think, so I haven't done too much further analysis along this line, but I think this is closely related to the magnitude of the of the El Nino events. So if you consider two scenarios, one is a very weak El Nino event, the other is a strong El Nino event, then the strong El Nino event would lead to a stronger tropospheric warming, and that will makes this delayed seasonal transition even stronger.
Great, thanks. Any other question?
Young-O has his hand up there.
Yeah.
Yes. Very nice talk. So
thanks.
I wonder if there's any interaction or dynamical feedback between the jet response to ENSO and the Western Pacific high intensification.
That's a very good question. My short answer is I don't know, but so as I mentioned earlier, many past studies have been focusing on using the intensification of Western Pacific subtropical high as an explanation of this rain band intensification. And as we saw from this study, that is probably not the whole story. At least from this jet perspective, you can see the mechanical forcing of the Tibetan Plateau induced downstream northerly could also play a role. But does that mean that Western Pacific subtropical high is not playing a role at all? I don't think so. So I think further work is needed to understand how to reconcile these two views. One is the jet transition view, the other is the intensification of the Western Pacific subtropical high. And also, maybe you already mentioned this, there are probably some causality between these two systems.
Thank you.
Any other question? No? Okay. We move ahead, and the next presentation will be given by Zoe Gillett. The topic is the role of the Southern Hemisphere subtropical jet for tropical, extratropical teleconnections. Zoe?
Okay, thank you. Yep. Okay, thank you. Hello. Can you see my slides? Okay.
Yes.
So thanks for having me today. I'm a PhD student working at Monash University in Australia with Harry Hendon and Julie Arblaster. And so today I'm going to be presenting a part of my PhD project that's trying to understand how teleconnections can occur during austral winter in the presence of the subtropical jet. And so these are teleconnections from the Indian Ocean, I should say. So first I'll start by motivating this work by discussing some studies that have looked at the impact of the Indian Ocean dipole teleconnection on Southern Hemisphere weather and climate. So in 2019, there were several studies that looked at how the record negative IOD in spring 2016 was linked to the record low Antarctic sea ice extent in the same season. And so this plot here, taken from Wang et al., shows in the top panel the anomalous stream function, so the anomalous Rossby wave train associated with convective heating in the eastern Indian Ocean. And so we clearly see this poleward and eastward propagating wave train from the eastern Indian Ocean towards Antarctica. And the changes in the circulation associated with this Rossby wave train were closely tied to the changes in Antarctic sea ice. A recent commentary looking at the drivers of the recent drought in southeastern Australia suggested that it's actually the absence of negative IOD events as well as La Nina events that are the cause of this drought, because it is these phases of these modes of climate variability that bring drought-breaking rains. And a recent study showed that extreme positive IOD events have already become more frequent, and this is expected to continue with clear implications for, say, drought in Australia. And finally, recent studies also shown that teleconnections from the Indian Ocean are important for Australian spring heat extremes, but these are often poorly simulated because Pacific Ocean teleconnections dominate over those from the Indian Ocean. So these studies provide sort of a good reason to sort of develop a better understanding of the teleconnection from the Indian Ocean. So firstly, I'll start just by reviewing what this teleconnection looks like. So these plots here show the observed IOD teleconnection in austral winter in JRA 55. And so these are showing regressions for the negative IOD. So what we see in the top panel, the shading is outgoing long wave radiation. So during the negative IOD, we have enhanced convection in the eastern Indian Ocean. This drives strong divergent outflow towards the southern hemisphere subtropics, shown by the vectors. And this then establishes a Rossby wave source when this divergent outflow encounters a large gradient in absolute vorticity. And then this Rossby wave drives a poleward and eastward propagating wave train, as you can see in this bottom panel, which is showing the anomalous geopotential height at 250 hectopascal. And the wave activity flux is shown by the vectors here. So tracing this wave propagation shows that it's propagating from the eastern Indian Ocean. This wave train seems to sort of split to the south of Australia and across New Zealand before sort of rejoining and then arcing back up towards the subtropics. And so this teleconnection here is summarized in this schematic from a 2011 paper. And so nicely shows this Rossby wave train from the Eastern Indian Ocean, which appears to propagate continuously. But it's sort of unclear to understand how this wave train is able to propagate continuously during winter because of the structure of the winds during the season. And so that's shown here, the 250 hectopascal zonal wind in June, July, August. And we can see at Australian longitudes, we have a strong subtropical jet at about 30 degrees south, as well as an eddy-driven jet slightly more poleward. And so the presence of the subtropical jet has a strong impact on wave propagation during winter because the strong anticyclonic shear that exists on its poleward flank creates a sort of a barrier to Rossby wave propagation. And that's shown here in this plot, these plots that show the total stationary Rossby wave number. So they're essentially showing what wave numbers can propagate in which regions. So we see a clear preference for waves to propagate along the subtropical jet, as well as the waveguide associated with the eddy-driven jet. But what's important here is that the white shading is showing where Rossby waves are unable to propagate. So that's in the tropics where there are easterlies, and on the poleward flank of the subtropical jet where the meridional gradient of absolute vorticity goes to 0. So looking at this sort of reflecting surface and comparing it to this apparent continuous Rossby wave train in the upper levels, it's hard to sort of understand how this is able to come to be. But a key point here is that this region is very shallow, and we only have this barrier in the southern hemisphere mid-latitudes in the upper troposphere. So by about 350 to 400 hectopascals, it disappears and is certainly gone by the lower troposphere. So to get a better understanding of what's happening here, I've designed idealized convective heating experiments in CAM5. So in these experiments, I force the model, I add a convective heating anomaly in the Eastern Indian Ocean with maximum amplitude of 5 Kelvin per day at the center of this ellipse, while in the vertical it obtains this maximum amplitude at about 500 hectopascal and decays towards the boundaries. And so I'm interested in understanding how this teleconnection develops, sort of on the daily evolution. So to do that, I have a large ensemble. So I created a 30-member control ensemble using observed present-day SSTs. And then at the beginning of June, July, and August, for each of those members, I imposed the heating continuously throughout the run and ran for 1 month. And then combined each June, July, and August from all the members to make a 90-member ensemble. And so this plot here is showing the evolution of this teleconnection from the Eastern Indian Ocean at 250 hectopascal. And so these are the geopotential height anomalies, the difference between the experiment and control. So what we can see here, sort of day one, the response, direct response to heating in the tropics starts to emerge, and then it starts to propagate towards the subtropics. And over the course of the first week, and we see the development of the equatorial Kelvin wave. But what's sort of important here is that there seems to be 2 parts or 2 phases to this response. So firstly, what we see in the first week, so it's clear on sort of day 5 or day 7, is this strong response in the subtropics that is confined to the waveguide of the subtropical jet. And this signal is able to rapidly get out to the Pacific Ocean because of the stronger group propagation of the waves in this region. And then it's really not until the second week that the response starts to emerge in the mid to high latitudes. And it's sort of nicely summarized in this final panel, which shows the mean over the final 2 weeks of the integration, where these sort of 2 wave trains, the subtropical and the mid high latitude wave trains combine, and we end up getting something looking quite similar to the observed wave train. So wave train observed propagating from the Eastern Indian Ocean arcing poleward and eastward south of Australia towards Antarctica. But again, just looking at this single level and knowing that waves shouldn't be able to propagate south of Australia, it's still sort of unclear how this wave train can exist. So to get a bit more insight, we've looked at what's happening in the lower troposphere. So this shows the same thing as the previous slide, but this is at 750 hectopascal. So what we see are some common features, that the response in the tropics and subtropics is strongly baroclinic. So here we have an anticyclone compared to the anticyclone above. But importantly, it's this poleward wave train is equivalent barotropic. And so it's only the equivalent barotropic part of the response that is able to get out of the tropics. And that is because by the time we get to 750, and certainly, as I said, below, sort of anywhere below 400 hectopascals, that barrier to Rossby wave propagation is removed. So what we're sort of arguing here is that this wave train is able to go underneath this apparent barrier to Rossby wave propagation and then re-emerge on the poleward side. And it's sort of nicely summarized in these latitude height cross sections, which should trace the ray as it moves poleward and eastward. So I've divided these plots into sort of 3 latitude bands, and each of these are at a different longitude to capture the high, low, high pattern that we observed before. So what sort of, the thick black contour shows the 0 contour of beta star less than 0, so that barrier to Rossby wave propagation. So what we can see here is that the subtropical part is confined to the upper troposphere, but the mid to high latitude parts are equivalent barotropic. But what we can sort of see just by comparing the centers of these anomalies is that the part in the tropics is sort of up in the upper troposphere, whereas the center is located lower down in the mid to high latitudes. So this wave is not just propagating horizontally, but it does sort of suggest that this wave is there's also some vertical propagation sort of tilting towards the pole. And so these maximum anomalies are shifted towards lower levels. And we do see stronger ascent at 400 hectopascal, sort of near this region of beta star less than 0, sort of supporting this development of the equivalent barotropic structure of this wave train in the mid to high latitudes. So some more evidence for this mechanism is provided by looking at this similar experiments in a simple linear GCM. So in this experiment was run in a very similar setup with heating imposed at 100 east at the equator. And so just basically comparing what this simple model looks like in the top with my CAM5 results, and they do have similar features. It's just mainly that the simple model lacks sort of that some subtropical pattern, but otherwise they're sort of very similar. And so what we see here, so this is showing the wave activity flux as well as the geopotential height anomalies in the simple model. And so the wave activity flux, essentially tracing the wave propagation on day 9 of the integration. And what we see in this simple model experiment, this wave response coming from the Eastern Indian Ocean, at 250 hectopascal, the waves appear to converge to the south of Australia when they hit this barrier to Rossby wave propagation, showing that the wave is indeed blocked. Whereas if we look lower, so below that barrier, the waves seem to be able to propagate more freely across the south of Australia towards this low here, shown by these relatively larger vectors south of Australia compared to aloft. So finally, just to summarise, so it seems that this response to heating in the Eastern Indian Ocean has 2 timescales. We see this wave strung out in the wave-guided subtropical jet in the first week, and then in the second week, this mid to high latitude wave train appears, which is equivalent barotropic and seems to be able to go underneath this shallow region where the meridional gradient of absolute vorticity beta star becomes negative. So essentially avoiding that region. And while I sort of didn't show it here, I only just showed the wave activity flux in the simple model, but there is also some indication, at least in CAM5, that wave activity can also pass through this beta star less than 0 region, shown by wave activity flux vectors that seem to just be able to go through that barrier. Lots of studies have suggested that transient eddies are also important, and I do find that it does reinforce the wave train in CAM5 to the south of Australia, but it doesn't seem to be an important required step, because this wave train does look similar and is able to propagate continuously, propagate in the simple model. And while it's sort of not directly sort of indicating these results, it is clear that the representation of this teleconnection does depend highly on the model's mean state. And you can imagine that there are errors in, say, the representation of the winds. This will have impacts on the Rossby wave source and beta star, which will then cause differences in how these teleconnections exist between models. Thank you.
Thank you, Zoe. Very nice talk.
Thank you.
Now, it's questions? Ella?
Yeah, I guess your arguments all make sense to me, but I was wondering if you thought about any role for the meridional wind. I know that there's been arguments have been made for how Rossby waves can propagate across the equator when you have meridional winds, because I guess the arguments related to beta star are kind of neglecting any potential role of the meridional wind. But I suppose probably your idealized experiments have pretty different meridional wind climatology than the full ones. But I just wondered if that's another factor you had considered.
No, I haven't sort of given much thought to that. Is that sort of just in the tropics that you're saying?
Yeah, but I guess I'm not sure if the same arguments would apply in this region, but there's papers by Schneider and Watterson in the 80s. And I'm not familiar with all the details, but they definitely argued that was how Rossby waves could propagate across the barrier on the equator when you have easterlies, and that maybe a similar thing would be relevant.
Okay, I'll have a look into it. Thank you.
Okay, Yusha, do you want to ask your question directly, or you want me to read your question?
So you're asking how high, if it can go above that beta star less than 0 region? I haven't actually looked to see how high and it continues, but certainly I think it could be possible. But yeah, I haven't actually looked into it. I'll still have to see how far it does exist.
Any other question? No? Okay. Now let's move on to the next. It's the CBCW updates, and the open discussion will lead by Ella.
Okay, thanks. So thanks everyone for staying around for this discussion. Hopefully we can get some feedback from you on things here, and let me share my slides. Okay, does that look good?
Yep.
Okay. So I'll give an update on behalf of the other co-chairs of the CVCWG and the liaisons on things that have been happening or are about to happen in the working group. And then we'll also have some updates from other members of the Climate Variability and Change Working Group community on things that they have been doing that might be of relevance to everyone else's research. So here's an outline. So we'll start with an update on the new simulations that are either available now or about to be available. And then I'll talk about the plan for the forthcoming simulations that will be done over the next year to year and a half with this current round of allocations. And then we'll have some updates on resources or tools that are relevant to the CVCWG. So Clara will mention the CVDP for large ensembles, which is a new diagnostics package that's available now. And I forgot to mention Dave in the program, but he's going to give an update on the climate data guide. And then we'll hear from Young-Oh and Sarah, who are both working on configuring new kind of modeling tools that might be of interest. And then we'll have an open discussion. So it'd be great if you could think about these questions and provide any feedback on any simulations you think the working group should be doing. And when I mention the forthcoming simulations, if there's any particular analysis you're keen to do, we want to make sure we output all the necessary variables. So please think about that. And then obviously any other thoughts on working group activities or directions are very welcome. So one thing that's happened since the last time we met is that Jerry's term as co-chair has ended. So Jerry was a co-chair for 10 years, I believe, since the CVCWG began. And before that, he was the co-chair of the climate change working group. So thanks to Jerry for everything that he's done for the working group over the years. And then, so Aishu, who was chairing the last session, has now taken over from Jerry as the co-chair of the CVCWG. So I'll begin with the new simulations that are available or about to be available. And please jump in if you have any comments or questions as we go along. So this is not necessarily a climate variability and change working group set of simulations, but many working group participants have been involved. And so this is the CSM2 large ensemble, which is well underway at this point. And so this has been a joint effort between ICCP in Busan in South Korea and NCAR. So ICCP has provided all of the computing time for this effort. And the project leads are Gökhan Danabasoglu, Clara Desser from NCAR, and then Keith Rogers and Axel Timmerman from ICCP. And there's been important contributions to this from Nan Rosenblum, Jim Edwards, and Sin-Sean Lee, who have all played a role in getting this up and running, and many others as well. So you may have heard about this already, but in case not, I'll just kind of give a summary of what the CSM2 large ensemble is going to look like. So this will be a 100-member ensemble initialized in 1850 and extending out to 2100 using the SSP 370 scenario after 2014. And so one of the things that was done a bit differently this time compared to the CSM1 large ensemble was the way the ensemble was initialized. And so it was decided we should take advantage of having these 100 members to explore the impacts of different initial conditions on the ensemble. So 20 of the members are going to be what's termed macro members, where each of these are initialized from a different state. And these states are taken 10 years apart over the 200-year period from year 1000 to 1200. And then the remaining 80 micro members are split up into 4 groups. And they're termed micro because within each of these groups, they're initialized from the same state, but with a random noise perturbation to the temperature field. So within each of these 20 micros, they're being initialized in the same way as the CSM1 large ensemble. And the years that were chosen for initialization were based on the state of AMOC. So here what you see is the time series of AMOC, sorry, I should have said that before, in the pre-industrial control from which all of these members are being initialized from. And so these 4 micros are being initialized. One set is from a high AMOC state, one from a declining AMOC state, one from a low AMOC state, and one from an increasing AMOC state. And so some things were kind of realized after the first 50 members were run. And so there are some changes between the first 50 members and the second 50 members. In particular, some bug fixes, but they're not really massively climate changing. But there is going to be a change in the biomass burning emissions in the late 20th and early 21st century between the first 50 and the second 50, which will be climate changing. So just something to bear in mind for your analysis, but that will be made clear, I'm sure, in the the paper that describes this. So the current status is that I think nearly 90 members have been completed, and the last 10 simulations, which are referred to as MORs, which stands for Mother of All Runs, because they have enhanced high frequency output, they're either about to begin or have just begun. And so there's a description paper, which is being prepared by Keith Rogers from Busan, and should be submitted soon, I guess, when these are finished and when the analysis is completed. And so then you can expect the data to become available at some point after that, probably May. So sorry, but late spring, early summer is when you should expect that to be available. So now I'll just talk about some of the simulations that have been performed by the working group recently. So we have a series of historical simulations with prescribed sea surface temperatures. And these have actually been available for a while, but recently they've been extended out to 2019. And I think given the current kind of extreme drought in the Southwest, I think it would be interesting to try and extend these out to 2020 as well. So hopefully we can try and do that soon. And so there's a 10-member ensemble of simulations with prescribed observed sea surface temperatures over the whole globe, the GOGA ensembles, and then a 10-member with prescribed sea surface temperatures just in the tropics from observations, and then climatological SSTs from observations in the extratropics. In addition to that, and this is new, there are now CSM2 pacemaker ensembles available. And so these are following a somewhat similar format to the CSM1 pacemakers, but with some differences. So it's a 10-member ensemble. And one of the differences is they start a bit earlier. So they start in 1880, whereas the CSM1 pacemakers started in 1920. They now extend out to 2019. And again, it might be nice to extend these out to the end of 2020 when we can. So this involves relaxation of the anomalies in sea surface temperatures in the tropical Pacific towards observations. So you reproduce the variability in tropical Pacific SSTs in the way that follows observations. And so one of the things that's a bit different from last time is the mask that was used to relax the pacemakers. And this was based on a suggestion from Dylan Amaya. Before the relaxation, which is done in this rectangle in the East Pacific, and now the relaxation towards the observed SSTs is being done in this with this wedge that extends into the Western tropical Pacific as well to try and better reproduce the SST anomalies in the West, but without interfering with regions where it's thought that the SSTs might be responding to this variability rather than or to the atmospheric response to this. One of the things we've added to the website, which you might want to check out, is kind of step-by-step instructions for how to set up your own pacemakers. These are really only work for CSM2. So if you are interested in CSM1, you need to get in touch and we can maybe add instructions for that at some point if it's popular too. So any feedback on this, if anything's not clear, please let us know. And in general, I feel like it would be good if we could document these kinds of recipes for doing these kinds of experiments. So if you do something and it's relevant to the working group and you have a publication and you want to describe the method for other people to reproduce it, I think it would be great if we could start some kind of recipes page for doing these kind of idealized experiments with the model. Another thing that's been done is an extension of the CSM2 pre-industrial control series. So some of these were already done a while back. We had extended the coupled pre-industrial control out to 2,000 years. Now available is a 1,000 year long uncoupled pre-industrial control with CSM2 that has SSTs prescribed toward the seasonally varying climatology from the coupled run. So this only has atmospheric and land variability. The SSTs and sea ice are prescribed to climatology. And then there's another new run, which is 500 years long, which is also an uncoupled run, but this one does have SST variability because we prescribe the full time varying SST variability from the coupled run. And the daily SST variability has been prescribed. So these three simulations might make a nice set of simulations to compare the role of coupling versus the role of having SST variability versus the role of just having internal atmospheric variability. So these are simulations that are currently underway, and so you should expect these to be available in the near future. So Nan Rosenblum and Sasha Glanville have been running a single forcing large ensemble, and so this will be complementary to the CESM2 large ensemble using the same model version and the same forcings. And unlike the CSM1 large single forcing large ensemble, which the tactic there was to have all the forcings evolving except the one that you're interested in. For these ones, all other forcings are being kept fixed at 1850, and the forcing of interest is going to be time evolving. And so quite exactly how many members we'll end up with or how long we'll go will really depend on the resources. At the moment, we're able to run an economy, so if that keeps going, we should be able to get more out of the computing allocation than if it doesn't. But the plan is to have at least 10, maybe 15 members for each forcing. At the moment, they're being run out to 2050, but if we have the time, we'll likely extend them out to 2100. And it was decided that we'd do 4 different forcings or sets of forcings. So the first, just greenhouse gases, and that one's well underway. The second is just industrial aerosol forcing. The third is just biomass burning aerosol forcing. And then the fourth is everything else. So this will include land use, land cover change, ozone changes, solar forcing, volcanoes, and a number of other things. And so the idea here is that assuming linearity, you could add up these to the overall evolution. Another ensemble that is underway and will be complementary to the CSM2 large ensemble is a 10 to 15 member ensemble with the lower forcing scenario, so the SSP 245 scenario. And that should be, 10 to 15 members, and they will be run out to 2100 under that scenario. So now I'll talk about the forthcoming simulations. And so these are things that are definitely not set in stone. So any feedback is obviously very welcome. So one of the things we had planned for our second year of the computing allocation is to do a regionally refined North Atlantic AMIP simulation. And so the idea here is to go down to 1/8 degree resolution in the North Atlantic and run from 1950 to present day with prescribed observed sea surface temperatures. And definitely open to suggestions on this, but it seemed like a sensible way to go might be to use the HADIS2 SST data set, which is 1/4 degree and goes back to 1950. And that was what was used in the high-res MIP protocol. So there could be a number of motivations for this simulation. The one that I'm primarily motivated by is the kinds of things that Haiyan talked about in her talk earlier, this possibility that our models might be deficient in the representation of eddy mean flow feedbacks and the response to sea surface temperature variability in the extratropics. And I think we already know from the high-res MIP simulations that going to 1/4 degree doesn't make things better. And so this would be a chance to have go to 1/8 degree, which I think is higher than most people have gone, and have a full historical length simulation. I feel like the chances are very high that this may not work out in the way that I wanted to in terms of North Atlantic variability. So my hope is that there can be many other applications. I mean, I think it'll still be useful to demonstrate that, but it will be great if there are many other applications for this run because it will be quite expensive. And so we already have a student from UQAM who's interested in studying polar lows. And if there's anything in particular that you want to look at in this simulation, please let us know so that we can make sure that we save the right output. And so we haven't started this run yet, but some work has been done thanks to Adam Harrington and Rob Wills to configure this domain. And so this is kind of the plan at this point, but this is also still somewhat flexible since we haven't started. But just to show you some results, these are from Rob, and he's been using the same configuration, but with a sort of different SST perturbation than what we will be doing, a kind of idealized shift in the Gulf Stream. And so he's prescribed a southward shift of the Gulf Stream in the SSTs. And the top panel shows what you get in response to that with the 1/8 degree resolution over the North Atlantic. And the lower panel shows what you get at the 1 degree resolution. And so these runs are very short at this point. They're only 4 years long, but Rob has tested whether there's kind of confidence if you divide them up into two-year segments in this difference. And it does seem like it could be, but it will be nice to run these out longer. But it definitely indicates that there might be interesting things that could come out of this run in terms of ocean atmosphere coupling in the North Atlantic. Another simulation that's planned is using a higher vertical resolution. So you may have heard or may not have heard that the CAM is going to go to a higher vertical resolution for CAM 7. And so here what I'm showing is the vertical grid spacing in a few different configurations. So the way to read this is on the bottom is the vertical grid spacing. So down here is higher resolution. And then this is height in the model. And so black is our current high top model, WACM. And then gray is our current low top model, CAM, which is what we use for most applications for the CVCWG. And so CAM does not have a well-resolved stratosphere. The model lid is very low. And so there's a plan to make a kind of intermediate model, which will have a higher lid, but not as high as WACM. So it should have a better representation of the stratosphere. And it's also going to have higher vertical resolution in the troposphere, which will allow it to have a representation of the QBO. And so many things are going to change as we go to CAM 7. And so one of the simulations that was proposed by the working group is to run a pre-industrial control where all we do is change this vertical grid. And that would be kind of a clean examination of the influence of this new vertical grid. And it also will be a validation simulation for a new set of simulations that are planned by collaborators at Scripps who want to run some initialized hindcasts with this new vertical grid to look at the impacts of having a QBO and good representation of the stratosphere on the hindcast performance. Okay, a few other things that are planned for CVCWG simulation. So there's a plan to run another pre-industrial control, this time using the pencil model, which is kind of a step between a slab ocean and a fully coupled ocean. And we're going to hear from Young-Oh about that in a few slides' time. So when this is ready, we will be running a 1,000-year-long pre-industrial control with that and a 10-member ensemble of historical simulations. There's also a plan for Indian Ocean pacemaker experiments, which will follow a similar protocol to the tropical Pacific ones, but for the Indian Ocean. There was a lot of interest in running a pre-industrial control with stochastic physics, and so computing time has been set aside for that, and so that's one of the plans for the next year. If the stochastic physics configuration can be tuned and is up and ready, maybe there's people involved in that on the line who might be able to clarify whether that seems likely or not. And then another simulation that might be of interest is one planned by Brian Medeiros to look at regionally refined tropical belts. So similar to what we were talking about with the North Atlantic, but with a high resolution belt in the tropics. And the original plan was to run with a 1/4 degree resolution. Depending on computing time and interest, Brian may run with 1/8 degree resolution, which would allow to have a look at things like tropical waves, MJO, and things like that with high resolution in the tropics. Okay, so we'll move on to what's new in terms of resources. And for that, I will hand it over to Clara to tell us about the CVD-PLE.
Thanks, Isla. This is amazing. I think what you are doing, all of you in the working group, I think these resources are fabulous. So with all these simulations, you might need a tool to look at them. So we have developed, Adam Phillips especially has done all the heavy lifting to develop a new version of our climate diagnostics package, but tailored to large ensembles. So like the CVDP, it is this automated tool. You don't need to know anything about the coding. It will produce for you lots and lots of metrics of many, many modes of variability in the ocean and the atmosphere and the sea ice. And the new thing here really are these summary metrics on, we give graphics and all kinds of pattern correlations, et cetera, RMS differences. And you can look at the ensemble mean, i.e. the forced response, and you get output for the ensemble spread. So it's a very, very valuable tool to do model evaluation, do the observations sit with it in the ensemble spread, and also to be able to compare models properly. So the code is available on GitHub, so you can just run it yourselves on whatever data files are of interest. Adam and I gave a joint seminar in November, and it's posted on the homepage for this package, if that is useful to you. And then in this red box, that's the extensive user's guide. And user's guide is maybe a bit of a misnomer. It's not just a technical document, but it really gives you a big picture of, what large ensembles are valuable for and how the diagnostics in this package really help you to answer many, many questions. So I encourage you to take a look at that. I think we can I just have eye candy on the next slide, if you wouldn't mind. Yeah, so for example, and it's just a incredibly valuable package. So here I've just pulled out one of the many, many types of graphics and metrics that you get. And this is all of the output files are saved to a data repository, so you can do your own further analysis. But this is looking at the NAO in the winter, defined as an EOF of sea level pressure. And it's just looking at over the historical period for each ensemble member of all these different CMIP6 models, how well they produce this pattern, this observed pattern of the NAO. And so you can see that, there is some spread in that pattern correlation. And importantly, we can finally then, compare distributions of pattern correlations across models to see if models really are structurally different. If their distributions don't overlap, where you can see I've pointed to two models that don't overlap, or if they overlap, then we know it's just, the luck of the draw in terms of the internal variability masquerading as structural differences. So I encourage you to take a look at this tool. I use it all the time just to explore and kind of bring up unanticipated questions and results that leads to some nice work. So we always love feedback. We're very happy to add different modes and metrics to the package. You just let us know what would be valuable. Thanks.
Thanks. So I think I'm not able to see everything properly, but I feel like some people have raised hands. Aishu, I don't know if you can. Are there questions about this or?
Yeah, I think Maria seems to have a hand raised.
Okay, yeah, go ahead, Maria, if you want to ask something now or.
Yeah, thank you. Yeah, it's about the CVDP for large ensembles. Thank you so much for this tool. It's really wonderful, and the visualizations are great. I took a look at the PDF document that offers more information, and I also attended, I think it was a research report or CGD seminar where there was an overview provided on the package and the tools. I was wondering if the snapshot EOF is a part of this. I wasn't able to quite find it in the PDF document. And then if you also have plans to add to your GitHub repository any Jupyter notebooks, example usage of the package, and if not, if there's interest in that.
Great, thanks for your feedback. So we did not include snapshot EOFs. I didn't want to delay the release of this package too much. It was an unbelievable effort on Adam's part to code this all up efficiently so that it runs quickly. I think snapshot EOFs are just such an excellent tool for looking at large ensembles, as we heard from JP earlier today, and other people have done work on that. So I actually, in the next rendition, I would love to include snapshot EOFs. The second question about the Jupyter notebooks, we haven't even talked about that yet. And at this point, I don't think, well, I think we need Adam on the line here to comment on if that is something we would do in the future. So I'll definitely, you and I and Adam can talk about that. That would be good. Thanks.
Thank you.
Okay, does anyone else want to chime in with anything at this point? Okay, I guess if anyone notices someone's hand raised, please just let me know because I'm not able to see it. Okay, so now is Dave, who's going to tell us about the climate data guide.
Thanks, Ella. So following from Clara's presentation, if you are evaluating models, you may need some observations to use in your model evaluation, and you may have some difficulty in deciding which observations to use. On the other hand, you could be an expert in the observations, and you may have some expertise on the strengths and limitations of observations to provide to the community. So whether you're a novice or an expert in the observations, you can use the climate data guide. So we have many users of this climate data guide, and the users have been growing steadily over the past several years. So what's new about the climate data guide? We have a plan to modernize the web interface with support from NSF over the next few years. So we'll be building an entirely new website. So if you look at it right now, you may notice some things that look outdated. So we'll be updating it hopefully in the near future. We also have a new board of advisors, or BOA, which is kind of like a mini working group just for the climate data guide, but it's a little less formal. So we have experts from a range of disciplines that meets quarterly, and they'll be advising on increasing the number of data sets, fixing the stuff that's out of date, and diversifying the types of data sets that we cover. And this is a great group of people that we have on the BOA, and I'm sure we could always accommodate one or two more people if anyone is interested in joining this group. And if you have any specific questions about the climate data guide, you can contact me at this email address. So that's it.
Great, thank you. Okay, so now we'll finish up with some information on a couple of exciting new developments in terms of modeling tools. So the first is from Young Oh, who's going to tell us about the pencil ocean model.
Thank you, Ira. So I'm going to spend a little bit of time to talk about the pencil ocean model. So it's an effort by many people spent on fairly long time and still going on. So I probably haven't mentioned someone here, but it's a team effort by many. And so I would like to introduce pencil model in the context of different choices we can make for the ocean model in CESM. So obviously there's a full ocean model right now, it's POP, and it's going to be POM 6, the next version. So it tells you everything in the ocean. So there's interaction, the vertical and horizontal, the advection and the mixings. So next, please. Another obvious tool we heard today already is the slab ocean model. So it's just one column at each grid point. And it basically just have S interaction enabled. And the thickness of slab or the mixed layer, that is not changing over time. So next. The simplest one is the true or pure data ocean. So it doesn't respond to atmosphere, but it SST acts as a boundary condition for atmosphere. So this is a typical, the options you have now from the CSM. So next, we would like to squeeze in one more so-called pencil ocean model. So it's an array of 1D columns. So at each grid point of ocean, we enable AS interaction. It's multi-level model. So it has prognostic mixing and the mixed layer that's boundary layer that's calculated, but there's no exchange laterally between the grid points. So it's one hierarchy is simpler than the full ocean, and it squeezes in between the full ocean and slab ocean. So next. So progress is so far, we have been implemented the pencil ocean model in the ocean component model. So we are using the POP structure rather than bringing some other model. So we are just disabling horizontal processes in the POP and leaving the KPP do the vertical processes. And we've been doing that in CSM 1 and CSM 2.2. And we've been conducted multiple about 10-year-long test simulations. So as of now, we are actually migrating this to the official version we're going to implement, which is the CSM2 Lens version, which is 2.1.4. So right now we are working on to bring this in this version. So next. So once we finish the implementation in the CSM Lens version, we're going to have long pre-industrial control that Ayla mentioned before. How long we have to see how stable it can go. The target is 1,000 years. And then also, I forgot to list that the 10-member historical simulations. And after that, we will add one more capability to the pencil model. So right now, pencil model doesn't have any oceanic lateral exchange between the grid cells or columns. But we can add one more simple Ekman transport that's passive to the atmosphere wind. So we have planned to implement that as a next step and do some experiments. That's it.
Great, thank you. Yeah, it will be very exciting to run these experiments when it's ready. Okay, and so then the final thing to talk about is this coming from Sarah Larson about a mechanically decoupled version that she is developing.
Yeah, apologies for my lighting. It's pretty dark where I am. And so now I'm going to have to update my hierarchy with Youngo's pencil model, I see. So that'll be nice. So this is an NSF-funded project. So we're taking what we're calling a mechanically decoupled version of now CESM2, and we were really funded to update it, experiment with decoupling the sea ice model, and then pushing this forward into historical, not really large, maybe more like a 30-year historical ensemble, and then later on a future ensemble. So initially the kinds of questions we were trying to answer with a model like this is, how does wind stress or anomalous wind stress on the ocean surface contribute to climate variability and ocean variability that we see? And so to make what we call this mechanically decoupled model is we're removing that anomalous wind-driven piece of the climate system. And so where it sits in the model hierarchy is here on the top left. So you have your fully coupled version where the atmosphere and the ocean interact through anomalous freshwater fluxes, heat fluxes, and then momentum fluxes. And then if we look at, and obviously has its dynamic atmosphere and its dynamic ocean. On the other side of the complex model hierarchy, we have the slab, where we have an atmosphere, a mixed layer ocean, and they're thermodynamically coupled. And so the issue I think a lot of us have faced in the past when trying to compare the slab ocean and the fully coupled is that we're really jumping two kind of tiers of complexity to get there. We're adding a dynamic ocean and we're adding that momentum coupling. So what we've done is we've been developing this version in the middle, the mechanically decoupled, where we have a dynamic atmosphere and a dynamic ocean, and they're connected through anomalous buoyancy. So we've removed that anomalous wind-driven piece. And the way we do that is by just allowing the ocean component of the model to feel wind stress climatology. So we basically can reproduce the mean ocean circulation. We have seasonal variations in the mixed layer depth. We have a lot of that realism that we feel like we're missing in the slab ocean model. We get a lot of that in the mechanically decoupled version. So one thing we've done, and I have one more slide, my postdoc Kay is gonna show some results. We've also experimented with decoupling the sea ice model too. And as you'll see, it may have made things a little too complicated. So when we push to a historical or a future climate run, we may just decouple the ocean model and not also the sea ice model. And I think when Kay shows you these results, that may make a lot of sense to you. So the experiments that we're running are multi-century pre-industrial control, and so long enough basically that we could look at the AMOC and AMOC statistics. We've got about 30 or 40 years currently, and then a historical and a future ensemble. So what we've done so far, we really just started in December, so we've been really hitting the ground running as we've updated all the code for net CDF capability. So if anyone wants to try to reproduce versions of this, it'll be a lot easier than if you have my legacy code, which I know some people have. It's pretty tough to deal with. We've also decoupled the sea ice model from anomalous momentum fluxes with huge help from Dave Bailey. He's been a really great help for us. And so the way we do this is we're prescribing wind stress climatology on the ocean, so POP, and then U and V from the atmosphere at the bottom level for sea ice. And so we're doing this on 6 hourly, we're using 6 hourly climatologies, which is a huge improvement from the monthly and daily that we've done in the past. So you should actually be able to use some of the daily output from these experiments. And then finally, we're trying to match apples to apples with the fully coupled versions. And Isla has been a really big help in making sure we're doing that correctly and using the proper CMIP6 version. And just as one quick example, this is usually how we tell if the ocean model is doing what we think it should be doing when we disconnect the wind stress coupling, is we look at ENSO. So this short circuits the Bjerknes feedback. So ENSO should go away when you do this mechanical decoupling. And you can see in the bottom right that even though we only have a few years to look at, there's definitely no large interannual ENSO variability. You can't see my cursor, but I'm pointing to the red curve that you see there. Yeah, and so I'm gonna pass it to Kay. So Kay is my new postdoc. He's been looking at some of the output from this run. And so kind of the issue we're facing now is if we wanna do a future climate ensemble, if we also decouple the sea ice, you'll notice that the sea ice changes drastically. And if we were sea ice experts, maybe we would have anticipated that a little bit better. But for the reasons that he'll show, we will probably just decouple the ocean for the future runs. So I'll turn it over to Kay.
Okay.
Thanks, Sarah. Yeah, so these are some results from comparing the mechanically decoupled and the fully coupled control runs for the years that we have. And the ocean is doing, I think, broadly speaking, what we might expect. So on the bottom left here is the AMOC maximum strength from those two. And you can see that generally speaking, we have a similar strength AMOC in the mechanically decoupled model. but it's a lot less variable, which is also what we would expect. We've disconnected this anomalous momentum forcing, so there should be less variability. Towards the end of the time series, it looks like maybe AMOC is becoming stronger in the mechanically decoupled, but it's a bit hard to tell if that's related to some of the things happening with the sea ice or if that's just something to do with variability that we kind of can't see with only this 30-year time series. And then looking at the sea ice, these two contour plots are showing the decoupled run minus the control run. On the left is the ice area, and then on the right is the ice thickness. So basically the red all shows an increase in ice in the mechanically decoupled run as compared to the control. So broadly what we're seeing is there's more ice pretty much everywhere in the Arctic in terms of ice area, and then also the ice is thickening in most places. And so trying to make sense of what's happening there, the seasonalities generally agree, so I think that's a good thing. We still have the most ice at the same time of year between the mechanically decoupled and the fully coupled, but the ice velocities have slowed down a lot, which is maybe to be expected since we have less variability in the winds. There aren't really large anomalous wind events. And so the ice velocities have slowed down, and then it seems that the ice has kind of aggregated and thickened, and maybe that potentially leads to more ice slowdown once the ice is too thick to really keep moving, and maybe there's another feedback there where then that leads more to ice thickness. Neither Sarah nor I are ice experts, so if anybody has comments or questions on that, mostly comments would probably be helpful, but we have been talking a lot to Dave Bailey. And then you can also see that in the time series on the lower right, the red curve is the control, where the ice volume's pretty constant over time. And then the blue curve shows the decoupled, where the ice volume really increases over the first 20 years. And then maybe it's kind of reached an equilibrium in the last 10 years or so.
Excellent. Yeah, very exciting developments. So I guess that's it in terms of updates. And so now we'll just have an open discussion. So if anyone has any questions on anything you've just seen, or just generally any comments on anything to do with CVCWG, I'll maybe stop sharing my screen now. Okay. Okay, yeah. Yeah, Clara just pointed out to me that I did not have the URL for the CSM Too Large Ensemble on my slide. Yeah, there's a website. I'm sure you can come across it if you Google it, and I'll add it to the slides that Elizabeth will post. See if there's anything else in the chat. Okay, well, I guess I have a couple. Oh, Maria, did you still have your hand up from before? Oh, okay, you have a new.
Oh, it's new.
Yeah.
Okay. You mentioned, so being new-ish, it's been like 5 months now that I've been at CGD, but you mentioned you could do like an overview about the working group, maybe a few details for people that are not familiar.
Yeah, sure. Sorry, I thought, yeah, maybe I should have done that at the beginning. So yeah, I guess well, CSM has multiple different working groups, and for example, the atmospheric model working group and the ocean model working group. And so most of them are focused on developing the model components, but the climate variability and change one is more focused on analyzing and running simulations like the ones we just described with the model. So really, we're given a certain amount of computing time each year, or every 2 years, we write a proposal for these kind of big experiments like we've just talked about, like the single forcing large ensemble or augmenting the pre-industrial controls. And then we make those available. So aside from running the simulations, I guess it's just a group of people with similar interests, and we have meetings like this twice a year, the winter working group meeting, which we're at now. And then there will be a meeting at the CSM workshop, which will be in June. And then we have a mailing list. So if presumably since you knew about the meeting, you're on the mailing list, but if you're not, then please join. And that's where we would make announcements about anything new, like the CBDP for large ensembles, or simulations that are available, or workshops and things like that. I don't know if Clara has more experience than me, if I have missed anything important.
Sounds good.
Does that cover your questions, or do you have anything else specific you wanted to know about the working group?
Thank you. That was great.
So I guess I had a couple of questions, and I don't know if Youngo or Sarah are the people to answer them, or maybe people from the Ocean Model Working Group. I was just wondering, I mean, your configurations seem like they're going to be really useful. And as we go to MOM, I'm wondering what will happen. Will POP still be around that we can run these configurations within there, or will it be easy to do the translation into MOM, or will that be a big effort?
So, well, you saw Gokhan's name in the list, so we are mindful of the transition going on right now. But rather than waiting for MOM6 implementation to finish, we thought to if we know how to do it right in the POP, it's not going to be too difficult to implement on the MOM6. So,
okay.
Yeah.
Yeah, that's good. And I guess for Sarah, yours is maybe more in the coupler, so maybe it doesn't matter so much, or?
Yeah, so right now the decoupling for the Ocean model is actually done in the Ocean model when it receives information from the coupler, and then the sea ice model is actually in the sea ice. The sea ice decoupling is in the sea ice model. But in general, it's a pretty straightforward process. You really just need your forcing files and to make sure you're reading them in with the right format and all of that. So I think with the right, partnership with someone who is familiar with MOM, I don't see it being a year-long effort, maybe like a month-long effort to get it going.
Okay, that's good. That's reassuring. Clara?
I just wanted to emphasize how unique this hierarchy of model simulations within any modeling framework is. I know of no other modeling center that will have a fully coupled version, a slab version, a pencil version, and a mechanically decoupled version. So first of all, I just thank everybody who is, contributing to this hierarchy, but also it just speaks to the value of our community and, these working groups and CESM and the way that, we conduct our open activities. This is what it leads to. And I'm just, it's just a really incredible resource that the community is building together. So just wanted to emphasize that as a past co-chair and wanting a pencil model for the last 10 years. And, finally these things are happening and I'm just really, really happy.
Yeah, it definitely seems important to be able to keep things going so that, with CSM3, we can run controls with all of the versions. And weird.
I have a question along those lines. So as these other versions of the model are spinning up and we're getting a bunch of output, and maybe this is something we can talk on offline about with Youngo, is sort of how do we organize this data, and because we're sort of external members, right? So really how to facilitate the community being able to have access to this, I think is something that's worth talking about at some point.
Yeah, definitely. I don't know if Gokhan's on the line, if he's there's definitely some things have come up recently where I think we don't really have the allocation to house the data for simulations that other people have done. But I definitely agree that it's important. The ones that we do under the working group, I think we have the allocation to store the data on Cheyenne and then make it available. But I think it becomes more difficult when other people have run them and we haven't allocated the space.
So hi, this is Gary Strand. I'm the CSM data manager, and a member of this working group. So we can, yeah, that's true. We don't have an allocation set aside for non-NCAR based CVC, WG related simulations, but let's talk. I mean, I don't want to say no now, excuse me, no now and forever, but this is one of the things that I've been exploring is, people that are using the same model as we are outside of NCAR doing very interesting science and very interesting research. How can we assist them in getting their data out to the community? So let's start our conversation and just take it from there. I'm very interested in this.
That's great, Gary. And I just want to add, Sarah and Young-Oh, it's not just, separate efforts outside of the working group. They've really tried to coordinate their experiments. We've had a lot of email. Okay, what exactly are the fully coupled experiments so that they can do the identical protocols with these other hierarchies. So I really see this as, just part of the working group and not, and it just, the sum of the parts is bigger, or whatever that expression is, than the whole. So I'm just wanted to add that.
Yeah, that would be good. I guess CESL does have some, well, now that you can kind of factor in the data into your proposals, right, Gary, with the to budget it.
If you're using like Cheyenne or the next machine, you can factor in storage charges and things like that. But if your stuff was run elsewhere on not on Cheyenne or somewhere else, let's talk. That's all I can say is, let's discuss it and see what we can work out. If we can come up with a solution that makes everybody happy and gets the data to the user community, because that's the most important thing.
Thanks. Any other questions or comments? I did have another question for Young-Oh, and that was just the timeline of kind of when should we be starting to think about running the pre-industrial control. Do you think it's near ready, or months away, or a year away?
So if you push me to answer, I would say a month away. So, I mean,
oh, okay.
We've been exchanging a lot of email with NCAR people last few weeks to get the CSM2 version ready. And I mean, we always have surprise when actually we want to do it, but I think we know how to do it. So we're working on it right now and probably start running in about a month's time frame.
Okay, excellent. Anything else?
You asked people to tell you what data they might want from these runs. I just want to reiterate how important that is to put in your requests now, because it happens over and over again that, things haven't been saved, and then, you're not able to do certain analyses. So really think about that.
Yeah. Yeah, and I guess if you have thoughts later on, then I think my email address is on the working group website, I believe, or if not, I think Adam and Gary's emails are. And so, yeah, email with any thoughts, and we'll get a list going of all the things to make sure we output, particularly for the North Atlantic one, because there might be other things that we don't normally look at because it's such high resolution. I think we'll want to try and save high time frequency fields and yeah, we kind of have our standard outputs for the other ones, but this will be a bit different. Does anyone have any thoughts on the SST forcing data for that simulation? I think our choices are either kind of the ones we normally use at 1 degree or HADIS 2 at quarter degree. Oh, Steve.
Yeah, sorry, I'm trying to unmute myself. Yeah, when I saw that slide, I was just wondering if quarter degree is going to be sufficient for such a high resolution atmosphere, and whether you might think about using output from some of our 10th degree simulations. But I mean, obviously,
Yeah.
it would be an AMIP experiment then, but it might improve the air-sea coupling at high resolution.
Yeah, I was wondering about that, but I guess we would want to use data from the decadal predictions, because we want to have like the real world decadal
Right.
variable.
So we're now starting our high resolution decadal prediction runs as part of the IHIS project, and we're using a high resolution FOSSI, so the equivalent of the low res run that we're using for SMILE, and it's fairly realistic. Obviously, it's not observed SST, but it's about as good as you can get with a forced ocean simulation.
Okay, yeah, I think that would definitely be a good idea. I didn't realize, I wasn't sure if the IHES was just going to be certain years. I didn't, but the FOSSI, I guess, would make sense to use that. I think that's a good idea. Rob, did you have a comment on that?
Yeah, I think that's a great idea, Steve. I guess we were running into problems that there's not really any good observational data sets at higher resolution that aren't susceptible to biases over in cloudy regions and so forth. But I will say that the results of mine that Isla showed, this is actually with one degree SST forcing, and it's already seems to make a big difference. The higher atmospheric resolution.
That was just the prescribed shift of the Gulf Stream, right?
Yeah. That's not to say that imposing higher resolution SSTs would open up a whole new set of questions. So I do think there would be value in that, but it's hard that we can't have both necessarily with how expensive the simulation is.
Yeah, I was wondering exactly if if we want to be able to compare the 1 degree model with the eighth degree model, then you need the same SSTs. Otherwise, you're not sure, is it the higher resolution and the SST forcing, or is it the model? So there's always going to be a bit of ambiguity.
Yeah. But I guess if we hit it with both the high resolution SSTs and the high resolution atmosphere, we maybe have more of a chance of getting something interesting, which would then promote subsequent experiments that we could try and pull it apart. And rather than going halfway there with the low resolution SSTs, not finding anything and then giving up, I don't know. Okay, yeah, I could see arguments either way. But it seems, I feel like it does make sense to just go for it with everything high resolution.
It would be easy to.
We can definitely discuss further.
It would be easy to run the lower resolution model with the high resolution SSTs as a supplement.
Yeah.
I mean, it's not going to cost very much in comparison.
That's a good idea.
Yeah. But I guess it wouldn't tell us whether we need both. It would eliminate the SSTs in isolation, but. Any other thoughts? We are at 4:30. Everyone's probably had enough Zoom for the day. Well, I guess we'll finish up there. Thank you for joining, and I guess I hope in the next winter meeting, maybe in person. And thanks for all the great talks and all the feedback on all of these things. And please get in touch with anything